Introduction to Universal Relativity. My name is Tripp Zejda. I wrote this as a concept first front door to universal relativity and to the determined recursive resolution state interface, RSI, that powers the rest of the manuscript. This is a book-length introduction to a single claim. The world is not fundamentally a pile of separate force laws stitched together by special cases. The world is a single, present-moment, deterministic resolution process, and the things we call forces are measurement overlays on top of that process. I'm not starting from a desire to replace physics with a new vocabulary. I'm starting from a desire to stop accepting paradoxes and patchwork as the final story. When I say universal relativity, I mean something narrower than a slogan and broader than a single equation. I mean that every physical behavior we measure is relative to context, relative to the lattice of identities in play, relative to the interfaces through which those identities couple, and relative to the present moment resolution constraints that decide what can exist and what must change. If you remove the identities, there is no background geometry left to curve, because in this posture, existence is what generates geometry, not the other way around. This introduction is the story layer. The formal statement of the system begins immediately after this, at the start of part 1, see 1.1. The logic foundation that pushed me into this posture begins here. And if you are the kind of reader who does not want any story before seeing falsifiers, you can jump forward to part 14, C14, for the solve workflow, prediction menus, and the standard reporting posture, and then to Appendix A, CA, for the audit spine and unit checks. If you want the widest, rule-bound long view pass, I collected in Appendix T, CK, but I recommend reading at least part 1 first, so the primitives and gates are not misread. Why I start from paradoxes, instead of starting from equations. The first phase of this work was not a physics phase, it was a logic phase. I kept noticing that the hardest problems in physics and philosophy share a repeating pattern. We encounter a contradiction, we label it paradox, then we build increasingly sophisticated workarounds on top of it. The workaround might be useful, and it might predict real numbers, but the paradox remains sitting underneath as an unresolved logical problem. So I began where I think every honest unification attempt has to begin, with a handful of facts that I cannot coherently deny, exposed by the paradoxes themselves. This is the stance I call existential logicism. It is not a replacement for science. It is the grounding posture that tells me what sort of science is even allowed to be coherent. At the risk of sounding too simple, the core axiom said is this: something is being experienced now. Any attempt to deny experience is itself an experience, so denial collapses into self-contradiction. If experience is occurring, there is an experiencer. I cannot coherently treat consciousness as a pure illusion, because even an illusion still has to be experienced. It is unjustified special pleading to accept my own experiencer status, while denying it for all others who present the same evidence. I treat other minds as real by the same consistency rule that makes any shared knowledge possible. Absolute nothingness is not an admissible state if I exist now. Nothing cannot be the source of something. If I accept reality now, I implicitly reject a true void as the prior state. An infinite regress of explanation cannot be the final answer. A chain that never bottoms out is not an explanation. It is a refusal to explain. Only the present moment is ontologically real in the strict sense. Past and future exist as stored information and projected expectation in the present, not as separate literal realms. Those are philosophical statements, but they are also constraints. They push me toward a universe that is present moment, self-grounded, and not fundamentally probabilistic in its ontology. They also push me toward a universe that does not need literal infinities to function. If something is real, it has a finite description in the present. If something is not real, it has no causal standing at all. From this viewpoint, I do not treat paradox as proof that the world is irrational. I treat paradox as evidence that my language and my bookkeeping are mismatched to what the world is doing. The rest of this book is my attempt to fix that mismatch. The small numerical attractor that taught me a big lesson. There is a simple number routine that a lot of people encounter as a curiosity. Take a 4-digit number, reorder its digits from high to low and low to high, subtract one from the other, and repeat. Unless you start from a degenerate special case, the iteration collapses onto the same fixed number over and over. The best known example is the 6174 attractor, often called Kapur-Carr's constant. I did not treat that routine as mystical or a paradoxical feature of reality. I treated it as a clean metaphor for something deeper. Resolution is a real behavior. Even in a toy arithmetic system, the repeated application of a rule can produce an attractor that the system converges to. The system is not pulling toward the attractor like a force. The system is resolving toward an allowed state under the rule. The Eland RSI strategy is to treat logical truths and mathematical principles not only as tools I use to calculate events in reality, but as reliable mappings between language and reality. I treat their accuracy and reliability as evidence that they can teach me about what the universe is doing at the underlying level, and about what kinds of deeper structures are even allowed to exist. That was the moment my intuition flipped. Instead of starting with pairwise forces and imagining pushes and pulls, I began to ask a different question. What if the world is not fundamentally about things pulling each other, but about configurations resolving, right now, toward admissible states? Once I saw the world this way, I could not unsee it. And it changed how I read almost every physical law I had learned, from pairwise forces to a field response picture. In the legacy picture, I often begin with a force law between two objects. Then I generalize to many objects. Then I add fields. Then I add potentials. Then I add gauge structure. Then I add curvature. Then I add quantization. Then I add renormalization. Then I add another overlay to handle the next anomaly. All of that can work, and much of it does work. But the cost is that the deeper the stack gets, the harder it becomes to answer the simplest question. What is physically happening in the present moment that makes the force appear? The resolution posture offers a different starting point. I treat what exists as anchored identities. An anchored identity is not merely a particle label or a wave label. It is a resolved system that persists, with a definable boundary interface through which it couples to its environment. The presence of an anchored identity produces an immediate structural response in the field context. That response is what we later report as force in the measurement overlay. So I do not begin from object A exerts a force on object B. I begin from identity A, changes the admissibility terrain for nearby configurations, and identity B resolves its behavior relative to that terrain. That is the conceptual seed of RSI. Identities exist or do not exist in the present moment. If they exist, they generate their own effective geometry, meaning they instantiate the coupling carrier at their boundary interfaces. The environment responds to the resulting stability imbalance. The force is a report of that response, not a separate ontological ingredient. Wave-particle duality becomes a category error. One of the biggest emotional barriers to unification is the sense that the world is fundamentally weird. Wave-particle duality is usually taught as if nature is intrinsically schizophrenic, sometimes a wave, sometimes a particle, sometimes neither until measurement. I do not accept that as a final answer. In RSI posture, the deeper claim is that the wave versus particle framing is an overlay language problem. It is not reality's identity problem. What I call fundamental is not wave or particle. What I treat as fundamental is identity, a resolved system that persists through present moment admissibility, with a boundary interface and an internal ledger. In some measurement regimes, the best overlay description of that identity looks wave-like. In other regimes, it looks particle-like. But RSI does not require me to treat that as two incompatible ontologies. It is one ontology, one identity, and two reporting overlays. This posture also clarifies why measurement changes what I see. Measurement is not a ghostly act of observation floating outside the system. Measurement is an interaction, a coupling edge in the lattice. When I couple a system to a detector, I do not reveal a mystical hidden wave function. I change the system context, and the identity resolves relative to that new context. So duality is not an embarrassment I patch around. Duality is a diagnostic that tells me my overlay languages are not primitive. Probability still works, but it stops being fundamental. I have no interest in denying the operational success of statistics. Statistical mechanics works. Quantum statistics works. Probabilistic modeling works in every domain where I have incomplete access to the full field context. The RSI move is not to mock probability. The RSI move is to demote probability to what it often is in practice, a bookkeeping tool for ignorance. When I do not know the full coupling lattice, I summarize it. When I do not know the microscopic phase information, I average it. When I cannot track every edge and every channel, I treat the missing degrees of freedom as a distribution. That is not shameful, that is practical. But it is not the same as saying the universe itself throws dice. In this framework, the deep claim is, a deterministic system can look probabilistic when I do not have full access to its context. The same move shows up everywhere in science. There were eras when the weather looked like chaos, and the sun looked like caprice. As measurement and modeling improved, randomness collapsed into mechanisms. I treat many probabilistic laws in physics the same way, not as lies, but as incomplete overlays. The place where RSI draws a hard line is not no statistics allowed. The hard line is, I do not define reality as probabilistic, and I do not allow probability to function as an unexplained primitive when a deterministic ledger is available. From UEFT to RSI, why I had to build a new language. Before RSI crystallized as its own system, I spent a long time trying to express the same ideas in legacy language. That effort is what I called Unified Equilibrium Field Theory, UEFT. UEFT did something important. It forced me to articulate the idea that the cosmos can be seen as a present moment equilibrium field, whose apparent dynamics are resolution behaviors, not fundamental pushes and pulls. But UEFT also hit a ceiling. The ceiling was not math, the ceiling was language. Legacy tools can describe the world with stunning precision, but they also bring their own metaphysical baggage, potentials that hide energy accounting, negative wells that function as placeholders, fields with directionality baked in, and probabilistic postulates that I cannot reconcile with the present moment determinism axiom. So RSI is not UEFT with different symbols. RSI is the decision to strip the overlays away, keep only the ledger primitives, and then rebuild the overlays as mappings. That is the key posture shift. Instead of stacking overlay after overlay to approach reality, I strip down to primitives and then I add mappings back in, explicitly, only where measurement requires them. In RSI, the familiar domain constants are not dismissed. They are treated as calibrated mappings between the ledger and the measurement interface, pinned once per regime and reused. They are consequences of the mapping, not mysterious primitives floating above the ledger. How RSI relates to Newton, Einstein, and modern theory. I am not writing this book to dunk on Newton, Maxwell, Einstein, quantum mechanics, quantum field theory, holographic ideas, or string models. I treat those as extraordinarily effective overlays that have captured real structure. My claim is more specific. These frameworks are capturing pieces of the same underlying grammar, but they encode that grammar in different languages and with different hidden bookkeeping choices. Here is the conceptual map I use while reading the legacy canon. Newton and the force picture. Newton gives an operational overlay. Forces produce accelerations. That overlay works extremely well when the system boundaries are clear and the contexts are stable. In RSI posture, Newton's laws are not wrong. They are a reporting layer that emerges once the scalar verdict is known, and I draw directionality indicators, verdict arrows, to represent toward increasing stability as a trajectory tendency. Special relativity and the speed of light. Special relativity teaches a deep truth about measurement constraints and frame comparisons. RSI does not need to deny invariance to become deterministic. Instead, I treat invariance as consequences of the measurement interface and the coupling lattice. Where legacy SNR uses spacetime geometry as the stage, RSI asks what a resolved identity can coherently exchange across edges without violating the ledger. The speed of light then becomes a boundary statement about how influence is reported in the overlay, not a license for paradox. General relativity, curvature, and the background problem. General relativity treats geometry as a manifold and matter as a source that curves it. RSI flips the causal story. Existence generates geometry. An identity instantiates its coupling carrier at its boundary, and the large-scale geometry I infer is an emergent terrain built from overlapping identities in the lattice. So RSI does not require me to imagine a pre-existing curvature field waiting for matter to arrive. Remove the identities, and operationally, the universe becomes effectively flat and indistinguishable from a featureless background, because there is nothing left to instantiate measurable geometry. Black holes and singularities. Black holes are one of the strongest examples of why I reject literal infinities as nominal physical objects. In RSI posture, I prefer to speak in terms of resolved boundaries and last resolved interfaces. A black shell horizon becomes a practical boundary choice, the last interface where external accounting remains resolved under the existence gate. That lets me discuss horizons, redshift, and observational behavior without treating a singularity as a required ontological ingredient. Quantum theory and the measurement problem. Quantum theory gives real numbers, and I respect that. But the measurement problem is still a unanswered question. RSI approaches the issue by refusing to treat the observer as external and refusing to treat probabilities as fundamental. A measurement is an edge, a context change, and an identity resolves relative to that new context. Holographic and string ideas. I treat holographic thinking and string-like models as hints about how much structure can be encoded on interfaces, and how deeply the world may be organized by constrained degrees of freedom. RSI's claim is that the deepest commonality is not a specific string spectrum or a specific duality, it is the repeated emergence of interface-driven bookkeeping. In RSI, that interface bookkeeping is explicit and sits at the boundary where an identity couples. None of these legacy frameworks become useless under RSI. They become readable as overlays whose success is explained by the fact that they are latching onto the same underlying resolution grammar, what RSI offers in the long view. Even if you never touch the formal machinery, RSI is already making a claim about what kind of universe I live in, a universe where systems persist by clearing explicit admission tests, and where change is a separate verdict, not a vague synonym for motion. That posture does not only unify domains, it also changes what questions become operational, because it forces me to declare boundaries, membership, and interfaces instead of hiding them inside story language. I collect a longer, rule-bound speculative expansion in Appendix T, CK. Here I preview the kinds of high-level consequences that fall out once I take the primitive seriously without pretending that every downstream model is already finished. Time, causality, and why a propagation ceiling is expected. If reality is a determined recursion of resolved states, then chronological order is not optional. It is the backbone that makes coherence possible. In that posture, a finite propagation speed is not an arbitrary postulate. It is what a causal network looks like when I measure it with clocks and signals. This is why I treat frame propagation limits, the speed of light in our regime, as an expected consequence of a resolved lattice, not as a magical rule added from outside. Horizons and black holes as last resolved boundaries. In RSI, I do not treat a black hole as a place where physics becomes infinite. I treat it as a place where a particular external accounting context stops being resolved, meaning I have reached the last resolved interface for that chosen boundary. That lets me discuss redshift, shadows, and time dilation effects without requiring a literal singularity as an ontological ingredient. Dark matter and dark energy as boundary and closure questions. RSI gives me a new first question before I invent new substances. Did I declare the right system, the right boundary, and the right partner set for closure? If I did not, then a missing pull signal can be a misaccounted stability distribution, not missing mass. For cosmology, RSI also forces me to say what boundary I'm assuming when I talk about expansion, acceleration, and horizons, instead of smuggling those choices into a single fluid term. What E equal to MC2 becomes when matter is an identity. I treat energy as ledger content and matter as a persistent anchored identity. In that posture, energy turning into matter is not a category swap. It is a reconfiguration where the ledger and the interface conditions support a new stable closure that keeps clearing the existence gate. Mass remains real as an overlay parameter, but it becomes a calibrated mapping between the ledger and the inertial and gravitational measurement interfaces. What wormholes would have to be if they ever become meaningful? If a wormhole ever becomes meaningful in RSI, I do not expect it to be a free geometric tunnel that ignores accounting. I expect it to be a declared corridor interface that creates a new adjacency in the solved network, while still staying admitted, existence stays above threshold, and while not forcing collapse, change stays in a stable band. I do not claim that such a configuration exists in our universe. I'm stating the filter it would have to satisfy. Outer solar system structure without a required Planet 9 lever. RSI adds a mechanism class that is often missing from the conversation, corridor capture, and corridor biased allocation in close approach pockets. That means distant small body clustering can, in principle, be discussed as a system membership and interface question first, not as an automatic requirement to posit an unseen massive planet before I have an admitted mechanism. System cartography as a long-horizon program. One of the most ambitious promises of RSI is that I can map the universe without a particle-by-particle census. Because the primitives are designed to classify persistence and change at declared boundaries, a mature RSI program could map reality as a nested lattice of anchored identities, interfaces, and stability terrains, from atoms to galaxies. This is not a claim that I can do it today. It is a claim that the language makes the task well posed in a way that many legacy framings do not. What I mean by discovery. I use the word discovery carefully. I'm not claiming that I discovered the universe ex nihilo. I'm claiming that I found a consistent posture and a consistent bookkeeping interface that let me stop patching contradictions and start deriving across domains using the same primitive grammar. In this project, I treat the discovery as 3 interlocked moves. The rest of the book is the disciplined expansion of those moves, how to read this book without getting lost. This document is not structured like a standard journal paper. I am not trying to compress the ideas into 4 pages of dense math and hope the reader fills in the gaps. I'm trying to introduce a new physical posture, show the underlying story and motivation, and then show how the formalism behaves when I force it to touch reality. So I wrote it as a guided walk, not as an abstract only drop. Here is how I recommend reading it, depending on who you are. Route 1, Concept First Reader. Start here, then read the Existential Logicism Foundations to understand the logic foundation and the persistent present determinism axiom. Then read the formal RSI statement at the start of Part 1, 1.1. After that, you can skim the equation-driven parts and then jump to Part 14, C14, to see how I turn the system into a workflow. Route 2, Skeptical, Falsifier First Reader. Skip the story, go straight to Part 14, C14. Read the solve card in the falsification posture. Then go to Appendix A, CA, and run what I call the macro adjudication benchmark and its unit coherence check on the derivations you care about. If the bookkeeping fails, you can stop. If the bookkeeping holds, then come back for the conceptual picture. Route 3, Builder, Implementer, or Engineer. Read the solve workflow in Part 14 first. Then read the system statement at the start of Part 1, C1.1. Then use Appendix A, CA as your audit spine. Treat every new application as a case study with a declared boundary, declared interface, explicit ledger, and explicit falsifier. Route 4, Long View Implications Reader. You want the widest conceptual expansion including time travel limits, horizon logic, dark matter reframes, corridor capture, and system cartography. Read Appendix T, CK. I recommend doing that after you have at least skimmed Part 1, so the speculative tier never gets mistaken for a new primitive rule. A practical warning about confusion points. Almost every reader who has never seen RSI will stumble in the same places. They will confuse existence and change, meaning they will treat exist now and will change as the same kind of statement. They will smuggle geometry into the wrong place because they are used to writing distance dependence directly into force expressions. They will think the absence of vectors means the absence of directionality. In RSI, directionality indicators, verdict arrows, are a reporting layer drawn after the scalar verdict. They will treat calibrated constants as tuning knobs. In RSI posture, calibrated constants are pin mappings per regime, reused without retuning. If you keep those 4 failure modes in mind, the rest of the manuscript becomes much easier to read. What I am promising in the introduction and what I am not promising. I am promising the following. A single consistent conceptual picture of reality as present moment resolution of identities in context. A disciplined separation between primitives and overlays, so I can explain why legacy models work without treating them as the deepest layer. A unification posture that does not rely on hidden reservoirs of energy, probabilistic miracles, or geometry smuggled outside the declared interface carrier. A workflow that can be used on sparse data, where system membership is a verdict and not merely a story. I am not promising that every possible cosmology expansion is completed inside this intro. This is an introduction and a primer. The goal is to make the RSI posture clear, audible, and testable, so that expanding the application library becomes a matter of disciplined growth rather than a matter of rewriting foundations. If you take nothing else from this introduction, take this. I am not asking you to believe RSI because it sounds good. I am asking you to read it as a disciplined attempt to replace patchwork with a single resolution grammar, and to judge it by whether it stays coherent and whether it survives falsifiers. The formal statement begins now, at the start of Part 1, C1.1. 1 Part 1, Orientation, Doctrine, and the Non-Negotiables. 1.1 Why I am building this baseline scope and purpose. I am not trying to rewrite every equation in physics. I am trying to rewrite what counts as the primary question. In legacy mechanics and field theory, I often see the standard sequence, write equations of motion, then we integrate trajectories, and then we interpret what the result means. RSI flips that order. I start by declaring the system boundary, defining what counts as an identity, and making the energy ledger explicit. Only after I have a ledger that can close do I allow myself to talk about motion, force, or other reporting overlays. Scope, what this introduction to universal relativity is and is not. This is the book-length introduction, not the full RSI manuscript. I'm building a baseline that a physics-literate reader can hold in their head without drift. I do not assume the reader is already sympathetic to my doctrine. I do assume the reader can read equations and wants a clear operational story, what I refuse to do in this baseline. I will not rely on hidden reservoirs, negative wells, or probabilistic primitives. I will not say, and then the constant is just G without showing what it means in RSI terms. I will not use vectors as primitives, I will not let geometry leak outside the anchor plane carrier. 1.2 The actual contract I am making in this baseline. This baseline is a contract, and I want it to be explicit. So the contract is, I will define what I mean by a system, an anchored identity, and an interface. I will define the core ledger quantities and keep them explicit and positive. I will define the two gates, existence and change, and keep their roles separate. I will confine geometry to the anchor plane carrier AP everywhere, with one audited exception. I will treat legacy physics as an overlay reporting layer. It is not erased, but it is not the primitive grammar. Why I'm not afraid to be strict. I am strict because RSI work drifts when the primitives are not kept explicit. The drift is predictable. If I speak loosely about distance, I will encode geometry into D or T. If I speak loosely about force, I will reintroduce vectors as primitives. If I speak loosely about potential energy, I will accidentally import negative wells or missing reservoirs. I do not want that drift. The rules are not limitations, they are guides that can't be violated if the system is to remain coherent across all four domains. 1.3 The minimal RSI picture I keep in my head, and you should too. If you want the short picture before the details, it goes like this. RSI is a deterministic scalar engine that allows a new posture when assessing observations and well-founded physics frameworks. It is a solver posture that uses an explicit positive energy ledger plus two gates to decide whether a configuration exists now and whether it must change. The two gates are the existence gate S, exists now, and the change gate DC, becoming. Geometry is confined to AP in the existence gate. Multi-anchor partner accounting is done by the allocation closure rule, not by splitting energies by hand. 1.4 The 5 non-negotiables anti-drift rules. These are the rails I do not violate. If you keep only one thing from this part, keep these. Not hide energy, and I do not treat it as negative. 6. Vectors are overlays. Legacy vectors encode directionality and magnitude. As an overlay representation, the solver yields a scalar verdict, stability and imbalance, and then I draw directionality indicators, verdict arrows, as a reporting layer. 7. Calibrated mappings, not tuning knobs. When I invoke a legacy constant, like G, key, or a coupling, I treat it as a calibrated mapping between RSI ledger primitives and the measurement overlay, pinned once per regime and reused. 1.5 RSI in one sentence, and the posture it implies. Reality is an updating present stability network whose persistence and change are deterministically decided by a closed scalar energy ledger and two gates, with all geometry confined to AP. This sentence encodes my posture. I am solving systems, not doing pairwise force laws as primitives. I am making the energy ledger explicit and closed. I am evaluating gates, verdict ratios, not invoking probabilistic evolution as a primitive. I am treating distance behavior as an interface geometry consequence, not as something I am allowed to insert by hand. 1.6 The claims ladder, derived, interpreted, speculative. Because this is a theory introduction, I will say some big things. I will also label them. I use a 3-tier ladder. Tier 1, derived and audited. These are statements I can trace to the core 12 relations plus explicit assumptions and calibrations, and that I treat as the solver stance. Tier 2, interpreted overlays. These are statements where I map RSI outputs to a legacy reporting overlay, GR language, QFT language, etc., and interpret what the overlay is actually describing. Tier 3, speculative extensions. These are statements about what might exist beyond the context I am describing. Tier 3 statements must be labeled as speculation. They are not theorems, and I will not pretend they are. This latter is how I will talk about redshift, black holes, cosmology, and the large-scale universe, in a way that does not smuggle in hidden assumptions. 1.7 Universal Relativity as a posture, not a brand. When I say universal relativity, I am naming a posture. I am not switching the grammar between domains. I am not using one set of primitives for gravity, another for electromagnetism, and another for nuclear interactions. I am using the same ledger and the same gates, and I am changing only the interface carrier and the domain mapping. That is the unifier claim. If I cannot keep the grammar consistent, then I have not built a unifier. I have built a patchwork. 1.8 The core 12 at a glance, what each equation is doing. The core 12 is not a decorative list. It is the minimal set of relations I need to run the solver, keep the ledger explicit, and keep geometry confined. If you only remember 3 discipline moves, remember that RSI keeps coming back to 3 discipline moves. EA. S equal to APDC equal to EFEA. Sigma equal to EF plus EA greater than 0. Everything that follows is bookkeeping around those moves. How EF is built from T and D EQ 2. How partner allocation works EQ 10. And how I translate the scalar verdict into legacy reporting overlays. 1.9 RSI in 12 equations, 1-page map. This is the minimum map I keep in my head. I will expand each piece later, but I do not allow myself to drift away from these roles. I also want to say this plainly. I am not presenting these 12 equations as decorative speculation. They are the core of a working solver stance. The rest of the book is how I use them to decide system membership, stability, collapse, corridor capture, and diagnostic observables across scale without switching the grammar. This is why I call them the core 12. If you are reading this to see whether RSI is operational and not just a vocabulary exercise, I point you to the implementation posture early. In Appendix B2, I lay out the solver first boundary order I actually follow, declare the system, choose the correct interface carrier, build the explicit positive ledger, then evaluate the gates. In Appendix A, I keep the audited math posture that supports the claims I treat as Tier 1, including the EQ 11. Exception Doctrine in Appendix A9. Part 1. Orientation, Doctrine, and the Non-Negotiables. For the compact validation cards and falsification posture that mirror these checks in a quick compute format, see Part 14, SEC. 14. A control panel picture. If you want a practical picture, I treat the Core 12 as a control panel with a few dials and a few gauges. The two gauges you should never confuse are the existence gauge S, EQ, 1, and the change gauge DE, EQ, 5. The main dials are the per layer budget T and layer count DE, which set EF, and the interface geometry carrier AP, which sets how the same ledger dilutes over a shell or concentrates inside a corridor pocket. Here's the concrete inverse square example I keep returning to. For a shell interface, AP R 4x R2C, so if I double the separation R2R at fixed E, the interface area grows by a factor of 4, and S drops by a factor of 4. That is the inverse square story, and I did not have to claim that 7 falls off with distance. How I read Table 1. This is not meant to be a full derivation. It is a one-page picture of how the same ledger variables can validate multiple domains. I try to keep each row anchored to either a real tabletop measurement, gravity redshift, or a standard proxy dataset, nuclear separation, and I use the same structure and symbols each time. Domain scenario, M, DA carrier. Gravity threshold, Earth raw. Surface sanity, E, F, J, 1 AP, R, 4M, 2C, 6X, 107, 6X, 107. Shell, EA, 3, SDZ, 10, 1. Gravity gravitational redshift, 22.51, AP, R, 42C, pound Rebka scale, shell, 2.5x, 10 to 15 EM Coulomb scaling, EQ, 1, 0.501, Malagasy area R, minus 40. Scaling only, fixed charge pair, have from, shell, 2.3 times 10, 14, 23 times 10, 14, 410, row 1 meter to 0.50 meters strong nuclear coupling, EQ, 11, 1 times 1. Exception, 10 to 15 AP is not used explicit outside. 16 times 10 to 13, 1.6x, 10 to 13, 110. Work week decay near threshold, EQ, 12, 7.8x, 10, 11, 7.8x, 10 to 13, 1 plus 1.1x, 10, 3, 1 plus 11 times 10. Table 1, RSI in the lab, representative tabletop validation scenarios, and safe proxies that show the same ledger variables across domains. I treat these as recipe-level magnitude checks, not as final precision fits. Coulomb scaling, note what is being checked here, EQ, 1, plus the spherical carrier APRX2 produces the inverse square scaling automatically for fixed EA, SREA, APRX112, so halving multiplies S by 4. This matches the distance scaling of the legacy Coulomb force law. If you want a concrete RSI sanity check for that factor of 4, pick any fixed charge magnitude, for example. Q equal to 1 UC, F, R equal to key EQ2 R2, so F, 0.50 meters, F, 1 meter, equal to 4. Potential energy scales as 1R and is recovered only after integrating the force overlay. I am not claiming a 1R energy law in this row. EQ, 11, exception explanation, why the strong case is different. I allow one explicit geometric exception, EQ, 11, in that equation only a factor 2 rands appears outside AP. This is the only allowed direct geometry injection outside AP. Gravity and EM use AP as the propagation carrier. That is shell dilution. Strong does not propagate as dilution, it is a contact normalization and confinement interface. For strong, R is a separation handle, not a macroscopic shell radius. The explicit 2 rands in EQ, 11, exist to isolate the exception. If I force strong into AP, I would smuggle shell geometry into the confinement domain unintentionally. 1. Resolution state law, stability at the interface. EQ, 1, S equal to EATP. Operational meaning, also called the existence gate, meaning how much anchor energy per projection area. Geometry lives only in AP. 2. Field energy, EQ, 2, EF equal to TDE. Operational meaning, the recursive field is D layers deep. Each layer carries energy T. EF EA equal to TD. Operational meaning, T is the per layer energy, and at the anchor boundary 1 layer EA equal to T. SE equal to EF plus EA. Operational meaning, no negative wells. Missing from your accounting. If something is missing, it is. 5. Deterministic collapse ratio change gate, EQ, 5. DC equal to EFEA. Operational meaning, how much recursive pressure exists relative to the anchor. 6. Engine channel weighted collapse accumulation, EQ, 6. K equal to XKCH theta DC. CH. Operational meaning, when change is allowed it routes through channels and orientation factors. In RSI I do not use chaotic vector mechanics. I solve for allowable states and deterministic loops. 7. Deterministic closure, engine closure, EQ, 7, DC equal to EFKBT. Operational meaning, the collapse threshold is not random. It is an evaluated ratio under the active channel structure. 8. Identity energy tally, how many anchors are present. EQ, 8, EA equal to D, X, SHU. Operational meaning, the ledger sums multi-anchor systems, and can even do direct cross-domain calculations since it uses the same equations and language across domains. The system's total identity is a recursion count times the sum of anchored units present. This is how I count identity contributions without introducing probability. 9. Redshift diagnostic frame ratio, EQ, 9, S, OBS, Z equal to 1. S, emit, operational meaning, redshift is a stability ratio comparison between frames, not a mysterious energy loss. EI epi lambdage equal to PKE K, operational meaning I do not split energy by hand. I allocate influence via the closure ratio. This is RSI's answer to the 3 or n-body problem. 11. Nuclear coupling equation, strong domain overlay readout, audited exception, EQ, 11, NC equal to EFR2, operational meaning, this is a confinement contact normalization interface readout, not the existence gate. The explicit 2 RANs is isolated and audited, Appendix A9, 12. Weak domain threshold diagnostic, EQ, 12, equal to DC, 1. Operational meaning, weak behavior is near threshold change behavior. I interpret it as the small excess above the change gate, not as a probabilistic decay primitive. 1.10 the core 4, EQS. 1 to 4, existence and ledger closure. The core 4 is the smallest closed container. It tells me what it means for a configuration to exist now, and it forces me to keep the energy ledger explicit and positive. 1.1101 existence as a ratio gate, EQ, 1. The resolution state law is the existence gate, S equal to EAP. I interpret it as a present tense question. Does the anchor energy budget EA meet or exceed the interface demand AP for the configuration I am testing? This is also the most commonplace RSI drift happens. If I allow myself to write a stray R2 outside AP, I can fake an inverse square falloff without actually confining geometry. That is why I treat geometry confinement as a hard doctrine, not as a stylistic preference. 1.110.2 field energy and recursion depth, EQ, 2, field energy defines the recursive field energy partnered to a given anchored identity, EF equal to TD. I treat T as energy per RSU layer, and DE as an integer layer count. If I find myself treating DE as continuous or letting geometry leak into it, I am drifting. 1.10 and 3, anchor energy or tension as per layer identity. EQ, 3, anchor energy pins the anchored identity, EA equal to EF equal to TDE. This is a compact identity, but it carries an operational discipline. If I am at a boundary where D equal to 1, then EA equal to T. I cannot reinterpret T as something other than energy without breaking the ledger. 110.4, the RSI ledger, the closure is explicit and positive. EQ, 4, RSI ledger closure, this equation closes the ledger from galaxies to atoms, without infinities in either direction, SE equal to EF plus EA. This is where I refuse negative wells. If a legacy derivation uses a negative potential energy story, I treat it as a reporting overlay that is compressing a positive ledger into a sign convention. 1.11, the 2 gates, existence now and change next. The RSI solver posture is built around 2 gates. S tells me whether the configuration can exist now under the stated interface carrier. DC tells me whether the configuration must change, collapse, transition, or reconfigure, given the field pressure relative to the anchor. I keep them separate because the most common conceptual failure mode is to treat force as if it is the same question as existence. In RSI, those are different questions. 1.12, what I mean by solving a system. When I say RSI is determined, I mean it in the solver sense. I do not mean I am making a philosophical claim about free will. I mean, if I specify the ledger in the interface carrier, the gates are evaluated deterministically and yield a scalar verdict. A solved system, in RSI terms, is a configuration where the system boundary is declared, the ledger quantities are explicit and closed. The correct interface carrier has been chosen, shell or corridor, the existence gate S is evaluated, the change gate DC is evaluated, and the multi-anchor closure, when present, is applied via EQ 10. That is what I mean by solving a system. I am solving the whole configuration under a closed ledger, not doing pairwise patchwork. 1.13 Geometry Doctrine, where distance dependence is allowed, geometry is not free decoration in RSI, it is confined. 1.13.1, what is allowed to depend on distance? I allow the following to depend on distance. AP, as an interface carrier, shell or corridor. Any overlay reporting quantity that is explicitly labeled as an overlay, fields, forces, curvature, potentials, and only after calibration. I do not allow T to decay with distance. I do not allow D to absorb geometry. I do not allow stray R factors outside AP in the existence gate. 1.13.2, 2 interface regimes, shells and corridors. RSI has 2 geometric situations that show up constantly. Shell regime, influence dilutes over an effectively spherical interface. The carrier is APR, equal to 4 per 2 degrees Celsius. Corridor regime, overlap is constrained and the effective interface is not a full shell. The carrier is an effective corridor pocket AP core. That represents the overlap interface actually in play. The corridor picture matters because it prevents me from adding new invisible masses or phantom anchors when the actual explanation is geometric overlap. 1.14 determinism, probability, and what I mean by no probabilities. When I say RSI has no probabilistic primitives, I am not denying statistics. I am denying the idea that probability is the fundamental update rule of reality. In RSI, probability appears only as a reporting layer. If I do not know the boundary conditions, or I do not track all channels, I can summarize outcomes statistically. That is a statement about my epistemic limitation, not a statement about fundamental indeterminism. 1.15 vectors, arrows, and what I mean by overlays. I need to be careful here because RSI readers and legacy trained readers have different instincts. What RSI does not say. RSI does not say vectors are fake. Vectors are powerful overlay representations, especially when the system is near a regime where directionality is stable and the vector language is a clean summary of scalar gradients. What RSI does say. RSI says vectors are not primitives. The solver does not need vectors to decide whether a system holds or collapses. The solver yields a scalar verdict, stability and imbalance, and I then draw directionality indicators, verdict arrows, as a reporting layer. This is not a downgrade. It is a discipline move, it keeps the primitive grammar consistent, and it prevents me from smuggling new degrees of freedom in the name of vector elegance. 1.16 calibrated constants as mappings, and why they are not arbitrary. I do not dismiss legacy constants. I treat them as calibrated mappings. A legacy constant is a mapping coefficient between the measurement interface and the RSI ledger primitives. It is pinned once per regime and reused. It is not a free tuning knob I get to adjust per example. This posture matters because it turns the constant question into an audit question. Can I calibrate once and then reuse across context without drift? 1.17 doctrine restated. The 5 constraints I do not violate. I restate the 5 constraints here because they show up everywhere. Roles never mix. S is existence now. DC is changed next. Ledger is explicit and positive. SE equal to EF plus EA stays positive. Geometry lives inside AP. I do not add stray R factors outside. Corridors are real interfaces. I do not pretend every interaction is a full shell. Allocation uses EQ. 10. I do not split energies by hand. 1.18 How I keep myself from drifting. A practical checklist. When I write or compute RSI, I run a simple checklist. 1. Did I declare the system boundary? 2. Did I choose the correct interface carrier, shell, or corridor? 3. Did I keep EF, EA, sigma explicit and positive? 4. Did I keep geometry confined to AP except for the audited EQ? 11. Exception 5. Did I keep S and DC role separated? 6. If multi-anchor, did I use EQ? 10. And not split by hand? If I fail any of these, I am drifting. 1.19. A first pass on how RSI treats the big questions. Conceptual only. I will keep this conceptual here. The math and audited posture come later, but I want the reader to have a picture. Redshift. RSI treats redshift as a diagnostic ratio. EQ. 9. A frame comparison of stability gates, not a mysterious energy loss. Black holes. RSI treats black hole language as an interface and ledger closure story under extreme recursion depth, not as a singularity with undefined physics. Big Bang and cosmology. RSI treats cosmology as a ledger closure story and a system lattice evolution story, where any successful narrative must keep the ledger explicit and avoid geometry smuggling. 36. Wave-particle duality. RSI treats the wave and particle languages as overlays describing system membership and interface behavior under different measurement cuts. The primitive is system stability and change, not a dual ontology. If any claim requires hidden negative energy reservoirs or geometry smuggling outside AP, it fails RSI doctrine. Any successful cosmology story must keep the ledger explicit. 1.20 section 1.6, form. The anti-drift doctrine and operational. This section is where I put the doctrine into operational form. What the primitives mean, what the gates mean, and where geometry is allowed to live. 120.1 What the primitive quantities mean in the real world. I keep 3 carriers explicit. EA, anchored energy bound in a resolved identity. EF, recursive field energy budget between anchors. AP, the interface carrier that holds geometry, shell or corridor, and the mapping constant that makes the existence gate dimensionless. 120.2 The 2 gates in 1 sentence each. S tells me whether the configuration can exist now under the stated interface. DC tells me whether the configuration must change under the stated field pressure. 1.20.3 The geometry confinement rule. I enforce one hard rule. All radius and area dependence lives inside AP. For shell dilution domains, gravity and electromagnetism, I do not encode geometry into D or T, and I do not add stray R or R2 factors outside AP. The sole explicit exception to this rule is EQ 11, which carries an audited 2 rands outside AP. For nuclear contact normalization, see Appendix A9. 120.4 Boundary sanity check. Boundary sanity check. At the boundary, 1 layer, EA equal to T. If I drift on units or roles, it shows up here first. Geometry sanity check. If I see a stray R outside AP in a gravity derivation, it is a drift error. Boundary sanity check. EQ 3 makes a simple statement that I use as a drift alarm. At the boundary where D equal to 1, EA equal to EFD equal to T. If I ever find myself writing prose that treats EA as something other than an energy, or treats DE as anything other than a dimensionless count, this boundary check is where the drift will show up first. 120.5 Why the ledger is in joules, and what I mean by mapping. When I call RSI a determined recursive resolution state interface, determined is not a mood, and it is not a rhetorical jab at probability. It is a statement about. When I feed the solver, I feed a closed explicit energy ledger, EF, EA, sigma, plus A, discrete recursion count, DE, and the gates I report, S, DC, are dimensionless verdict ratios. The solver is not allowed to hide units, and it is not allowed to hide missing energy. This is why I use joules in the core ledger. Joules are not a philosophical choice here. A joule is the RSI unit of work, so it is the unit that directly matches what I can measure at the measurement interface: mechanical work, heat, radiated energy, and so on. Once I commit to EF equal to T with the dimensionless, T must carry the same energy units as EF. Once I commit to S equal to EA IP as a dimensionless existence verdict, AP must carry the same units as EA. The ledger is an energy ledger, so I keep it in energy units. Important nuance: AP is not a raw geometric area. In prose, I sometimes describe AP as a projection area because it is the home for shell versus corridor geometry, but AP is a carrier that includes both geometry and the regime mapping constant that makes S dimensionless. In a shell regime, I write AP R equal to 4 per 2 degrees Celsius, and in RSI units that means C carries whatever units are needed so that AP and EA match. In other words, C is part of the overlay to ledger bridge, not a free geometric decoration. 38. What mapping means in RSI. RSI does not erase legacy physics. I treat legacy laws as overlays that already work operationally, and I add a disciplined translation step. I translate the measurements and parameters that appear in an overlay into ledger quantities that RSI can audit. This is exactly where constants live in my posture. A domain constant is not an unexplained primitive that I get to invoke without accounting. It is a calibrated mapping coefficient between the measurement interface and the ledger, pinned once per stated regime and then reused, so I cannot retune it per example. Worked example, new. Converting a legacy Coulomb energy into a ledger calibration handle. Here is a simple numeric conversion that keeps the units honest and shows how the bridge works. Take 2 elementary charges in the legacy Coulomb overlay, separated by R0 equal to 1 nanometer equal to 10 9 meters. The legacy potential energy scale is U0 equal to key E2R0, with key E8.9875517923 by 109 NM2C2 and E equal to 1.60217663 for 1019 degrees Celsius. Numerically, U0 approximately equal to 2.31x 1019J, approximately equal to 1.44 eV. In RSI language, that number is not a new kind of substance. It is simply an energy scale that the measurement interface is telling me the configuration carries. Now I show the AP side of the same bridge without smuggling geometry into D or T. If I choose a clean normalization for this one regime, I can set the shell carrier to match that energy scale at the reference separation. AP R0 U0, which is equivalent to choosing the reference so that S R0 equal to EA EAP R0 equal to 1 when I take EA to represent the reference energy scale in the ledger bookkeeping for that interface. With APR equal to 4 per 2 degrees Celsius, this pins the mapping coefficient to CEM equal to U0 4 per 2, 0, approximately equal to 1.84 x 10 2 JM2. 2 points matter more than the specific number. 2. Once CEM is pinned for this stated regime, the shell geometry immediately yields the inverse square interface dilution behavior because APR R2. The legacy field strength or force overlay inherits that 1R2 scaling as a reporting layer. The legacy potential energy scaling is different 1R because it is an integrated work statement, not an interface density statement. RSI keeps those roles separated. S is an interface verdict ratio, while ledger energy differences are cumulative bookkeeping. 1.2.6 geometry confinement, shells versus corridors. RSI has 2 geometric situations that show up constantly. Shell regime, influence dilutes over an effectively spherical interface. Corridor regime, overlap is constrained and the effective interface is not a full shell. I keep both in the same grammar by keeping geometry inside AP. The ledger stays scalar. The interface carrier changes. 120.7, a concrete corridor intuition, capture without adding a new planet. If you want one practical corridor picture, think of a capture channel where overlap creates a restricted interface region. In a shell-only picture, I might be tempted to add a new invisible mass or a new hidden anchor to explain the observed stability. In RSI, the first thing I check is whether I have accidentally used the wrong interface carrier. If the interface is corridor-like, I use a corridor AP core, and I see whether the same ledger closes. 1.2.8. The key anti-drift sentence. This is the sentence I keep writing in the margins of my own drafts. All distance dependence lives inside AP, except for the audited EQ. 11, strong exception. If I see distance hiding elsewhere, I am drifting. 1.21 What I mean by solving a system in RSI. When I say RSI is determined, I do not mean I dislike probabilities. I mean something stricter. Given a declared system boundary and a declared geometry interface, the core 12 produce a scalar verdict for stability and change, and that verdict determines what belongs to what membership before I draw any legacy directionality indicators. A solved system in RSI has 3 properties. 1. The system boundary is declared. I name the anchored identities I am allowing to participate, and I say what counts as inside the ledger for the solve. Shell interfaces, corridor interfaces, and the relevant anchor planes. 2. The geometry carrier is declared and kept disciplined. All radius and area dependence lives inside the projection area operator AP for shell dilution domains, gravity, and electromagnetism. I do not smuggle geometry into D or T, and I do not add stray R or R2 factors outside AP. The sole explicit exception to this rule is EQ 11, which carries an audited 2 rands outside AP for nuclear contact normalization. See Appendix A 9. 3. The verdict is computed as a ledger outcome. I build EF equal to TDE, EA equal to EFD, and SE equal to EF plusia. I evaluate the existence gate S equal to EA AP now, and I evaluate the change gate DC becoming If the gates pass, the system holds. If DC reaches threshold, the system is forced into an engine outcome and membership can reallocate. This is also why I insist on multi-body solving instead of pairwise solving. In legacy practice, it is easy to treat systems as sums of pairwise influences, and then patch the failures with approximations or probabilities. In RSI, membership and allocation are explicit readouts. If multiple anchored identities contribute, I use EQ 10 as the allocation law. I do not split EF by hand, and I do not guess a partner's share by intuition, a micro picture. If I want a concrete mental model, a stable three-body structure, for example, a primary anchor with two persistent companions, is not stable because the pairwise forces balance. It is stable because the whole ledger stays above the existence gate and below the change gate under the declared interface geometry. If a fourth identity approaches and pushes DC across threshold for one corridor or shell interface, the system does not become probabilistic. It deterministically admits a reallocation outcome, something captures, something ejects, or the structure reconfigures, and I can name that as a forced ledger result, where the full procedure lives. Later, Part 6 and Part 14, I give the full solve loop as an auditable checklist, declare, choose geometry, build ledger, compute gates, allocate partners, and report outcomes. Here, I am putting the concept up front, so the Core 12 read like a working instrument panel, not a vocabulary list. 1.22a Concepts Only Preview Legacy Questions. How RSI reads the big. This book begins with simple domains and controlled examples, but I do not want the reader to carry the wrong picture of what RSI is for. So I will name the big questions early and state the RSI posture in plain terms. I will keep the math elsewhere, and I will label what is solved versus what is inferred. Redshift. In RSI, redshift is a resolution diagnostic. It is read as a cumulative mismatch in resolution state across the path, not as a required expanding metric. The observable is tied to changes in S along the propagation context, and it must stay compatible with lensing and time dilation diagnostics in the same ledger language. Gravitational lensing and time dilation. I treat these as scalar ledger outcomes of gradients in the declared interface geometry and anchor distribution. The reporting layer may use legacy directionality indicators, but the solver itself is scalar first. Black holes. RSI does not require a singularity. A black shell horizon is a last externally resolved shell defined by the existence gate threshold evaluation. The interior is not treated as a magical negative well or a hidden reservoir. It is a deterministic but externally isolated recursion regime. Big Bang and early universe. RSI treats the Big Bang story as an anchor nucleation event triggered by a corridor to anchor transition, not as a breakdown of physics. The early universe scaffold is stated in RSI primitives, pre-anchored background, corridor emergence, anchor nucleation, rapid layer propagation, and then system formation as local closure at all scales. Cosmic expansion and missing narratives. I treat large-scale expansion narratives as overlay readouts of stability terrain evolution. If a claim requires hidden negative energy reservoirs or geometry smuggling outside AP, it fails RSI doctrine. Any successful cosmology story must keep the ledger explicit and positive and must survive cross-checks between redshift, dilation, and lensing, probabilities, and quantum posture. RSI does not deny measurement uncertainty. What I deny is probability as a fundamental causal primitive. When data are sparse, I may report uncertainty bands, but the core engine gates and allocation rules remain deterministic. In other words, probability is an overlay of ignorance, not the solver itself. Infinity and singularities. RSI is built to avoid them by construction. Existence has a gate, and resolved interaction has practical bounds. Where legacy theories drift into infinities, RSI forces me to state which interface is resolved and which is not. Wave-particle duality. RSI treats the primary object as an anchored identity inside a declared system. What looks like wave behavior is often corridor-mediated influence and reporting layer directionality, and what looks like particle behavior is a stable admitted anchor in the ledger. The unifier is system membership and deterministic admission, not a dual ontology. Why structures look web-like instead of random. RSI predicts corridor network topology as a natural outcome of corridor-mediated closure across scales. I treat this as a mechanism for filamentary structure in the large, and I label any finer claims as inference until I combine them to data with an audited solve. I include this preview only to lock the reader's mental model early. When I make a Tier 2 interpretation or a Tier 3 speculation, I will label it explicitly. The solver itself remains Tier 1, 1.23, where the rest of the book goes from here. Part 1 is doctrine and orientation. The rest of the book does 4 things. I build the core 4, existence and ledger closure. In operational detail, I build a deterministic collapse and engine posture, EQS, 5 to 7. I build the multi-anchor and redshift posture, EQS, 8 to 10. I build the 4-domain overlay readouts, gravity, EM, strong, weak, while keeping the grammar fixed. If you want to audit, I point you to Appendix A early. If you want to see the solver posture in a procedural form, I point you to Appendix B. 2. If you want quick validation recipes, I point you to Part 14 SEC. 14. Part 2, the primitives as real-world carriers. In Part 1, I drew the hard boundary around RSI. I said what I refuse to compromise on, because those refusals are what make RSI a solver and not a metaphor. Now I am going to do the thing that makes the rest of the document possible. I am going to make the symbols feel physical, and I am going to do it without letting any one symbol secretly do two jobs at once. When I say the primitive set is made of carriers, I mean something very specific. A carrier is not a philosophical placeholder. A carrier is the minimal object I allow myself to touch when I translate between abstract bookkeeping and the measurable world. If I keep the carriers clean, then RSI does not drift when I move from cosmology to orbital mechanics to particle phenomenology. Two drift traps show up immediately, and I'm going to name them here so I can catch them later. First, I cannot let d become a disguised distance coordinate, and I cannot let t become a distance decaying field strength. In RSI, t is energy per RSU layer j, and any distance-like dilution is carried by AP. Second, I cannot treat legacy domain constants as additional primitives. In RSI, those constants are calibrated mapping coefficients, pinned on a reference boundary and then reused across a stated regime while the ledger structure stays fixed. There are only three carriers in the base system. Energy, in the anchor, EA, the anchored budget that is available at the interface as exists now. Energy in the field, EF, the recursive budget distributed across layers as. What can become change? Geometry in the interface, AP, the anchor plane that is allowed to carry all explicit dilution and area scaling. Everything else in the core 12 is built from these three carriers by ratio, counting, or closure. The point of this part is to lock the semantics so tightly that when I later say gravity drops off or an orbit is stable, I never accidentally smuggle geometry into T or distance into DE. 2.1 The three carriers, EA, EF, and AP. The most common way RSI drifts is that I start speaking like a legacy field theorist and I let a single symbol do two jobs at once. RSI does not let me do that. Each carrier has a single job, a single unit role, and a single failure mode. Carrier 1, EA, anchor energy. I use EA to denote the anchored budget of a system at the boundary that matters for existence. In practice, this is the quantity that sits in EQ 1 as the numerator of the existence gate, S equal to EAP, and it is the quantity that I will later allocate across partners in multi-anchor closure, EQ 10. Conceptually, I treat EA like this. EA is what the system has on hand at the interface. It is the anchored budget that can underwrite a stable configuration now. EA is not a force, and it is not a potential well. It is a positive energy ledger entry. EA is not allowed to silently inherit geometry. If I find myself saying EA falls with distance, that is a category error. In RSI, distance and dilution are the job of AP, not the job of EA. In the core 12 identity relations, EA ties directly to the per-layer tension T via EQ. 3. This is the first place people tend to get confused, so I will say it plainly. Within RSI, EA is not a knob I tune as a function of radius. If something looks like it weakens with radius, I will handle that through AP, not by weakening EA. Carrier 2, EF, field energy. I use EF for the recursive layer-spanning budget in the field. This is the energy ledger entry that counts how much recursive work is present across D layers, as written in EQ. 2. EF equal to TD. Conceptually, I interpret EF like this. EF is the energy budget that exists in the recursive span. It is the becoming budget, not the already exists budget. EF is still positive. It is not a negative potential reservoir, and it is not a trig sign convention. EF is not geometry. It does not contain R, R2, solid angle factors, or anything that would be better represented by AP. In later parts, EF is the thing that shows up whenever I talk about collapse thresholds, decay, or structural change, because it is the thing that feeds the change gate DC, EQ, 5. Carrier 3, AP, anchor plane. I use AP as the one and only geometry carrier. This is not negotiable. If RSI has a single anti-drift rule, it is this. In RSI, explicit distance and area scaling live in AP, and nowhere else. I say this because the easiest way to drift is almost invisible on the page. I write something like T, R, or I hide a 1R2 decline inside a chosen DR, and then I tell myself I derived an inverse square effect. In RSI, I do not allow that move. If the story is separation like dilution, the dilution must be carried by AP. The one explicit exception I allow is the strong domain form with an explicit 2 rands outside AP, EQ, 11, and I label it as an exception precisely so it cannot leak into the rest of the book. The anchor plane is an interface object. It represents how much geometry the anchored budget must cover. In the simplest spherical shell regime, the standard helper relation is EQ. S4 AP of R, APR equal to 4 pi R2 degrees Celsius, but I want to be careful about how I speak about this. AP is not just area. The calibrated constant C is doing conversion work so that AP can function as the denominator of an energy ratio in EQ. 1. In other words, AP is the geometry carrier expressed in the ledger units that make the existence gate meaningful. Conceptually, I interpret AP like this. AP is the interface surface that distributes an anchored budget into a resolution state. AP is where inverse square overlays come from when the geometry is shell-like, because shell-like AP grows like R2. Is where corridor and overlap corrections live when the geometry is not a full shell, because the interface is not sampling a full solid angle. If you only remember one sentence from this entire part, remember this. When I say something weakens with separation, I mean the interface AP got larger or the effective coupling geometry changed, not that the per-layer tension T decayed. 2.2% the energy ledger, nothing hidden, nothing negative. Once the carriers are clear, the next thing I have to lock down is the energy ledger. RSI uses a strict positive ledger, and that is not a rhetorical flourish. It is a design constraint that forces me to keep track of what I'm doing instead of hiding sign conventions inside a potential. The ledger closure relation is EQ. 4. SE equal to EF plus EA. I interpret this as a statement of explicit accounting. EA is the anchored budget at the interface. EF is the recursive budget in the field span. SE is the total recursive energy ledger for that identity, or for that composite system, and it is expressed as the sum of two positive terms. This is where I diverge from how many legacy treatments are spoken, even when the underlying physics is consistent. In a lot of legacy mechanics, potential energy is defined relative to a reference and can be negative. That is not wrong as a coordinate choice, but it is easy to misuse, and it is easy to let it blur what is being conserved and what is being compared. In RSI, I do not allow that blur. I do not permit negative wells to do conceptual work. If I want to talk about binding, trapping, or stability, I do it by partition and ratio. Partition between EA and EF tells me how the ledger is distributed between present stability and available change. Ratios like S and DC tell me whether the configuration exists now and whether it is forced to change. Geometry selection through AP tells me whether I am distributing that budget over a shell, a corridor, or an overlap pocket. A practical consequence of this is that I always have an audit step available. Anytime I build an RSI description of a system, I can ask, did I keep SE explicit, positive, and closed under the assumptions I am making? If I cannot answer yes, then I did not build a ledger, I built a story. 2.3 The two gates, S for exists now and DC for will change. RSI is not a catalog of forces, it is a decision system. The decision system is built out of two ratios that I treat as gates. Gate 1, the existence gate S. The existence gate is EQ. 1, S equal to EA.AP. This ratio answers a very specific question. Given an anchored budget EA and given an interface requirement AP, does the configuration have enough anchored budget per interface to count as holding? I use threshold language because RSI is built to be solver-like. In the RSI baseline doctrine, a clean way to speak is, if S greater than or equal to 1, the configuration is admitted as existing in the sense that the anchored budget is sufficient for the interface it must cover. If less than 1, the configuration is not admitted as holding in that form. Something must reconfigure, because the interface requirement outstrips the anchored budget. I am intentionally keeping this conceptual because later parts will discuss how the threshold is used in different domains and how C calibrates overlays. For now, the point is the role. S is a present tense diagnostic. It is my exist now gate. Gate 2, the change gate DC. The change gate is EQ. 5, DC equal to EF.EA. This ratio answers a different question. Given the present anchored budget EA, how much recursive budget EF is present in the span, meaning how much capacity there is for structural change relative to the anchor. In the simplest reading, DC is a collapse ratio. RSI already includes a local stub for the threshold condition. See the Section 8 helper stubs, for example EQ, S8 DC threshold. Conceptually, DC less than 1 reads as stable in the change sense. There is not enough field budget relative to the anchor to force a collapse event. DC equal to 1 reads as threshold. The ledger is balanced at the edge of an event. DC greater than 1 reads as collapse in the change sense. A reconfiguration is forced. I will later refine this with the engine regulation, EQ, 7, because in practice, DC is not a naked ratio floating in the void. It is tied into K and BT through closure. But the role is already fixed here. DC is my will change gate. It is not the same thing as S, why I insist on 2 gates. Legacy intuition often wants a single scalar that does everything. RSI refuses that, because existence and change are not the same question. A configuration can be admitted as existing, high S, and still be forced to change, high DC. A configuration can fail the existence gate, low S, even if it is not in a collapse regime, low DC, because it can simply be geometrically mismatched, meaning the interface requirement is too large for the anchored budget, even before I talk about dynamic instability. This is exactly why RSI is useful for system allocation problems. If I'm trying to decide whether an object is truly a member of a system or a transient passer, I'm not only asking about trajectories. I'm asking whether the configuration is admitted by the existence gate evaluated on the correct geometry carrier AP. A flyby can have dynamics, but it fails the existence gate in the sense that it is not underwritten by the system's anchored interface. Anti-drift checklist, the roles never swap. This is the checklist I run on myself whenever I write RSI papers. 1. If I am describing what exists now, I talk in S language and I point to EQ. 1. 2. If I am describing what will change, collapse, decay, or reconfigure, I talk in DC language and I point to EQ. 5. And, when needed, EQ. 7. 3. If I'm describing distance like weakening, I do not weaken T, and I do not reinterpret D as a metric. I change AP, because geometry lives there. Statement in ledger language using SE equal to EF plus EA, EQ. 4. If I follow those 5 steps, RSI stays coherent when I later move into gravity, electromagnetism, strong behavior, and weak behavior. 2.4 RSUs, what D counts and what T is. This is the place where I have to be extremely explicit, because the most natural legacy misread is to assume D is distance and T is field strength. RSI forbids both, what an RSU layer is. In RSI, I treat the linkage between anchors and their environment as layered. A layer is a resolution state unit RSU in the sense that it is one discrete step in the recursive interface. You can think of it like a recursion depth counter, but I am not using that as metaphor. I am using it as a bookkeeping primitive that forces discreteness when I build the field energy EF. This is why the doctrine statement in the equation stubs is so blunt. D is an integer layer count, and T is energy per RSU layer. what D means. D is defined as a layer count. It is dimensionless, and I treat it as integer by doctrine. The boundary condition is also explicit in the stubs. At the anchor boundary, D equal to 1 CEQ S6D at boundary. I want to say what D is not. D is not a radial coordinate. D is not a continuous metric distance. D is not a place to hide a 1R2 decay. Here's the internal check I use to catch myself. If I can produce a far-field 1R2 decline by picking a clever counting rule day, R, while keeping AP fixed, then I have already violated geometry confinement. They can correlate with separation in a given regime, because deeper recursion spans can show up when anchors are farther apart, but correlation is not permission. D enters the ledger through EF equal to TD EQ 2, and the gates that depend on EF, for example DC EQ 5, it does not carry the dilution that a shell interface produces. In many practical regimes, larger separations correlate with larger layer spans, so it is tempting to talk as if D is distance. I do not allow that temptation to leak into the formalism. The geometric scaling still lives in AP. What T means. T is the energy per RSU layer. It is a ledger primitive. It is the per layer budget that generates EF when multiplied by DE, EQ, 2, and it also ties to the anchor energy via EQ. 3. The simplest way to lock the meaning is to state the anti-drift sentence directly, because I will repeat it in every domain. In RSI, T does not decay with distance. Apparent distance drop-off is geometry in AP, and partner allocation in multi-anchor closure, not a weakening of T. This is not a minor stylistic choice. It is the mechanism by which RSI can reproduce inverse square overlays without adding new postulates. A worked micro-example, why inverse square overlays appear without weakening T. Here's the cleanest version of the intuition. Assume I am in a regime where the appropriate geometry carrier is a spherical shell, so AP grows like R2, EQ, S4 AP of R. Now consider two shells at radii R1 and R2 around the same anchored identity with the same anchored budget EA. I do not say the tension weakened. Instead, I evaluate the existence gate on two different interface requirements. EA S RON equal to R1, AP EA's R2 equal to AP R2. Now take a concrete comparison that everyone already knows in legacy form, doubling the radius. If R2 equal to 2R1 and the geometry is truly shell-like, then the anchor plane scales by the square, meaning AP R2 equal to 4 AP R1. Therefore, S R2 equal to EA 4 AP R1, 1 equal to S R1 4. That is the entire inverse square story in RSI language. The ratio fell by a factor of 4 because the interface got 4 times larger, not because the per layer energy budget T decayed. When I later translate to legacy overlays, that ratio behavior reads like a field weakens as 1 R2 or a force falls off as 1 R2. In RSI, I keep it as an interface statement. The same anchored budget distributed over a larger interface yields a smaller stability ratio, where RSUs enter that picture. Notice what I did not do. I did not need to assign a numerical value to DE for that micro example. That is not an accident. It is a feature. RSUs enter when I ask questions about change, collapse, and recursion depth, because DE is the multiplier that builds EF from T, EQ, 2, and because DC is the ratio that turns EF into a change verdict, EQ 5, RSUs do not enter as a replacement for distance. In other words, RSI lets me keep two ideas clean. Separation like dilution lives in AP, layer spanning recursion lives in DE and EF. When I later build solvers for orbital stability, decay channels, or multi-anchor coupling, I will have to define how DE is counted operationally for a given regime. For now, the conceptual lock is the important part. RSUs are recursion layers, not meters. 2.5 calibrated constants, mapping coefficients, not moving. Targets. If you want the posture in one sentence, before I expand it, calibrated constants in this book are not moving targets and not free tuning knobs. They are mapping coefficients that fall out when I match the RSI ledger to a legacy overlay at a declared boundary, and then I reuse the same coefficient across the regime. Notice that I already used this idea implicitly in the shell helper relation AP, R, equal to 4 per 2 degrees Celsius, EQ, S4 AP of R. The symbol C is not doing new physics, it is doing unit consistent mapping between a geometric interface and an energy ledger ratio. This subsection exists because the language around constants is one of the easiest ways to accidentally overclaim. I'm going to be careful and explicit. In RSI, I do not treat the familiar domain constants as sacred primitives. I treat them as calibrated mapping coefficients between the RSI primitives and ledger variables, EA, EF, T, D, AP, S, DC, and the legacy overlay language we use to report results, Newtonian G, Coulomb constants, effective couplings, curvature parameters, and so on. That is what I mean by calibrated constants. It is not a claim that the SI defining constants vary physically. It is not a claim that measurement standards are unstable. It is a claim about what those constants are doing conceptually inside an overlay. They compress context, geometry conventions, and unit conversions into a single number, which is exactly what an overlay is supposed to do. What I mean by calibrated. When I call a constant calibrated in this book, I mean this is the discipline that turns RSI into something testable. It gives me a clean separation between what the ledger says and how I report it in legacy language. What I do not mean by calibrated, I do not mean that SI defining constants change with location or time, that I can arbitrarily tune constants to make any result fit. The constants are only psychological conventions. A constant can be a definitional anchor in a measurement system and still be, in an overlay equation, a bundle of assumptions about how we are mapping the deeper structure into our chosen language. A mainstream analogy that keeps me honest. Even in legacy physics, we already live with the idea that some parameters are regime-dependent. Effective theories use fitted parameters. Material constants depend on state, and quantum field theory couplings can be scale-dependent. I am not importing renormalization group math into RSI here. I am pointing out a simple lesson. Constant in an equation often means stable inside the regime, where this description is valid. RSI formalizes that lesson by demanding a boundary in a geometry carrier and by making the mapping coefficient explicit. 2.5.1 concrete example, Earth calibration in RSI gravity language. I want one concrete example, because this is where the model stops sounding like philosophy and starts sounding like computation. In the gravity overlay, the intro package already pins a reference condition, Earth, and derives a mapping coefficient. The stubs encode this in a compact way. I impose the surface normalization surf equal to 1 at R equal to REQ, S4 stress Earth. I use the boundary identity condition day equal to 1 at the anchor, which implies EA equal to T EQ, S60 at boundary, and EQ, S6 EA equals T. I use the spherical interface mapping AP, R, equal to 4PR2 C, EQ, S4 AP of R. Those three steps immediately give a clean ledger statement at the reference interface. Surf equal to 1 EA, equal to AP, RT equal to 4 per 2 C, which is exactly the content of EQ, S4 T Earth. Now, if I want to express the same reference pin in the familiar Newtonian overlay language the package uses, T equal to GMR, which is EQ, S4T legacy. Equating these two expressions at the reference boundary yields, C equal to GM, 4PR3, which is EQ, S4 degrees Celsius Earth. This is the pattern I mean by calibrated constant. C is not a new metaphysical constant I invented. It is a mapping coefficient that converts the geometric interface into ledger units so that the existence gate ratio has the right operational meaning. Once pinned, the same C can be reused to compute APR for the same regime, which means RSI makes a direct structural statement and the 1R2 falloff appears as a geometric dilution inside AP. Why this matters for unification? This is the template I reuse in every domain overlay. RSI does not start by adding a new constant for each effect. RSI starts by declaring boundary and geometry, then closes the ledger. Legacy constants appear as mapping coefficients when I translate the same ledger into legacy reporting language. So when I later say the constants are calibrated, I am not saying physics is arbitrary. I am saying the mapping from the ledger to our reporting overlays is explicit, regime stated, and testable. 2.6. A cross-scale snapshot, the same carriers everywhere. Part 2 is not the place for a full application gallery, but I do want to give a single snapshot that keeps the universe picture in frame. When I move across scales, the primitives do not change. What changes is the boundary choice, the geometry carrier, and the partner allocation posture. Atoms, the boundary is a nuclear and electronic interface regime. EA is the anchor budget that admits a stable identity, and strong and electromagnetic overlays are ways of reporting what the ledger permits at those interfaces. Apples and people, the boundary is a macroscopic surface, and the context is Earth. The apparent downward force is a legacy arrow drawn after I compute a stability gradient membership under the Earth's anchored interface. Planets, the boundary is the system lattice of coupled bodies. Membership is not merely proximity, it is stable closure under the gates and under multi-anchor allocation. Black holes, the boundary is the last resolved interface for a given context, meaning a horizon in the RSI sense, the place where the ledger no longer admits a stable resolved interface for the observer context. Cosmology, the boundary is the observable context itself. Redshift is reported as a fractional structural shift in SEQ 9, not as an independent substance called expansion. When I draw arrows in those overlay descriptions, I am drawing reporting layer directionality indicators, verdict arrows, not introducing new primitives. The solver output is still scalar and ledger-based. It is S and DC verdicts together with geometry choice and allocation, and the arrow is just a way to summarize a stability gradient or imbalance after I've already done the accounting. I will make each of these concrete later. Here I just want the reader to see the promise. The same three carriers, the same two gates, and the same calibration discipline apply everywhere. 2.7 Compact symbol table. This table is the conceptual anchor for the rest of the document. If I keep these meanings stable, RSI stops drifting when I move into examples. Symbol role S carrier, EA, carrier, EF, AP, carrier, sigma ledger, counting, D, primitive, T, change gate, DC engine, K scale, BT, gate, theta, allocation, Q, identity, U, observable, Z, calibration, C, strong only, R, meaning and how I read it, existence, gate, resolution, state ratio, S, equal to EA, AP, EQ, 1, does it hold now given the interface? Anchor energy, J, anchored budget at the interface, numerator of the existence gate, field energy, J, recursive budget across layers, EF equal to TDE, EQ, 2, anchor plane, geometry carrier, the only place explicit dilution and area scaling live. Total recursive energy, SE equal to EF plus EA, EQ, 4, positive and explicit. Integer layer count, RSU span, not geometric distance, boundary condition day equal to 1 at the anchor, EQ, S6D at boundary, energy per RSU layer, J, does not decay with radius. Collapse or change ratio, DC equal to EF, EA, EQ, 5, is change forced? Recursive engine aggregation EQ 6, used to regulate closure. Boundary scale used with K to regulate DC EQ 7. Scalar orientation, or coherence gate, used in engine and multi-anchor closure. Partner contribution quantity in multi-anchor closure, EQ 10. Unique system identity count used in the counting law, EQ 8. Recursive redshift or shift measure, Z equal to SS, EQ 9. Calibrated mapping coefficient that converts geometry to ledger units in AP. See, for example, EQ. S 4 degrees Celsius Earth. Radius scale used explicitly only in the strong domain exception, EQ 11, 2.8. Next we cover geometry. Part 2 did one job. It made the primitives concrete, and it locked the carrier roll so I cannot accidentally drift when I start doing real physics. In Part 3 I will take the next step that makes RSI operational in the everyday sense. I will formalize the geometry doctrine, shells, corridors, overlap pockets, and why inverse square overlays appear without weakening T. That is where the tension is constant, but spreads thinner intuition becomes a clean statement. It is not T thinning. It is S decreasing because AP increased, or because I chose the wrong effective interface geometry for the interaction region. I will also keep developing the universal relativity stance. At the practical level, the solver does not require privileged coordinates or privileged arrows. Those appear later as reporting overlays, and they must remain consistent across contexts if the ledger picture is right. Part 3, Geometry Doctrine, Shells, Corridors, and Why Inverse Square Appears. I ended Part 2 with a sentence I treat as a non-negotiable diagnostic rule. If an interaction looks weaker with separation, I do not let that drift into T is thinning or T is decaying. In RSI, T is energy per RSU layer. The lawful place where separation and dilution appear is the interface geometry AP, evaluated through S equal to EAAP EQ 1. This part is where I formalize the geometry doctrine in a way I can reuse later for gravity overlays, Coulomb overlays, lensing, orbital membership, and any other place legacy language tries to drag me back into distance decay habits. The simplest way to say what I'm doing is this. In RSI, geometry is not a background stage. Geometry is an explicit accounting object. If I choose the wrong geometry carrier, I will misclassify stability, misclassify membership, and then I will be tempted to invent new physics. Most of the time, the right move is not to invent anything. The right move is to fix the interface. Throughout this part, when I say identity, I mean an anchored identity, a resolved entity with an anchor boundary and an anchored budget EA. Later, when I switch into the system lattice picture, part 4, I will sometimes describe an anchored identity as an identity node in a graph sense. A node that represents an anchored identity, but I keep the full noun here so geometry talk does not drift into graph talk. 3.1 What is and is not allowed to depend on separation. When I say RSI confines geometry to the anchor plane, I mean something strict. The only object that is allowed to carry explicit separation and area scaling is AP. D is never allowed to silently become distance. It is a discrete layer count. The moment I treat it as a continuous radius proxy, I've smuggled geometry into a budget variable. T is never allowed to silently become field strength that decays with distance. It is energy per RSU layer J, and it is treated as constant per layer at the anchor boundary by doctrine, C EQ S6D at boundary, and EQ S6EA equals T. This single design decision does two things at once. First, it prevents double counting. In legacy physics, it is easy to bake separation into multiple places. I can write a field that already encodes 1R2, then I can also divide by an area later, then I can also normalize by a radius in yet another step. RSI prevents that by forcing me to name the geometry carrier explicitly as AP, and then forbidding geometry from reappearing inside T or D. Second, it is the clean way to recover inverse square behavior as an overlay without adding a postulate that says the law is 1R2. In RSI, the 1R2 story is not a fundamental force law. It is a geometry dilution consequence of evaluating S equal to EA, AP, on interfaces where AP grows like a square. There is a subtle point here that matters later. I'm not claiming that nothing in nature changes with separation. I'm claiming RSI has a specific place where separation dependence is allowed to live. In RSI, separation dependence enters through one of these lawful mechanisms. I evaluate the same anchored budget EA on a different interface AP because the interface radius changed shell regime. I'm not in a full shell regime, so the correct interface is an effective corridor interface that samples a restricted solid angle corridor regime. I am in a multi-anchor environment, and the partner allocation, EQ 10, changes the effective anchored budget that belongs to the anchored identity I am evaluating at this location without splitting EF by hand. None of those mechanisms require me to claim that T decays with separation. 3.2 Shell geometry, the default carrier in the inverse square overlay. The simplest geometry regime is a spherically symmetric shell. In that regime, the anchor plane is the spherical form, EQ, S4 AP of R, APR equal to 4pi R2 degrees Celsius. I'm stating this for role clarity. AP is the geometry carrier. In this regime, the existence gate, EQ1, reads in plain words as, I take an anchored budget EA and I ask how much existence that budget supports per unit anchor plane. If I hold EA fixed, or approximately fixed over the timescale I care about, then evaluating S equal to EAP on larger shells produces smaller S values, because the same anchored budget is being distributed across a larger interface. This is where the inverse square overlay comes from in RSI. In legacy language, one might say, the field weakens as 1, R2. In RSI language, the correct statement is, the The stability ratio evaluated on shells is smaller at larger radii because APR grows like R2 and S equal to EAAP is an energy per interface ratio. This is not limited to gravity. This is a cross-domain geometry fact. A lamp looks dimmer with distance because the same power spreads over a larger surface. A flux density drops with distance because the same flow crosses larger shells. RSI folds that family of intuitions into one disciplined rule. If something is behaving like budget per interface, it is a candidate to be read through EAAP. A one-line sanity check. The check I keep in mind is the same one everyone knows, but I keep it RSI clean. If I double the characteristic shell radius in a spherical regime, then the anchor plane increases by a factor of 4, meaning AP2R equal to 4 APR. Therefore, for the same anchored budget EA, S2R equal to EAAP, 2R E equal to 4 APR, 1 second R4. Nothing in that argument required T to decay. The overlay that looks like inverse square weakening appears because the interface grew, not because the per layer budget changed. Legacy overlay comparison. Legacy physics often motivates inverse square behavior using symmetry and conservation. If a source radiates isotropically, then the same amount crosses larger spheres, so the density per unit area decreases with sphere area. RSI is doing the same structural move with different primitives. Legacy, constant flux through spheres implies field magnitude scales like 1R2. RSI, anchored budget EA evaluated on APR, implies S equal to EAP, PR decreases as APR grows. The point is not that RSI rederives Maxwell or Newton line by line inside this baseline part. The point is that the reason inverse square overlays show up so often is geometry dilution. RSI makes geometry dilution explicit and then confines it to one object so I do not lose track of where I put it. 3.3 corridor geometry, when shells are the wrong carrier. The spherical shell is not always the right geometry carrier. Many real interactions are not mediated over a full 4pi solid angle around an anchored identity. They are mediated through a corridor or overlap pocket, a restricted region of linkage where two anchored identities actually couple. The visual I keep in mind is simple. In a 2D sketch, two expanding rings overlap in a limited arc region. In 3D, that overlap becomes a corridor, a restricted solid angle pocket where the shells intersect and where coupling is operational. If the operational coupling region is not a full sphere, then using the full shell form, EQ, S4 AP of R, is not a physics discovery. It is a geometry selection error. To represent this cleanly inside RSI, I define an effective anchor plane for the corridor. I do not add new separation factors to T. I do not let D become a distance. I simply choose the correct interface. I parameterize the corridor by an effective solid angle OMF with OMF less than 4pi. Then I define the effective interface as a fraction of the spherical interface, AP core R OMF for pi APR. This definition is RSI clean because it keeps the full geometric dilution inside AP, and the corridor only restricts how much of that interface is actually participating. Now the existence gate evaluated on the corridor interface becomes score R equal to EAAP core R equal to 4pi EOEF AP R equal to 4 POMF SSPHR. This is the corridor amplification rule, in one line. For the same anchored budget EA, a smaller effective interface yields a larger stability ratio. I want to highlight why this matters. If I incorrectly smear a corridor coupling across a full shell, I will understate S and I will call something less stable than it actually is. Then I will be tempted to invent new physics to explain the mismatch. The right move is to fix the interface, a practical analogy that stays RSI clean. This corridor versus shell distinction is not restricted to astronomy. A bare bulb emits roughly into 4 steradians. A flashlight emits into a smaller solid angle. The same electrical power can produce a higher brightness down the beam because it is distributed over a smaller angular region. Legacy optics describes this with divergence and intensity profiles. RSI describes the same structural fact as the effective anchor plane is smaller, so EA API core can be larger than EATP at the same range. I am not claiming optics is literally gravity. I am claiming the geometry doctrine is the same if the coupling is corridor-like. Use a corridor-like interface. 3.4% anchor influence analogy and overlay clarity. People often reach for mystical language when they try to talk about how systems influence each other at a distance. I do not need mysticism here. RSI gives me a clean way to talk about an anchored identity's anchor influence, and I will label that as an interpretation layer statement. If you want a picture, you can imagine an anchored identity's anchor influence as an aura around it, generated by its existence within the relative context of a larger system. In the RSI view, the existence of the identity generates an effect from the field, larger system context, and that effect is what we observe and measure across the 4 force domains. I return immediately to RSI language though, interface choice, shell or corridor, stability distribution across that interface, and gate evaluation via S equal to EA AP EQ 1. So you could imagine identities surrounded by a perfectly symmetrical aura. Then you can either place an identity fully within the other's aura, or you can overlap only part of the shells, creating an imbalance in the direction of the overlap. RSI seems to point to the conclusion that anywhere space is compressed, whether that be overlapping shells, areas of influence, or into an identity, there is a slope in that direction. Which is exactly what Einstein was trying to express by using curved spacetime as his geometric overlay, which was a brilliant move, but I intend to take it to its natural conclusion and describe all of reality and the events within as relative in themselves, not just tied to spacetime overlay. The fact that time becomes paradoxical conceptually when applied across domains, in L terms, is a sign of a mapping error. Many theories have tried to solve this by stacking many more overlays dimensions, etc., RSI starts by abandoning the overlays so it can locate and calculate the primitives, then maps reality once it has an accurate picture of the territory. These concepts could take an entire book to explain on their own, but for the purpose of this intro book, I think the point is made clear enough. I eliminate time as a fundamental, and by doing so, I am free to model reality as a present moment, causal, deterministic, and finite, yet recursively unbounded system lattice. Only after systems are solved within the ledger and lattice can we then use the space and time overlays as tools to understand from our mind-based contextual viewpoint. As simply as I can put it, reality cares about causality, chronology, and resolution, not the brain-based overlays we use. Time is our representation of the physical fact that there is a propagation rate to reality, and at the high end within our relative context-dependent system structure is the speed of light. For physical change to happen, events must take place, and because those events can't happen simultaneously and still have causal or chronological structure, a propagation rate and limit is a natural and expected feature of a reality that operates on cause and effect. Time measures rate of change, existence causes imbalance gradients, those gradients require resolution, and that resolution happens causally. So in RSI, existence and anchored identities are fundamental, not the overlays that describe them. Tier 1 definition language. Tier 1, RSI does not need any extra primitive noun here. Tier 1 only needs this, a boundary, an interface AP, or an effective interface AP EF, an anchored budget EA, and the gate ratio S equal to EA AP. Tier 2, interpretation language. Tier 2, I use plain language shorthand for a practical fact about coupling range in a given context. An anchored identity has a finite region of non-negligible coupling in a given context, because its interface evaluated stability ratio and its stability gradients become too small to matter beyond that region. In shell regimes, the anchor influence region is the region where the shell evaluated S, R, and its changes remain operationally meaningful. In corridor regimes, the anchor influence region is more structured, coupling can be strong along a corridor linkage and weak outside it, because the effective solid angle is restricted. This is why I treat anchor influence as an interpretation layer statement. It is not a substance, and it is not a third energy reservoir. It is a context-dependent description of how the interface and the ledger distribute coupling capacity. I also keep the gates separate while I say this. S is the existence gate, holds now, and DC is the change gate, must transition. When I talk about a region of influence, I'm describing where gate values and their gradients are large enough to matter in the context, not inventing a new gate. Cross-scale examples without changing the grammar. In everyday gravity overlays, the anchor influence region is simply the region where the stability ratio and its gradients are large enough that motion overlays like falling and orbiting are obvious to us. In electromagnetism, a charged system can have a strongly structured anchor influence region because geometry is not only shell-like. Conductors, boundaries, and materials create corridor-like and shielded regions that concentrate or exclude coupling. In nuclear structure, the anchor influence region is extremely short-ranged in legacy language. RSI reads that as an interface regime where the effective coupling region is highly constrained, and the relevant interface is not a large shell. I am not solving those domains in this part. I am keeping the universal relativity promise. The grammar stays the same, the interface changes. 3.5 corridors as a membership tool, captured without inventing a new planet. The corridor idea is not an abstract flourish. It shows up whenever I'm trying to reason about sparse data anomalies and system membership. If two massive systems pass near each other, their spheres of influence can form a transient overlap. In that overlap, I can get a capture corridor. Objects can be deflected, exchanged, or temporarily stabilized in a way that is extremely hard to infer from limited kinematic data alone. In legacy mechanics, I model such events by integrating trajectories and asking what orbits are bound. RSI adds a different diagnostic that comes earlier. Before I draw any directionality indicators, verdict arrows, what interface is actually mediating the coupling during the encounter, and what is the correct effective anchor plane for that coupling? If the coupling is corridor-like, then the relevant interface is not the full shell AP. The existence verdict can move in or out of a threshold range just by correcting the geometry carrier, especially for near-threshold configurations. This is one reason RSI can be useful in system allocation problems. In sparse data regimes, a correct corridor interface can shift the gate verdict enough to decide whether a candidate body is a member, a transient capture, or a passer, even before I can trust a long-run legacy vector integration. A corridor capture is not only a gravity story. In RSI terms, it is a membership reallocation mechanism. The operative interface becomes APF instead of a full AP, and in multi-anchor environments, the partner allocation, EQ10, shifts which portions of the ledger belong to which anchored identities in that overlap pocket. That combination can move a near-threshold configuration across either gate, first S, admit or reject existence on the interface, then DC, stable band or forced transition, without inventing an extra planet, an unseen field, or a hand-tuned energy split. I will make the membership logic explicit later using EQ10, because multi-anchor allocation is where membership becomes a ledger readout rather than a proximity guess. For now, the corridor doctrine is the prerequisite. If I mismodel the corridor as a full shell, I will mismodel membership. 3.6 operational recipe card, choosing the interface without drifting. Whenever I do a real RSI calculation later, I use this checklist first. It is the simplest drift prevention tool I have. The chosen interface. Do not retrofit legacy force language yet. Part 3, geometry doctrine, shells, corridors, and why inverse square appears. And recheck whether I accidentally hand split a multi-anchor environment instead of using EQ. 10.5. Only after the RSI native verdict is stable do I overlay legacy, comparators. That is where I compare to Newtonian gravity, Coulomb, language, lensing observables, orbital periods, and so on, without letting those overlays rewrite the RSI ledger. The most important part of that recipe card is the ordering: geometry, then ledger, then gates, then allocation, then overlays. Ordering is what I mean. By solver posture, the system is solved by the ledger verdict, and directionality indicators, verdict arrows, are a map of that verdict, not the thing that produces it. 3.7 Work mismatch fix, shell estimate versus corridor. Estimate. I want at least one concrete worked reconciliation in this part, because corridor versus shell will otherwise stay too abstract. Suppose I evaluate S using a full spherical interface and obtain a near threshold value, call it SPH. I then revisit the physical configuration and realize the coupling is not isotropic. It is mediated through a restricted overlap pocket with effective solid angle less than 4. I compute a corridor evaluated value score. The conceptual move is simple. A smaller effective interface yields a larger S for the same each. As a concrete numerical illustration, a previously computed shell value near 0.83 can become a corridor value near 0.942 without changing any ledger primitives. The entire correction is geometry selection. Written as a ratio, the boost factor is Rx equal to supple, scored 0.942, 0.83, 1.135, using the corridor amplification relation X equal to 4, the corresponding. Effective solid angle is 4p 11.07 senior tenth, which is smaller than the full spherical 412.57 SNR, exactly as expected for an overlap pocket. Two things matter about this example. First, the correction did not touch T, DE, or any decay assumption. It changed only the interface. That is what I mean when I say many RSI mismatch moments are not new physics. They are geometry selection errors. Second, the correction did not introduce a parameter hack. The solid angle OMF is not a free constant that I tune to force agreement. It is a geometric description of the coupling region. In principle, it can be estimated from configuration information if the geometry is known, and in practice, it is exactly the kind of quantity I can try to infer from repeated anomalies if the corridor window recurs. This kind of reconciliation is exactly what I expect to happen in multi-body environments like Sun, Earth, Moon, and in sparse data outer solar system structure. The moment I stop pretending every interaction is mediated over a full 4p shell and instead treat operational coupling as a corridor pocket, I can move near threshold existence values in a way that is honest and controlled. 3.8. The key anti-drift sentence. When I catch myself slipping into legacy distance decay language, I repeat one sentence until the model is clean. In RSI, T does not decay with separation. Apparent drop-off is geometry in AP, and partner allocation in multi-anchor closure, EQ, 10, not a weakening of T. Everything that follows in later parts, including gravitational overlays, Coulomb overlays, orbital membership, lensing as sideways stability gradients, and ultimately the strong and weak overlays, should be readable through that sentence without forcing any new distance decay postulates into the RSI ledger. 309. Next we talk system membership. Part 3 locked down where geometry is allowed to live, and it gave me a clean corridor mechanism that explains why a full shell model can mispredict near threshold configurations without invoking new physics. In Part 4, I'm going to use this doctrine to define what a system lattice actually is in RSI and how membership works operationally. In legacy practice, I often start with directionality indicators, verdict arrows, and then ask what the system is. In RSI, I reverse the order. I first compute the ledger verdicts and gate values on the correct interface, and only then do I draw directionality indicators as a map of what is already solved. That reversal is where the system lattice becomes a practical tool. It tells me what is inside a system, what is outside, and what is merely passing through, even when the kinematic data are too sparse to make the legacy integration approach feel trustworthy. When I present that lattice as a graph, the nodes are identity nodes representing anchored identities, and the edges are interfaces that carry geometry honestly, but the underlying computation remains the same scalar gate and allocation procedure. 3.10. What this part established. This part established the geometry doctrine I will not violate later. Separation dependence belongs in AP and in multi-anchor allocation, not in T or D. In the shell regime, inverse square overlays appear because S equal to EAP is evaluated on an interface that grows like R2. In corridor regimes, many near-threshold mismatches are fixed by replacing a full shell interface with an effective corridor interface and re-evaluating S without touching the ledger primitives. For Part 4, the system lattice picture. In Part 3, I enforced a strict discipline: geometry lives in AP, and I do not let geometry leak into T, DE, or any other ledger variable. That discipline is not a stylistic preference. It is the mechanism that keeps RSI portable across domains, and it is what makes membership a solvable question rather than a narrative label. Now I need a practical picture that I can reuse everywhere. In legacy physics, the system is usually chosen by convenience. I write down a force law, I choose a coordinate chart, I integrate trajectories, and then I decide what the system is by looking at what the trajectories seem to do. That approach is not wrong, but it has a weakness. The definition of the system becomes downstream of the directionality indicators, verdict arrows I drew, and in sparse data regimes those indicators can be ambiguous for a long time. In RSI, I reverse the order. I hypothesize a structure first, and I test that structure against the gates. If the structure passes, I treat the system as solved at the level I care about, solved in the sense of membership, stability, band, and closure. Only after that do I draw directionality indicators, verdict arrows, as a summary of a solved structure. Those directionality indicators do not build the system. The system is the solved lattice. The simplest way to hold that structure in my head is a lattice picture. Identity nodes represent anchored identities, meaning resolved identities in RSI package language in lattice mode. Node means identity node, not a new primitive. Edges are coupling interfaces, meaning shells or corridors whose geometry carrier is an anchor plane evaluated through AP, or an effective APF. Shell versus corridor selection, a practical rule of thumb. I default to a shell when the coupling is approximately isotropic around an anchored identity, so the interface is well approximated by a full spreading surface APR. I treat the shell case as dilution across area, so inverse square overlays appear as SR equal to EA APR with APR R2 inside the interface. Example, shell. For gravity around a roughly spherical body, at separation R from its center, I use the shell interface APR, not an extra 1 R2 factor outside AP. I switch to a corridor when coupling is confined to an overlap pocket or constrained path, meaning the interaction participates in a restricted solid angle rather than the full 4P shell. 4P so, R, AP OMF. I model that by defining an effective interface. APFR equal to SEFR equal to EA API R is larger than the shell value for the same EA. Sample corridor in a close encounter capture window or a shared Lagrange pocket regime where only a narrow overlap participates, I use APEE, so I do not misclassify a corridor as a full shell. If I catch myself writing an extra R or R2 anywhere outside AP, I stop and rewrite. In RSI, geometry is confined to the chosen interface by doctrine. I keep DE as an integer recursion count, not a distance proxy, and I let shell versus corridor do the separation work through the interface choice. This is the posture shift I care about. I stop thinking in terms of a bunch of things in space, and I start thinking in terms of a candidate network of anchored existence that must close 4.1%, what I mean by system in RSI. A system in RSI is not everything inside a boundary, and it is not everything that feels a force. A system is the smallest closed set of anchors and couplings that passes the existence gate and remains coherent under the change gate. Minimal lattice picture, conceptual. Identity nodes, A, primary anchored identity, B, secondary, C, tertiary, 10th candidate or intruder. Edges, A, B, shell interface, B, C, shell interface, AC, weak corridor, XB, transient corridor. In RSI, I do not start from vectors. I start from whether this candidate lattice closes under the gates in multi-anchor closure. Figure 1, a minimal system lattice picture. Identity nodes represent anchored identities, edges are coupling interfaces, shells or corridors, evaluated on the correct interface geometry. System membership is allocation, not proximity. When I say member in RSI, I mean allocated in the closure ledger. A candidate anchored identity is a member only if it contributes materially to closure, EQ 10, while the admitted edges clear the existence gate, EQ 1, and the configuration remains inside the stable band of the change gate, DC, EQ 5. In other words, I do not award membership for being nearby in a coordinate chart. I award membership when closure allocation and gate outcomes say the edge is real in the declared context. I want to say this carefully because it is where most readers will unconsciously revert to legacy habits. In RSI, a system is not defined by a coordinate region. It is defined by closure. That means two things. One, a system is always contextual. What counts as closed depends on what I include as environment and what I treat as external. This is also why I call this book an introduction to universal relativity. I am not only making a physics claim, I am making a posture claim. Any description I use, whether vectors, time parameters, curvature language, probability, or calibrated constants in a measurement overlay, is a reporting overlay tied to context. The system itself is the solved closure object. So when I say the solar system, I do not mean whatever is near the sun, I mean a lattice hypothesis, a set of anchors and coupling interfaces, such that the ledger closes, the existence gate admits the relevant edges, and the change gate keeps the configuration inside a stable band. In many practical regimes, this agrees with the usual intuition. In hard regimes, where a body sits between competing anchors, or where a corridor turns on briefly during a close encounter, RSI gives me a sharper vocabulary: member, non-member, pass-through, overlap, intruder. 4.2 identity nodes, anchored identities as resolved identities. An identity node is an anchored identity represented in this lattice picture, meaning it clears the existence gate at its own boundary in the context I am modeling. At the anchor boundary, RSI is deliberately simple. Existence is measured by the resolution state SEQ1. The anchor boundary is 1 RSU layer, so dr anchor equal to 1 EQ. S6D at boundary. Therefore, EA equal to T at the boundary, EQ. S6EA equals T. This does not mean every anchor has the same size or the same physics. It means RSI refuses to hide the definition of exists, now behind a field equation. Existence is the gate S equal to EAA. Different objects differ because their interface ledger AP differs, their closure environment differs, and their partner allocations differ. Universal relativity note: anchored identities are contextual, and identity nodes are modeling choices. Whether I treat something as an anchored identity and therefore represent it as an identity node depends on my context. A molecule is an anchored identity in one context, but a fluid parcel in another. A planet is an anchored identity in one context, but part of a rotating multiple structure in another. I do not treat that as inconsistency. I treat it as the core principle. The descriptive layer is context dependent, but the solver layer must remain coherent inside each declared context. 4.3 Edges, interfaces that carry geometry honestly. An edge is a coupling interface between anchors. This is where the Part 3 geometry discipline becomes operational. An edge is not a line segment in space. It is a physical interface whose geometric dilution is carried entirely by an anchor plane. In practice, I use two main edge types. Shell edges, a full spreading interface modeled by a spherical anchor plane APR such as EQ, S4 AP of R. Corridor edges, an overlap pocket or band modeled by an effective corridor interface APEF. That represents a restricted solid angle participation in the interaction. The edge type is not decorative. It is the difference between energy spreads across a whole shell and energy couples through a narrow overlap in RSI. The difference is expressed by choosing the correct interface. I do not encode it by weakening T with separation, and I do not bury it inside DE. A corridor interface stated in the cleanest form. When I need a corridor model, the clean RSI move is to define the effective interface as a restricted fraction of a shell interface. APEFR, OMEF, 4P APR, 0 less than OMEF less than 4P. Then the existence gate evaluated on the corridor becomes CEFR equal to EAP EFR. This keeps all geometry where it belongs, inside the chosen interface. What an edge carries as a ledger record. When I say edge, I mean a record with at least these fields, because these are the things I will later use for closure and for diagnostic comparisons. Interface geometry, recursion span, orientation gate, partner weight, AP for shell edges, or APF for corridor edges, no geometry outside the interface. D counted as an integer layer span for the interaction ledger, never treated as a distance proxy. Theta as the sign or coherence factor used only inside the engine and closure relations, EQS. 6, 10. Q as the scalar partner quantity that calibrates participation in closure, EQ. 10. I keep this list explicit because it prevents drift. If I find myself wanting to add and also the distance vector, I know I am sliding back into legacy mechanics. In RSI, the lawful place for distance-like dilution is the interface, and the lawful place for direction-like effects is the orientation gate theta in closure and engine terms. Trajectory arrows, meaning directionality indicators, verdict arrows, come later as reporting overlays. 4.4 Contextual horizons, where a system stops being a system. This is one of the most important ideas to make explicit early. A system has a horizon in RSI language. I am not using horizon in a mystical sense here. I am using it in an operational sense. A horizon is the last resolved interface for a given context and boundary choice. In RSI, an edge is an edge only if it is resolved on the correct interface geometry. That resolution is evaluated by the existence gate. So a natural way to speak is, inside the horizon, the relevant edges clear the existence gate so the lattice can close and membership can be meaningful. Beyond the horizon, the candidate edges fail the existence gate for the given interface geometry, so the coupling does not define membership at that context. In RSI terms, I treat that as anchor influence, and I keep horizon as the gate-defined boundary of resolved edges in the declared context. A horizon is the boundary where the interface no longer admits a resolved edge for the declared context. The Tripp limit as a context ceiling. Later I will use the Tripp scale language as the ceiling regime where recursion is so resolved that change is suppressed and the world looks effectively flat in that context. Here, I only need the conceptual link. Horizons are context dependent. A horizon in one context may not be a horizon in a larger context. This is the practical meaning of universal relativity in RSI. There is no single privileged boundary that all observers must adopt. There are consistent solver verdicts inside each declared context. Why I introduce horizons this early. The horizon concept is the bridge between everyday system membership and cosmology. The same logic that tells me whether a moon is a member of a planetary system in this context is the logic that later lets me talk about event horizons and cosmological far-to-field horizons in a single grammar. The details differ by regime, the posture does not. 4.5 Membership becomes a verdict, closure, not proximity. The lattice picture matters because it turns fuzzy membership language into a verdict language. In legacy practice, membership is often inferred indirectly. A small body is part of a system if it seems bound, if its orbit fits, if long integration stays in a region, or if it shares a dynamical family. Those are reasonable operational definitions. They are also often ambiguous in the regimes where we most want clarity, limited observation windows, crowded multi-to-body environments, and transient corridor events. In RSI, I can ask a sharper question. Does this candidate participate in closure in a way that keeps the system resolved and stable in the context I declared? Membership question stated in the most operational form. In practice, I treat membership as an allocation question. Does EQ 10 give the candidate a non-negligible share of closure while the relevant edges clear S greater than or equal to 1 and the configuration remains inside the stable band for DC? If the allocation share is negligible, proximity is not membership in RSI, it is just proximity. That question decomposes naturally into the two gates. Existence gate is the coupling a resolved edge. A candidate interaction between an anchor and a body has to clear the existence gate on the correct interface geometry. That means I evaluate S using EQ 1 with AP for a shell regime or with APF for a corridor regime if I cannot make the coupling clear. S greater than or equal to 1 on any physically justified interface, then the edge is not a resolved binding. At best, it is a weak perturbation or a transient influence that does not define membership. Change gate. Does the lattice remain in a stable band? Even if an edge exists, it can still destabilize the lattice. The collapse ratio DC EQ 5 and its regulated closure form EQ 7 tell me whether the configuration is inside a stable band or driven into collapse. I make the threshold language is explicit in the equation stubs. DC greater than or equal to 1 marks collapse EQS, S8 DC threshold, and S8 DC band. So when I ask whether a candidate belongs, I also ask whether including it pushes any anchor past the collapse gate. The verdict categories I actually use. For a candidate body X relative to a model system S, I use 4 categories that will show up again later. 1. Member. The relevant edges are resolved, the lattice closes under multi-anchor accounting, and the configuration stays inside the stable band. 2. Pass-through. X can influence the environment, but its closure participation is negligible. In RSI terms, its ledger share is near zero, and its edges never become decisive for closure. 3. Transient capture. A corridor edge becomes resolved during an encounter, overlap pocket, producing temporary closure participation that later shuts off as the corridor geometry changes. This is the clean RSI language for capture corridors. Membership can be time local without being an identity claim. 4. Intruder or disruptor. The edges may be resolved, but including X pushes the lattice past the change gate threshold. In that configuration, X is not a member, it is a trigger for reconfiguration. This is where the directionality indicator doctrine becomes practical. In RSI, I do not draw directionality indicators to define these categories. I compute gate outcomes and closure participation. Then I draw directionality indicators as a map of the solved verdict. 4.6. Multi-anchor closure. How I avoid hand splitting. The lattice picture only earns its keep if multi-body interactions are handled cleanly. That is why EQ 10 is one of the most important equations in the whole framework. EQ 10 is the discipline that replaces the most common failure mode in multi-body reasoning, hand splitting. In legacy contexts, it is easy to say something like, half the influence comes from here and half from there without stating what rule imposed that split. In RSI, I do not do that. Anchored energy closes by partner sum, EA equal to XQ theta DC. When I want to speak with indices, I treat that sum as running over the neighbor set of an anchor. The point is not the indexing style, the point is the posture. I do not manually allocate EA, closure allocates it. This does not assume a Newtonian pairwise potential decomposition. It does not assume vector addition of forces as the primitive. It assumes that anchored existence is an accounting object, and that partners participate in its closure through scalar terms whose sign and coherence are carried by theta. Determinism without vectors, stated precisely. When I say RSI is deterministic and scalar first, I mean, given a declared context, a boundary choice, an interface geometry choice, and closure inputs, the gate verdict is determined. The directionality indicator, verdict arrow, and coordinate descriptions I draw afterwards are reporting overlays that summarize what was already decided. This is the sense in which RSI lets me say the system is solved. A stable lattice is solved with respect to membership and persistence, even if I later choose to overlay detailed trajectory computation for visualization or comparison. Ledger closure stays explicit and positive, because I never hide energy. In negative wells, the ledger remains transparent. Total recursive energy SG is explicit and positive, EQ 4. When I talk about binding, I am talking about how EP and EA partition under closure and how the gates behave, not about subtracting an arbitrary reference potential. 4.7 ledger share or direct allocation readout. The closure sum in EQ 10 is the right rule, but in practice I want a fast diagnostic that answers allocation questions immediately. When I'm doing system identification, I want to know which partner is actually carrying closure for this anchor. Is a small body truly a member, or is it a neighbor with negligible closure participation? If a body sits between two candidate systems, which system claims it in the context I declared? For that I use the ledger share partner I in the closure of an anchor, defined as EQ 4 pesos ledger share Q10 DEIS equal to sigma Q0 des. This diagnostic is deliberately simple. It is dimensionless. It is defined directly from the closure terms already present in EQ 10. It does not introduce any new primitive object. Part 4, the system last picture. How I interpret ledger share. I interpret F as how much of the closure demand for this anchor is carried by partner on that is not automatically the same as a mass fraction and not automatically the same as a force fraction. It is an RSI closure diagnostic. In domains where 0 is positive and coherent, the shares behave like ordinary fractions that sum to 1. In sign domains, the sign of 6 can be meaningful, so I can either track sign share to represent opposed closure, or track magnitude share to represent total participation irrespective of sign. The definition remains the same. The interpretation is domain dependent. Allocation as a membership tool. Suppose a small body X is in the neighborhood of two larger structures. Legacy analysis often has to wait for long observation arcs to see whether X is bound to one system, bound to the other, or passing through both. In the lattice picture, I can set up two competing hypotheses. Hypothesis S1X participates in closure primarily with anchor set of 1. Hypothesis S2X participates in closure primarily with anchor set of 2. Then I evaluate which hypothesis produces a consistent lattice that clears the gates, and I compare the resulting ledger shares. If Fx is stable and non-negligible under S, but remains near 0 under $2, that is an allocation verdict. If both are non-negligible, I do not force a label. I treat the situation as an overlap regime and revisit the interface geometry, because overlap systems are exactly where corridor edges matter. Why this unifies part of the system across domains. The phrase part of the system is loaded in every domain. In orbital mechanics, it means bound membership. In condensed matter, it means participation in a collective mode. In nuclear physics, it means participation in a coupled state. In RSI, I unify these by using the same closure language. If a partner participates materially in closure and the lattice stays stable, it is a member. If it does not, it is not allocated, even if it is nearby. If its participation pushes collapse, it is an intruder in that configuration. This is also where RSI becomes predictive in a practical sense. If I observe ledger shares drifting, I treat that as a structural warning. It tells me that a new partner term is rising, a corridor is turning on, or a previously negligible edge is becoming relevant. Those are the signatures of upcoming reconfiguration events, and they can appear in the ledger before a long trajectory integration makes them obvious. 4.8. A practical workflow for sparse data hypothesis lattices. I want to state the practical workflow that falls out of this part because it is one of the main reasons I care about RSI. When data are sparse, legacy dynamics can stall. You can integrate many candidate orbits, but you can also fit many models. The ambiguity is not always about arithmetic, it is about system definition. RSI gives me a workflow that is solvable earlier. 1. Propose a candidate lattice L, anchors and plausible edges. 2. Choose the correct interface geometry for each edge, shell versus corridor. 3. Evaluate the existence gate on those interfaces. 4. Enforce closure with EQ, 10, and reledger share diagnostics. 5. Check change gate stability using DC and its threshold band. If L passes these checks, then it is a defensible model of system membership and stability in the declared context. If it fails, I do not paper over the failure by adding a new planet or a new force. I ask whether I chose the wrong interface, whether I declared the wrong boundary, or whether the situation is genuinely a reconfiguration event. This is how I keep RSI from becoming an unfalsifiable story. The lattice either closes or it does not. 4.9. What this part established. I define the RSI system lattice as a graph of anchored identities, identinodes, and coupling interfaces, edges, where edges are evaluated on the correct interface geometry and cleared by the existence gate, EQ. 1. I made membership a verdict. A candidate belongs if it participates materially in closure while clearing existence and remaining inside the stability band set by the change and collapse relations, EQs. 5, 7, and the threshold stubs. I introduce contextual horizons as last resolved interfaces for declared context and boundary choice, linking everyday membership questions to later cosmological horizon language. I enforce the multi-body discipline, no hand-splitting, anchored energy closes by partner sum, EQ, 10, with sign and coherence carried by theta. I defined ledger share, EQ, 4 pesos ledger share, as a direct allocation readout that supports system allocation decisions without introducing new primitives. 4.10. Next, we cover multi-body interactions. Part 5 is where I stop speaking abstractly and do a flagship macro demonstration. I take a conventional, stable 3-body configuration, then introduce a 4th body as a foreign intruder. I will show what I can decide using RSI lattice verdict language before I ever draw a vector diagram, membership versus pass-through, stability versus imminent collapse, and how the ledger share diagnostic highlights which partner is actually carrying closure. That example is also where I will juxtapose what RSI can decide quickly versus what legacy analysis usually needs long observation arcs to infer. Part 5, macro adjudication benchmark, unit, coherence check. Part 4 ended with a promise. I will stop speaking abstractly and demonstrate what RSI can decide in a familiar macro setting. I am going to do that now. I am choosing a scenario that has enough structure to be realistic, but not so much detail that the baseline becomes a numerical ephemeris book, a stable 3-body configuration, and a 4th body that enters the region. In legacy language, this is the Sun-Earth-Moon problem with an intruder. In RSI language, it is a lattice membership and stability test. The goal is not to produce a high-precision trajectory. The goal is to answer the solver question that comes before trajectories. Does the configuration as proposed hold as a resolved system? And if it holds, is it driven toward deterministic change? I call this the macro adjudication benchmark because it is the fastest way to check whether the reader and I are using the same grammar. I also treat it as a unit coherence check, meaning I verify that the ledger quantities and interface choices are being used with consistent units and roles before I ever draw an overlay diagram. If we are aligned, the outcome categories become crisp immediately. If we are not aligned, we drift back into an argument about vectors, potentials, or probability, and we lose the point of RSI. Unit coherence check. When I say unit coherence check, I do not mean a trivial dimensional analysis exercise. I mean the specific RSI discipline that prevents me from smuggling geometry or dynamics into the wrong primitive when I am under pressure to explain a messy macro scenario quickly. In this benchmark, I confirm, explicitly, that I am using the primitives in their declared roles. T is energy per RSU layer, J. D is an integer layer count, dimensionless. EF equal to TDJ and EA equal to EFDJ, with the anchor boundary D equal to 1 giving EA equal to T. The existence gate is S equal to EA AP EQ 1, evaluated on the correct interface geometry, meaning all radius factors live inside AP. Change gate is DC equal to EF, EA, EQ, 5, and it is not the same statement as existence. The total ledger quantity remains explicit and positive. SE equal to EF plus EA, no. Hidden reservoirs, no negative wells. If I can state that grammar cleanly, then the rest of the macro discussion becomes a disciplined application of the gates and the multi-anchor allocation rule, not an argument about which legacy overlay diagram I prefer. 5.1 Macro example setup: Sun, Earth, Moon, and a candidate intruder. I begin by declaring the cast of the configuration. I label the anchors: S, the Sun, primary anchor at this scale; E, the Earth, secondary anchor; M, the Moon, tertiary anchor; X, the candidate intruder, a foreign body entering the neighborhood. In RSI language, each of these is an anchored identity at the declared macro context. When I draw the lattice picture, I represent each anchored identity by an identity node, and I represent each coupling by an interface edge, shell, or corridor. That is a reporting convenience. It does not replace the gate definitions. It just keeps the bookkeeping visible. Then I declare the minimal lattice I am testing. This matters because RSI is explicit about boundaries. A system is never an undefined cloud of influences. A system is a declared configuration with a declared boundary and declared couplings. For this example, I will use two closely related boundary questions because they mirror how real research questions are posed. Question A, membership. Is X a meaningful member of the Sun's planetary system in the present configuration, or is it a fly-through corridor encounter? Question B, stability under intrusion. Does the proposed four-body configuration remain inside a stable band, or does it drive one of the relevant subconfigurations toward a threshold, meaning forced reconfiguration? Those questions sound like legacy orbital questions, but the RSI move is different. I do not start by fitting orbital elements and integrating for a million years. I start by asking whether the lattice is resolved now, and whether the lattice is driven toward deterministic change. To make the lattice explicit, I name the couplings I expect to matter. The dominant large-scale coupling is SE. The dominant local coupling is EM. A weak long-range coupling exists SM, but in this baseline, it is not the defining edge for membership questions. The candidate couplings for the intruder are XS and XE, and sometimes XM if it passes close. Now I impose the Part 3 geometry doctrine. Every coupling edge must be evaluated on the correct interface geometry. That means I must choose, explicitly, whether each edge is shell-like or corridor-like. I do not fix a geometry mismatch by modifying DE or by letting T decay. I fix it by choosing the correct interface. In simple words, SE is usually shell-dominant for a baseline macro discussion because the effective interface at that scale samples a broad solid angle. EM is often corridor-dominant because the coupling is mediated through a restricted overlap pocket rather than a full 4PI interface. Lattice hypothesis, conceptual. Identity nodes S, EM, and candidate X. Each identity node represents an anchored identity in the declared context. Edges, SE shell, EM corridor, SM weak, and one or more candidate edges involving 10th RSI question. Does the hypothesized 4 identity node lattice clear the existence gate on the correct interface choices, and does it remain inside a stable change band under multi-anchor closure? Figure 2, a 4 identity node lattice hypothesis. For the macro adjudication example, identity nodes represent anchored identities in the declared context. RSI does not begin by integrating trajectories. RSI begins by checking whether the configuration is a resolved system now, and whether it is driven toward deterministic change. X is the whole point, because depending on its path, it can couple as a transient corridor, brief overlap, or as a persistent edge, capture. To keep this anchored visually without relying on external graphics, I use a simple lattice picture. Baseline assumption: the 3-body core is stable before the intruder. To make this an adjudication example rather than a chaos lecture, I assume the known 3-body core is in a stable band before X enters. In RSI language, that means the relevant edges are resolved, existence gate admitted, under the correct interface geometries. The relevant subconfigurations are inside the stable change band, meaning DC less than 1 in the sense of EQ, S8 DC band. I am not claiming the real Sun-Earth-Moon system is perfectly stable in every sense, or that perturbations do not exist. I'm saying the baseline configuration is an admitted, persistent lattice for the context I am using. That is the point of having the 2 gates. I can admit existence now, and still track slow drift or eventual reconfiguration later. 5.2 Legacy framing: why inference is hard in sparse observational regimes. I want to be careful here. Legacy physics can model multi-body orbital mechanics extremely well when the observational inputs are rich and when numerical integration is feasible. So my claim is not that legacy physics cannot compute. My claim is that legacy workflows often blur 2 separate problems: trajectory prediction given a fixed system, system identification and membership under limited information. The Sun-Earth-Moon system is a classic case where the full 3-body problem is not solved in closed form in the same way the 2-body problem is. In practice, we use perturbation theory, numerical integration, and ephemeris fitting. That works. But it also hides a key epistemic problem that shows up whenever we look at slow systems with long periods from sparse data. It can be hard to decide what the correct system hypothesis even is. This difficulty shows up in multiple places. Outer solar system anomalies involve slow motion, long periods, and short observational arcs. Candidate perturbers can be inferred indirectly as residuals. A transient visitor can mimic a member over a short arc, simply because the arc is too short to see whether the interaction is a bound closure or a fly-through corridor event. Legacy mechanics resolves this by doing what it is built to do. It integrates, it fits, it estimates parameters. Over long arcs and with enough data, that is decisive. RSI is not trying to replace that integration. RSI is trying to provide a prior classification step that is available even when integration is underdetermined by data. In other words, RSI wants to answer, is the candidate object X even eligible to be treated as a member of this system, as a matter of gate closure and allocation? This is why the existence gate and the geometry doctrine matter. If the configuration including X does not clear the existence gate under any physically justified interface geometry, then RSI classifies it as a non-member, regardless of how messy the short arc looks. 5.3 RSI framing, change. Adjudicate existence, then adjudicate. In RSI, I treat the configuration as a lattice, and I perform a deterministic audit. I keep the audit steps explicit because the explicitness is the point. Step 1. Declare the identities and the boundary question. I begin by stating what I mean by the system in this question. That sounds trivial until you realize how often real arguments come from silent boundary drift. For question A, membership, the boundary question is X a closure participating partner in the sun-centered configuration, or is it only a transient corridor encounter? For question B, stability, the boundary question is, does adding X push any relevant subconfiguration toward an existence threshold, meaning S1, or a collapse threshold, meaning DC1, forcing rerouting or reconfiguration? Those questions already hint at the two gates. The point is that I do not start from a vector diagram. I start from a declared system hypothesis. Step 2, choose the correct interface geometry for each relevant edge. This is where most drift used to occur, so I make it an explicit step. For each edge, I decide whether the coupling is shell-like or corridor-like, and I choose the corresponding AP. For the baseline example, a clean choice is, use a shell interface for SE, use a corridor interface for EM. Treat X as unknown and test both regimes, transient corridor overlap versus persistent edge. The doctrinal point is the same as part 3. If I choose the wrong interface, I will miscompute the existence gate. I do not fix that by modifying DE or weakening T with separation. I fix it by choosing the correct AP for the physical interaction region. When I need a corridor model, I keep it RSI clean by defining an effective interface as a restricted participation of a shell interface. OMEF, APEFR, 4P, APR, 0 less than OMEF less than 4P. Then the existence gate uses the effective interface directly, CEF R equal to EAPP Step 3, adjudicate present existence of candidate edges. Now I evaluate the existence gate in its canonical form, EQ1 S equal to EA.AP. In this macro example, there are two levels of existence I care about. Existence of edges, is the coupling resolved? If the coupling I am using to justify membership is not resolved, then the edge is not a binding edge in RSI. In practice, that means if the XS interaction is only a brief overlap pocket and it fails the existence threshold when evaluated on the correct effective interface, then RSI classifies it as a fly-through influence, not membership. If the XS or XE coupling remains resolved on a persistent interface, then it is eligible to be a membership edge. Existence of the proposed boundary, is the system resolved as declared? Even if individual edges exist, the overall proposed configuration may fail to be a coherent resolved system at the boundary I care about. This is the difference between an object that interacts and an object that belongs. This is also where RSI differs from common intuition. In legacy language, an object can interact gravitationally without being bound. In RSI language, an object can contribute weakly without being allocated to closure. Membership is not defined by interaction. It is defined by participation in closure of the resolved configuration. Step 4, enforce multi-anchor closure and read membership through ledger share. If X clears the existence gate on a physically justified interface, I move to closure. Closure is where the lattice becomes a solver. For an anchor, multi-anchor closure is done by EQ. 10, E1 equal to QAD, L. This equation is the discipline that prevents hand splitting. It also gives me a practical membership meter, the ledger share, EQ, 4 pesos ledger share. S1 equal to Q11 des, sigma Q0D. I read Fx as the membership meter for X in the closure of the relevant anchor. The definition is deliberately simple. It does not add a new primitive. It reads EQ, 10, as a normalized fraction. Now the membership interpretation becomes concrete. If Fx remains effectively 0 across the stable band of configurations, then X is not a meaningful member of the resolved system, even if it perturbs trajectories. If Fx becomes non-trivial and remains persistent, then X is participating in closure, which is RSI language for membership. If X spikes briefly during an overlap and then returns to near 0, that is a transient capture corridor signature, not a persistent membership signature. If Fx rises and forces other shares to reroute while thresholds are approached, then X is acting as a destabilizer, meaning the lattice must reconfigure. This is the RSI prior classification step in a single sentence. Membership is a closure and allocation statement, not a proximity label, and not a trajectory fit label. Step 5, adjudicate change and threshold approach. Finally, I evaluate the change gate EQ, 5, EF, D equal to X. In this baseline macro demonstration, I do not need to compute a numerical D to show the classification logic. What matters is how I use it. If the configuration that includes X remains in a stable band, I expect DC to stay below the collapse threshold in the relevant sub-configurations, meaning no forced reconfiguration, EQ, S8 DC band. If adding X pushes a sub-configuration toward DC, 1, then I am approaching a deterministic barrier. If DC crosses threshold, RSI interprets it as force change, not as probabilistic instability, EQ, S8 DC threshold. When I care about rates and the pacing of change, I close DC through the engine relation, EQ, 7. I am not using that closure numerically in this baseline part, but I will use it later when I discuss orbital reconfiguration pacing, stability horizons, and deterministic decay closure. A tiny toy readout, illustrative, not an ephemeris. To make the closure language feel real without pretending I am producing a new NASA ephemeris here, I use a simple toy readout. I emphasize it is illustrative. Assume the baseline 3-body lattice is stable. DC baseline less than 1. FS dominates Earth closure, FM is secondary at Earth. Now imagine X enters. In a fly-through, FX stays near 0, and the other shares barely move. The lattice remains the same lattice. In a transient capture corridor, FX spikes briefly when the overlap pocket turns on, then returns to near 0 as the pocket turns off. In a persistent capture, FX becomes persistently non-trivial, and the lattice remains inside DC less than 1%. In destabilization, FX rises while DC approaches threshold for some subconfiguration, and the shares reroute sharply before an eventual reconfiguration event. This is the solver posture I keep emphasizing. Even if the trajectory overlay looks ambiguous for a while, the closure pattern can classify the regime earlier. 5.4 Intruder Outcome Taxonomy, 4 solver-relevant cases. Once I frame the problem with the lattice and the 2 gates, the meaningful outcomes become crisp. I do not need to enumerate a dozen qualitative cases. There are 4 solver-relevant cases, and they map directly to gate patterns and allocation patterns. I want to be explicit about the split between 2 ideas that are often mixed in casual talk. Transient capture means a corridor edge becomes resolved for a time and produces a temporary allocation signature. Persistent capture means the edge remains resolved and the allocation signature remains non-trivial in the stable band. That split is exactly the difference between it looked bound for a while and it became a member. Outcome A, fly-through, not a member. This is the case where X only contributes through a transient influence that never becomes a closure-carrying edge. It can perturb local motion, but it is not allocated to closure. In RSI terms, one or more of these conditions holds. The proposed binding edge involving X does not clear the existence gate on a physically justified interface. The ledger share Fx remains effectively 0 in the stable band. The configuration clears existence for the original SEM lattice, but the configuration that treats X as a member does not clear existence as a resolved closure. What does this look like observationally in legacy language? It looks like a flyby, a gravitational assist style event, or a weak perturbation. If the observational arc is short, it might look ambiguous. RSI does not claim the trajectory will look simple. RSI claims membership is not ambiguous if closure participation is near 0. Outcome B, transient capture corridor, temporary edge, temporary allocation. This is the case where a corridor edge turns on for a time because the overlap pocket geometry becomes favorable. For that interval, the coupling is resolved, and the closure sum can show a temporary allocation signature. Then the geometry changes and the corridor shuts off. In RSI terms, I expect all of these. The X coupling clears existence only in a limited window and only under the corridor interface. X spikes in that window and then returns to near 0 outside it. The stable band is not permanently broken. If a collapse threshold is approached, it is approached as a transient warning, not as a persistent crossing. The legacy feel here can be confusing. It can look like a temporary satellite, a strange resonance, or a short-lived perturbation that leaves a small imprint. In RSI language, it is not mysterious. It is an overlap pocket event that turned on a coupling interface temporarily. This is also where RSI can be predictive in the practical sense. A corridor window can be tied to configuration geometry, meaning it can recur. If corridor windows recur, they can produce repeated anomalies in the same region without requiring a permanently bound hidden member. Corridor capture as a general membership reallocation mechanism. I want to generalize this because it is easy to misread transient capture as a special gravitational curiosity. In RSI, transient capture is the generic signature of a coupling interface whose geometry has a duty cycle. When the overlap pocket exists, the edge can clear the existence gate on an effective corridor interface, and the multi-anchor closure sum reallocates shares accordingly. When the pocket closes, the edge fails existence again, and the ledger share returns toward its prior baseline. This is the same mechanism that shows up in other domains as temporary binding, catalysis windows, near-threshold scattering, or short-lived resonance locking. The domain-specific overlay story changes, but the solver-level pattern is the same. A corridor turns on, allocation shifts, then the corridor turns off. Outcome C, persistent capture, new member. This is the case where the intruder's coupling persists, and the configuration reallocates closure in a stable way. Capture in RSI is not random energy loss. Capture is a stable band classification. In RSI terms, the signature pattern is the X coupling clears existence in a persistent way under the correct interface geometry. The system including X remains resolved at the relevant boundary, meaning the existence gate does not collapse toward threshold. The change gate remains in a stable band for the relevant sub-configurations, EQ, S8 DC band. The ledger share Fx becomes non-trivial and remains persistent across the stable band. This is the key point. Capture is not an extra phenomenon I append to the model. Capture is a configuration that lies inside a stable band bounded by deterministic barriers, with closure reallocation that keeps the system resolved. In legacy mechanics, capture often requires dissipation. In RSI, the language is different and the posture is different. The relevant question is whether the ledger enclosure support a stable lattice that includes 10th. If they do, the configuration is admitted. If they do not, it is not. I will reconcile this with dissipation and scattering overlays later. For this macro adjudication test, I am showing the solver stance. RSI decides capture as a closure verdict first, then I can ask what overlay mechanisms, dissipation, tidal coupling, resonant transfer, explain how the configuration moved into that band. Outcome D, destabilization, intruder forces rerouting. This is the case where X couples strongly enough that one or more subconfigurations is pushed toward a threshold, meaning the lattice must reroute. In legacy language, this is chaos, instability, or a transition to a new orbital family. In RSI language, it is a threshold approach and a forced reconfiguration. In RSI terms, I expect one or more of the following. A relevant existence gate approaches threshold, S1, because the interface requirement in AP is no longer underwritten by the available anchor budget in that configuration. A relevant change gate approaches collapse, DC1, indicating forced change, EQ, S8 DC threshold. The ledger shared distribution reroutes rapidly, meaning a new partner term is rising and the closure network is reorganizing. This outcome is the one that produces the most confusion in sparse data regimes. Short arcs can make it look like the system is doing something inexplicable. In RSI language, the system is doing something very specific. It is crossing a stability boundary in the lattice. 5.5 verdict table, gate patterns to classification. To make the macro adjudication benchmark truly fast in practice, I want a single table that maps the gate and closure readout patterns to the classification. This is the table I want a reader to internalize, because it is the lens that makes RSI feel like a solver rather than a story. In the table below, I use X edge exists to mean the relevant coupling clears the existence gate under, a physically justified interface choice. FX to mean ledger share readout, EQ, 4 pesos ledger share for the relevant. Anchor closure, stable band to mean DC less than 1 in the relevant subconfigurations. EQ, S8 DC band, case X edge existence FX behavior gate and workflow. Readout, fly through, transient capture, persistent capture, destabilization, fails or only marginal, exists only in corridor window, exists persistently, exists and grows, approximately equal to 0 always. Spikes then, returns approximately equal to 0, non-trivial and new stable lattice admitted. Persistent closure reallocates but remains in stable band. Now trajectory overlays are drawn after the verdict to describe the admitted configuration. Threshold approach in S or DC, treat as deterministic reconfiguration regime, look for which share rises first as early warning, grows while shares reroute. Lattice remains effectively the same as baseline, treat X as a perturber, not a member, integrate for trajectory overlay if needed. Corridor overlap pocket turns on, then off, expect localized anomalies. Do not promote X to a stable member unless FX persists and stability remains. What I would do with real data. If I were producing a research workflow, I would use the table as an ordering tool. 1. First, I would build the best justified interface model for each candidate edge. Shell versus corridor. 2. Then I would compute gate verdicts and ledger share patterns as classification, even if I do not yet have enough data for a definitive long arc orbit. 3. Only after classification would I allocate computational effort, long trajectory integrations for cases that are persistent or destabilizing, and shorter localized integrations for corridor windows. This is the practical sense in which RSI changes the posture of orbital mechanics. It changes what comes first. 5.6 What RSI adds to the legacy picture. I want to phrase this carefully. Legacy physics can model the above with sufficient data and numerical integration. So the RSI claim is not that legacy cannot compute. The RSI claim is that RSI changes what gets emphasized and what becomes available earlier in the research workflow. RSI provides a prior membership diagnostic. Before I integrate long trajectories, I can ask whether X is even eligible to be treated as a member in closure language. That is what FX is for. It is a membership meter derived directly from the multi-anchor closure rule. This is especially valuable in sparse observational regimes, where the same short arc can be fit by multiple orbital hypotheses. RSI forces interface geometry choice to be explicit. Legacy models can approximate geometry implicitly. RSI forces me to say whether the coupling is shell-like or corridor-like because the existence gate depends on AP, and geometry is confined there. This matters most near thresholds, where a corridor correction can move a configuration from marginal to resolved without inventing new physics. RSI separates existence from change. Legacy language often mixes these. A system can exist now and still be driven toward change. RSI makes that distinction explicit by using S for existence, EQ, 1, and DC for change, EQ, 5. This is exactly what I need to interpret intruders. I can classify membership and stability independently. RSI gives a structural early warning signal. If ledger shares drift, something structural is happening. A new corridor is turning on, a partner term is rising, or a subconfiguration is approaching a threshold. Those are solver-relevant signals even before long baseline trajectory data are available. RSI makes arrows after solve operational. In this chapter, I still describe the macro situation in words. The point I want to carry forward is methodological. If I have classified the lattice as stable, transient, persistent, or destabilizing using gates and ledger shares, then arrows become a visualization choice. They are no longer a prerequisite for system definition. Part 6 will formalize this. Vectors and time parameters remain powerful overlays, but the RSI solver does not require them to decide membership and stability. RSI carries cross-domain unification. The same lattice picture and closure logic applies whether the interaction is gravitational, electromagnetic, or nuclear. In this macro example, I speak in gravitational language because the objects are astronomical, but the solver posture is the same posture I will use when I discuss confinement bands or deterministic decay closure. What this part established. I provided a flagship macro adjudication example that uses the RSI lattice picture instead of vector-first integration as the primary system definition tool. I made the RSI workflow explicit, declare the boundary question, choose the correct interface geometry, shell versus corridor, evaluate existence, EQ, 1, enforce closure, EQ, 10, read ledger shares, EQ, 4 pesos ledger share, then evaluate change, EQ, 5, against stability bands, EQ, S8 DC band. I expanded the intruder outcomes into 4 solver-relevant cases: fly-through, transient capture corridor, persistent capture, and destabilization, each with a distinct gate and allocation signature. I provided a verdict table mapping gate patterns to classification so the reader can run the macro adjudication benchmark quickly and consistently as a unit coherence check. Next part builds out the solve loop. Part 6 formalizes the solver posture that I used informally in this example. I will write the deterministic solve loop as a repeatable procedure: boundary declaration, identity counting, interface selection, ledger closure, gate evaluation, and then change closure through the engine. That is where I turn the macro adjudication benchmark into a general method and repeatable unit coherence check that can be used across domains without rewriting the primitives each time. Part 6, vectors and fields as overlays, the solver posture. Part 5 was the macro adjudication benchmark, a unit coherence check at macro scale. I showed that RSI can adjudicate membership and stability in a familiar macro setting without starting from vector-first integration. Now I have to make the philosophical and technical posture explicit, because this is the place where people usually misread me. I am not saying vectors are fake. I am not saying time is fake. I am not saying the legacy field language is worthless. I use vectors, time parameters, and field language constantly in practice because they are brilliant reporting tools. What I am saying is narrower and more precise. RSI is scalar first as a solver posture. The solver decides existence and change through explicit gates and an explicit ledger. The arrows are drawn after the solve. That phrase has a strict meaning. The direction is already encoded by the imbalance in the solved ledger and allocation. I draw arrows afterward, only to visualize the already solved imbalance in a chosen coordinate chart. In the rest of this part, when I say arrows, I mean directionality indicators, verdict arrows, namely overlay encodings of how the solved scalar verdict changes under small context perturbations. If I do not keep that posture disciplined, RSI turns back into legacy mechanics with new vocabulary. If I keep it disciplined, RSI becomes a unification grammar. The same ledger logic can be used across atoms, apples, planets, black holes, and cosmology, while vectors and time remain as overlays I can add for visualization, approximation, and comparison. The core claim of RSI remains simple. A configuration is either a resolved structure that holds, or it is a configuration that must change. The first verdict is the existence gate S, EQ, 1. The second verdict is the change gate DC, EQ, 5, close through the engine, EQs, 6 to 7, when pacing matters. Everything else I do, including the legacy overlays, is downstream of those verdicts. 6.1 What I mean by overlay in universal relativity, I use the word overlay in a very specific way. An overlay is a descriptive layer that depends on a chosen context and representation. Coordinates are overlays. Time parameters are overlays. Vector fields are overlays. They are not wrong. They are not optional either, because humans need them to think. But they are not the source of the system. Universal relativity, in the sense I am using it here, is not only Einstein's insight that time depends on the observer. It is the broader posture that every description is context dependent. When I say an object is moving, I am already inside an overlay, because motion is a statement relative to a frame, a time parameter, and a chosen decomposition of the world into objects. RSI is my attempt to keep one layer underneath those overlays stable and audit-friendly. The solver layer must be able to say the same thing no matter which overlay language I use to report it. That is the point of the ledger. So when I say vectors are overlays, I mean something constructive, not destructive. A vector diagram, directionality indicators, verdict arrows, is an efficient map of an already solved imbalance. A time series is an efficient index of successive reconfigurations of an already solved structure. A field plot is an efficient visualization of a scalar stability distribution. Once I have decided what I am holding fixed and what I am varying. In RSI, the solver layer produces verdicts and scalar diagnostics. The overlay layer turns those scalar diagnostics into pictures. 6.2 What a field is in RSI? Stability distribution across context. Legacy physics uses the word field in multiple ways. Sometimes it means a fundamental object in a field theory. Sometimes it means a derived vector field like gravitational acceleration or electric field. Sometimes it means an effective potential landscape. In this intro, when I say field in RSI, I mean a stability distribution. I mean a map that assigns gate values and ledger diagnostics to points in a declared context. Field is distributed closure state on interfaces. In RSI, the thing that is distributed is not a separate substance. It is the closure state of the ledger evaluated on a declared interface. For each context point I declare, a separation, a material configuration, a corridor overlap, a channel availability. I can evaluate S and DC, and I can also read out the closure allocation terms that appear in EQ. 10. The collection of those gate values and allocation readouts carried across the context variables of interest is what I mean by an RSI field in practice. This is exactly why the field language remains useful. While still being scalar first, the field is a distributed report of solved closure, not a primitive object that exists before the ledger is built. The simplest RSI field object is not a vector. It is a pair of scalars, as the existence diagnostic, evaluated on a declared interface geometry. EQ, 1. DC as the change diagnostic, optionally engine close when rates matter. EQ, 5, and EQs, 6 to 7. To say it plainly, the RSI field is the map of S and DC over the space of situations I care about. Now I have to be explicit about what space of situations means, because this is another place drift creeps in. Sometimes that space is literal 3D physical space around an anchor. Sometimes it is configuration space of relative states, positions, separations, orientation gates, channel activations. RSI does not require me to commit to one in advance. RSI requires me to declare what I'm varying and what I'm holding fixed. Here is the clean operational definition I use, given a declared boundary and a declared interface geometry. The RSI field is the collection of gate values and closure allocations evaluated across the context variables of interest. This is why the field concept becomes unifying. The same definition applies when the context variables are separations and overlap geometry and orbital mechanics, boundary conditions and materials and electromagnetism, channel structure and identity counting in nuclear regimes, and global context boundaries in cosmology. Field is not a new substance in RSI. In RSI, the field is not a separate substance that carries energy in a hidden way. The ledger is explicit and positive. SE equal to EF plus EA, EQ, 4. When I draw a field picture, I am drawing a picture of that explicit ledger behavior. Field includes allocation, not only gates. The most useful RSI field diagnostic in multi-anchor environments is not only S and DC, it is allocation. Multi-anchor closure is EQ, 10. EA equal to XQ theta DC. That sum has an immediate map-friendly readout ledger shares. I do not need a new primitive to get that. I just normalize the closure contribution CEQ, 4 pesos ledger share for the form I use. So when I say field in RSI, I include this as well. The gate values S and DC, the closure allocation pattern ledger shares, and, when needed, the channel structure that appears in the engine sum. That is the RSI definition of field. It is a stability and allocation distribution across contexts. 6.3 directionality indicators after solve, how vector pictures are constructed from scalars. Now I can say what I actually mean by drawing arrows afterward. Directionality indicators, verdict arrows. I use the phrase directionality indicators, verdict arrows, for the arrow overlays I draw. In legacy notation, a vector is a compact encoding of directionality and magnitude. RSI does not throw that away. RSI treats that encoding as an overlay representation of an already solved scalar map. A directionality indicator encodes I, which way a chosen scalar diagnostic changes under a small perturbation of the declared context point, and 2, the relative steepness of that change, which I may display as arrow length or density. It does not assert that a vector field is fundamental, it does not introduce a new RSI primitive, and it is never evaluated before the gate verdicts and closure allocation are computed. In legacy physics, a vector field is often treated as primary. I write F, X, I integrate trajectories, and the arrows are the computation engine. That works. And it is beautiful. But it hides an assumption. The vector field is the primitive object. In RSI, the primitive object is the scalar ledger verdict. The arrows are a visualization. So the constructive question becomes, given a solved RSI field in the sense of 6.2, how do I produce a vector overlay that looks like the legacy arrow picture? The answer is, I treat the scalar stability distribution as a terrain, and I draw the arrows as slopes of that terrain, a minimal stability terrain. Because S is dimensionless, I can map it into an overlay-friendly scalar terrain in several ways. A common choice is to use a logarithm because it turns ratios into differences. Phys, X, ln X, where X denotes whatever context coordinates I am using, literal space coordinates or configuration variables. This is not a new RSI primitive. It is an overlay function I build from S for visualization and for comparison to legacy potential language. Then I define the arrow overlay direction as the direction of steepest decrease of this terrain. Overlay, X, Phys, X, equal to ln X. I want to be extremely clear about what this equation is and is not. It is not a claim that the gradient operator is fundamental. It is not a claim that PHS is a new physical potential. It is a definition of a vector overlay derived from a solved scalar map, after I have chosen a coordinate chart and a notion of neighborhood in the context space. That is what I mean by arrows after solve. I compute the scalar map first, then I compute differences and slopes, then I draw arrows. Finite difference interpretation, how I actually do it. In code, I usually do not take analytic gradients. I sample the solved scalar diagnostics on a grid of context points and compute finite differences. That matters for RSI because RSI is inherently discrete in its RSU layer counting, and because many of the interesting problems live in irregular corridor geometry, where analytic gradients are the wrong mental model anyway. So the arrow is literally a map of the already solved imbalance. If moving slightly in one direction increases S or decreases DC in a coherent way, that direction is favored as a change direction. If moving slightly in a direction decreases S or increases DC toward threshold, that direction is disfavored or reads as destabilizing. I can draw arrows to represent those directional differences. but the directional differences were computed from scalar verdicts. The direction is encoded by allocation as well. In multi-anchor cases, the direction is not only a geometric gradient, it is also encoded by which partner term is rising. A very practical RSI statement is this. If the ledger share of partner I increases when I move the candidate configuration in a certain way, then the effective arrow of pull points toward the partner whose share increases. That is not a vector axiom. It is a closure diagnostic. It is exactly the sense in which direction is encoded by imbalance and arrows are a map of that imbalance. This is why I sometimes say Feynman was close to this posture. Arrow calculus is a powerful reporting and computing tool. RSI is saying yes, and those arrows are summaries of a deeper closure object. When the closure object is explicit, the arrow picture stops being the foundation and becomes what it always really was, an efficient map. 6.4 time is also an overlay, why RSI does not need a privileged clock. People often assume that if I demote vectors, I must also be trying to eliminate time. That is not what I am doing. Time is a reporting overlay. It is one of the most useful overlays we have. It is also the place where universality breaks if we treat it as privileged. In RSI, what is fundamental in the solver layer is not a global time axis. What is fundamental is which configurations are admitted as resolved, which configurations are driven toward deterministic change, and which channels and closure patterns are available for that change. If I want to report a process as a function of time, I can. The way I do it is by indexing successive configurations in a sequence and assigning a time parameter as an overlay coordinate for the sequence. The solver does not require that parameter to exist as an absolute entity. This is exactly the same posture as in relativity. There is no privileged universal time, but time coordinates are still exceptionally useful within a chosen frame. In RSI, I treat time the same way I treat arrows. First, I solve what holds and what must change. Then I choose how to parameterize that change for reporting. When I need rates, I use engine-regulated closure, EQs, 6 to 7, and I interpret the output in the context of the chosen reporting parameter. When I do not need rates, I do not pretend a rate exists just because I can write a derivative symbol. 6.5. The solve loop in one paragraph. Here is the solve loop in one paragraph the way I hold it in my head, now stated in a way that makes the overlay stance explicit. I declare a configuration and a boundary. I choose the correct geometry carrier, AP, for the coupling, shell, or corridor. I build the ledger by computing EF from T and DE, EQ, 2, and by specifying EA from boundary identity, EQ, 3, and closure. I evaluate existence first, S equal to EA, AP, EQ, 1, because if the configuration is not admitted as resolved, nothing else matters. If it is admitted, I evaluate change, DC equal to EF, EA, EQ, 5, and then I close the change verdict through the engine if dynamics or rates matter, EQS, 6 to 7. If multiple anchors participate, I do not split energy by hand. I allocate by the multi-anchor closure relation, EQ, 10. Then I output a verdict, persistent member, transient member, fly-through, or forced transition. Only after that do I translate the result into legacy language as an overlay, including arrows, time coordinates, and field plots, all tied to the solved scalar diagnostics. Everything in this part is just that paragraph unpacked into steps that can be audited. 6.6 Inputs and declarations, what I need before I compute anything. RSI is boundary explicit. That means the first thing I do is write down what I'm actually testing. I do not let the boundary remain implicit, because implicit boundaries are how drift enters. For any solve, I declare 4 items. 1. The configuration and the boundary question. I say what the system is supposed to be and what I am asking about it. Examples: is this body a member of the system or is it a pass-through? Does this configuration hold or is it forced to change? If it changes, which channel is open and what is the pacing? This is not fluff. Different boundary questions imply different edges and different geometry carriers. 2. The identities, anchors. I list the objects that I am treating as identities in this solve. This can be macroscopic sun, earth, moon, or microscopic nucleus, electron, state, quark triplet. The RSI rule is the same. If I'm calling something an identity, I'm willing to assign it an anchor budget EA and treat its boundary as a one-layer interface when needed. See EQ, S6D at boundary, and EQ, S6EA equals T. T as the energy per RSU layer. D as the integer layer count across the interface. The identity budget's EA is obtained from boundary identity, identity counting, or multi-anchor closure. Once those declarations are made, I can do the solve in a way that is checkable. 6.7 Step A, Geometry Selection, Shell versus Corridor. This is the first place where I enforce the geometry doctrine that prevents drift. All explicit geometry belongs in AP. I do not put stray geometric factors outside AP. I do not hide geometry in D. I do not let T decay with separation. So the first computational choice is what interface geometry is actually in play for the edge. Shell geometry, default. If the coupling samples a full spherical interface around the anchor, I use the spherical mapping, EQ, S4 AP of R. In this regime, inverse square overlays appear because AP grows like a shell area. The weakening is not a weakening of T or EA. It is the same budget distributed over a larger interface. Corridor geometry, overlap pocket. If the coupling is mediated through an overlap pocket or a restricted band, I use an effective anchor plane that corresponds to that restricted participation. I keep the effective interface explicit to avoid drift. OMEF, APEF, AP 4P0 less than OMEF less than 4P. Then I evaluate the existence gate using APE-EF directly. I do not pretend the full shell is participating if only a corridor is. In this posture, the correct fix for many near-threshold mismatches is not new physics. It is selecting the correct effective geometry carrier for the edge, the one geometry audit sentence. Before I move on, I say this sentence to myself. If I'm about to change T or reinterpret DE to fix a distance effect, I stop. The fix is almost always the geometry carrier AP or the effective corridor interface APF. 6.8 Step B, ledger build, compute EF and specify EA. Once the geometry carrier is declared, I build the energy ledger. This is where I force myself to be explicit about units and roles. Compute EF from T and D. Field energy is defined by EQ. 2. EF equal to TDE. I keep two things strict. T is energy per RSU layer J. It is not a field strength per meter. DE is an integer layer count. It is not a hidden radial coordinate. Operationally, this step is where I decide the recursion span of the coupling, which is a modeling choice that depends on regime. In a macroscopic gravity solve, D can be large. In a tightly bound microscopic solve, D can be constrained by identity counting and channel closure. Specify EA without hand waving. Anchor energy is defined by EQ, 3, in the canonical map, and it is tied to the boundary condition D equal to 1 at the interface. EQ, S6D at boundary. In practice, I obtain EA in one of three lawful ways. 1. Boundary identity. At a declared anchor boundary, D equal to 1 and EA equal to T, EQ, S6EA equals T. This is the simplest case. 2. Identity counting. When the regime is quantized by discrete identity units, I use the counting law, EQ, 8, as the lawful way to build EA from the counted structure. 3. Multi-anchor closure. When multiple partners contribute to the anchored budget, I obtain EA through the closure relation, EQ, 10, and its allocation structure. I do not split by hand. This is the point where RSI differs from many legacy narratives. I do not treat EA as a mysterious binding well. I treat it as a ledger entry that must be specified explicitly and positively. 6.9 Step C, gate evaluation in the correct order. RSI is a two-gate solver. The gates are evaluated in a specific order, and I do not swap them. 6.9.1 Gate 1, existence, admit the configuration or reject it. Existence is EQ, 1, EAS equal to .AP. I evaluate this first. The reason is simple. If the configuration is not admitted as resolved at the interface, then there is no point describing its future behavior as if it were a stable entity. Conceptually, I treat S as an admission gate. If S greater than or equal to 1 in the normalized regime for the declared boundary, the configuration is admitted as a resolved identity at that boundary. If it's less than 1 at that declared boundary and interface, the configuration is not admitted and must reconfigure. I treat that as deterministic failure of the proposed resolved structure in that form. The practical note is this. If a verdict surprises me, the first thing I check is whether I chose the correct interface geometry for the edge. Near threshold, shell versus corridor selection can flip the admission verdict. 6.9.2, Gate 2, change stable band or force transition. Change is EQ, 5. I evaluate the second. This gate answers a different question than existence. It does not tell me whether the thing exists now. It tells me whether the configuration is forced toward deterministic change. The canonical threshold posture is in the stubs, CEQ, S8DC threshold, and the stable band relation in EQ, S8DC band. In baseline language, I read it this way, DC equal to EF.EA. If DC stays below the collapse threshold, the configuration is stable in the change sense. If DC approaches threshold, the configuration is near a deterministic barrier. If DC crosses threshold, the configuration is forced to reconfigure. That can mean decay, ejection, fusion, fragmentation, or any other transition, depending on which channels are open. Separation is exactly why the overlay discussion matters. In legacy language, it is easy to blur existence and motion, and treat motion as the defining truth. In RSI, existence and change are two separate solver questions, and motion overlays are downstream reports. 6.10 Step D, engine regulated closure when dynamics and rates matter. A naked ratio DC equal to EF. EA is enough to classify many stability questions. When I care about how the change is routed, which channel is open, or how the pacing behaves, I close DC through the engine. The engine begins with EQ, 6, K equal to X KCH theta DC, and it closes through EQ, 7, DC equal to EF, K BT, 1. The engine makes channel structure explicit. The sum in EQ, 6, forces me to list what channels exist, what their weights are, and what the orientation or coherence factor is for each. This is where RSI encodes what legacy physics often encodes as selection rules, couplings, and phase conditions. I do not treat theta as a decoration. I treat it as the lawful location for sign and orientation gating in a scalar solver. 2. The engine makes change a closed loop, not an intuition. EQ, 7, makes DC a closed condition rather than a free dial. In practice, closing the loop means start from a provisional DC, often the raw ratio EF-EA, compute K from the channel sum, update DC using EQ, 7, repeat until the loop stabilizes or until the configuration exits the stable band. 6.1, 1 step E, multi-anchor closure and allocation, membership as an output. Once I can compute gates and close the engine, the lattice becomes a practical allocation tool. Multi-anchor closure is EQ 10, EA equal to XQ theta DC. Part 6, vectors and fields as overlays, the solver posture. This equation is the single most important anti-drift discipline in multi-body reasoning. It stops me from doing the thing that ruins theories, splitting the ledger by hand. Allocation is not the same as interaction. In legacy language, everything interacts gravitationally with everything. That is true as an effective statement. But it is not the same as membership. Membership in RSI is allocation and closure. A passer can interact without being allocated to the system ledger. A member participates in closure in a persistent way. Ledger share is the readout. In part 4, I introduced ledger share as a normalized read of the closure terms. I do not need new primitives to do that. I just read EQ 10 as a fraction, chi des, k equal to sigma, q0, d. I interpret f as how much of the closure burden is carried by partner I for the anchor I am analyzing. This gives me a practical membership meter. If fx is persistently non-negligible and the lattice is stable, x is a member in RSI language. If fx remains near 0, x is not allocated to closure. It can be a perturber, a fly-through, or a weak neighbor but not a member. If fx rises and forces other shares to reroute while thresholds are approached, x is an intruder that drives a transition in the present configuration. This is why I keep saying systems are solved already. The system is solved when the closure network is solved and the gates produce a verdict. The trajectory arrows come later. 6.12 outputs, verdicts, and the overlay products I allow. Once I have done the steps above, I output a solver verdict. Then, and only then, I generate overlay products. I keep the verdict categories simple because they recur across. Solver verdicts. Domains. Not admitted fails existence. The configuration is not a resolved structure at the boundary I declared. In RSI language, it fails the existence gate. The correct statement is not, it is unstable. The correct statement is, it is not admitted in that form. Admitted but transient, exists now, force change. The configuration is admitted by existence but driven toward deterministic change by the change gate and engine closure. In macro language, this is a captured but decaying configuration. In micro language, this is an unstable state with a deterministic transition window. Admitted and persistent, stable band. The configuration clears existence and remains inside the stable band for change. This is the holds verdict. Intruder-driven transition, forced reroute. A new partner term becomes dominant. The ledger share distribution reroutes, and one or more subconfigurations approaches a threshold. In RSI language, it is a deterministic crossing of a stability boundary. Overlay products, allowed and encouraged. After I have a verdict, I allow myself to produce these overlay products. Directionality indicators, verdict arrows, and field line pictures, derived from the solved scalar stability distribution, as described in 6.3. Time parameterizations and trajectories that index a sequence of configurations, without claiming an absolute clock. Legacy equation comparisons and stated regimes, using calibrated mapping coefficients where needed, without claiming SI defining constants very physically. This is the posture bridge. RSI does not abolish legacy tools, RSI gives them a place in an order. 6.132 work translations Applefall in stable orbit. This subsection exists to prevent a common misunderstanding. If I only speak abstractly, people think I'm avoiding physics. I am not, I am reordering it. 6.13.1 Why an apple falls without making vectors fundamental. People always ask the simplest question, why does an apple fall from a tree? In legacy mechanics, the answer is a vector force and an acceleration. RSI does not deny that acceleration is measurable. RSI changes what I treat as primary. The RSI answer begins with a configuration statement. Configuration 1, apple supported. When the apple is attached to the tree, there is a strong contact edge between the apple and the tree. In RSI language, that edge is an interface with its own effective geometry, and it participates in closure. The configuration apple suspended is admitted because the contact edge plus the rest of the environment produces a resolved lattice that holds. Configuration 2, contact removed. When the stem breaks, I remove the contact edge from the lattice. That is a structural change. The configuration apple suspended with no support edge is not the same system. I then apply the same solver loop, I evaluate existence, and change for the new configuration. In RSI language, the unsupported configuration is not admitted as a persistent hold at that boundary. It must change until it reaches a configuration that is admitted. The admitted configuration is the apple on the ground, where new contact edges exist and closure is satisfied again, where the directionality indicators show up. After I have solved that the apple must transition from one admitted configuration to another, I can generate an arrow picture by sampling the solved stability distribution in the region between the two admitted states. The arrow direction is the direction in which the stability diagnostic increases toward an admitted configuration, or equivalently the direction in which the instability diagnostic decreases away from threshold. The arrow picture is a report of the solved imbalance, not the source of the solve. That is why RSI can speak in the same grammar at every scale. A decay transition in a nucleus is also a movement between admitted configurations, routed by channels. The details differ. The posture is the same. 6.13.2 Why a stable orbit is a contour story, not an axiom story. Now take the next everyday question, why does a satellite orbit instead of falling straight down? Legacy mechanics answers this with initial conditions plus a central acceleration field. That works. RSI does not compete with that. RSI changes the order. 1. First I solve membership, the satellite is allocated to the planetary system, and the relevant edges are resolved. This is the lattice and closure posture. 2. Then I solve stability band. The configuration remains inside the change-adjustable band for the regime of interest, so the orbit is a persistent configuration class rather than a forced transition. 3. Then I draw directionality indicators, verdict arrows. I visualize the stability gradient as a vector overlay and use a time parameter overlay to draw trajectories. In this view, a stable orbit is not mysterious. It is the path that stays inside the admitted and stable band of the lattice, while the reporting overlays describe the path as a curve in a chosen coordinate chart. A useful picture is to imagine level sets of a stability terrain. If the stability terrain is roughly radial around the anchor, then the arrow overlay points inward, toward increasing stability in the sense of the terrain, while the tangential motion overlay can keep the trajectory on a contour. The satellite does not need a new force to make it go sideways. The sideways motion is part of the reporting overlay of the stable configuration class. This is also why RSI is strong in system allocation problems. Even if I have sparse data about the trajectory, I can still ask whether the lattice is admitted and whether the system is inside the stable band. Those are solver questions, not kinematic storytelling. 6.1 for final sanity checks, the drift detectors. Before I trust any RSI verdict, I run the drift detectors. These are the failure modes that created most confusion in earlier drafts. 5. Hand-splitting drift. I confirm that I did not split EF or EA by hand in a multi-body environment. If more than one anchor matters, I must use EQ. 10.6. Hidden reservoir drift. I confirm that the ledger is explicit and positive. SE equal to EF plus EA, EQ. 4, and that any openness was declared. If a solve passes these checks, then I treat the verdict as an RSI result. If it fails any check, then I treat the result as undefined, not as a mysterious new phenomenon. What this part established. I made the overlay stance explicit. Vectors, time coordinates, and legacy fields are not denied, but they are reporting overlays tied to context. I defined the RSI meaning of field as a scalar stability and allocation distribution across context variables, primarily through S and DC, plus closure allocation patterns. I made arrows after solved constructive, directionality indicators, verdict arrows, are computed from solved scalar diagnostics, stability terrains, and allocation gradients, not treated as primitive causes. I preserved and strengthened the deterministic solve loop as an auditable procedure, declarations, geometry selection, ledger build, existence gate, change gate, engine-regulated closure, and multi-anchor allocation. I gave two concrete translations, AppleFall and stable orbit, to show how RSI can remain scalar first while still producing the familiar directionality indicators and vector pictures as overlays. Next we talk proof. Part 7 sets the proof stance. I will define what counts as strong evidence inside RSI, how calibration is allowed and restricted, and what would falsify or force revision of the framework. I will also describe the implementation credibility posture, including what is already encoded in the working mathematical model, what has been checked, and what remains pending, so an educated reader can distinguish Tier 1 results from Tier 2 interpretation and Tier 3 speculation. Part 7, evidence standard, calibration discipline, and how RSI earns trust. Up to this point, I have been building RSI as a solver posture, not as a new vocabulary layer on top of legacy physics. I have defined the ledger, EA, EF, SE. I have confined geometry to AP, I. Have separated present existence from future change, S versus DC, and I have framed systems as a lattice of anchored identities, identity nodes, and edges where membership becomes a verdict rather than a vibe. That posture is powerful, but it also creates an immediate obligation. I cannot ask an educated reader to trust RSI because it sounds unified, or because it gives me a story I like. I have to be explicit about what would count as success, what would count as failure, and what I am allowing myself to calibrate. This part is where I define my proof standard. I do not mean proof as in a formal theorem in a vacuum. I mean, what evidence would convince a skeptical technical reader that RSI is not just interpretive poetry? 7.1 What RSI is claiming, at the evidence level. RSI is not finished, and it is not a replacement of all physics in a single draft. It is a disciplined attempt at a unification posture under strict guardrails. That posture is, the core -12 equations are a small, explicit solver skeleton. They compute ledger carriers and gate verdicts. They restrict where geometry is allowed to live. They restrict what may be calibrated and how calibration must be reused. I'm going to make three things painfully clear. RSI does have calibrated constants, but I treat them as mapping coefficients, not as magical tuning knobs. RSI does have domain overlays, but those overlays must be written as consequences of the same ledger and gate structure. RSI does have strict failure modes, and I name them in advance. If RSI needs new knobs per system, or if it needs distance decay hidden in Tor D, then it is not a solver. If it does not have auditable failure modes, then it is not falsifiable. 7.2 What success looks like. If RSI is real, it should do something very specific. It should reproduce known scaling families from the ledger and the geometry rule, without introducing new distance-dependent fudge factors. It should reproduce discrete outcomes, quantization-style phenomena, as closure outcomes of the same ledger grammar, not as separate postulates. It should reuse the same primitives across domains, instead of redefining the primitives when I move from gravity to electromagnetism to nuclear structure to decay. It should produce falsifiable gate and closure signatures, membership, instability, confinement, decay permission, that I can check against observation, not only against my own narrative preferences. In other words, RSI should be able to earn trust through repeated, structured reuse. 7.3 What this part does. This part gives a reader a concrete evidence map. I specify 1. What I count as strong evidence inside RSI. 2. What I allow myself to calibrate and what I forbid myself to tune. 3. Why cross-domain reuse is the unification test. 4. The minimum flagship validation suite I treat as the evidence floor. And 5. How I interpret legacy physics as overlays instead of as competitors. 7.4. What counts as strong evidence inside RSI. In RSI, I treat evidence as a hierarchy of checks. Some checks are hygiene. Some checks are the actual reason this program deserves attention. I want a reader to be able to disagree with my interpretation while still conceding that the proof standard is clear and that the failure modes are named in advance. A prediction, test, card template. What I mean by an evidence standard. When I say evidence standard in RSI, I mean I can write a compact card for a claim, declare the interface model, state the ledger target, state a tolerance band, and state the kill test before I look at the data. I do not get to move those goalposts later without admitting that I changed the claim. I include a kill test column because in practice a framework usually fails by a single decisive counterexample, not by a slow accumulation of discomfort. A kill test is the observation that forces me to stop, rather than rescuing a mismatch by quietly swapping shell for corridor, redefining AP, or introducing a new calibration constant for a one-off case. Part 7, Evidence Standard, Calibration Discipline, and How RSI Earns. Observable Setup RSI Target Tolerant Pass, Fail Rule Kill Test, Gravitational Vertical Path Compute. Band, 1%. Redshift H, 22.5 million rands, Z equal to as S Zez. ZRSI band, wrong sign or order of readout Z shell regime, escape, APR via EQ, 9. Atmospheric exobase bound threshold, boundary shell versus corridor near to 1 AP, explicitly 4. Photon energy threshold, hydrogen ionization, threshold scan M scale count width, overlay with desistant, cleared interface bromine approximately equal to 13.6 EV. Magnitude, posture miss. Qualitative, he, airy declare classification while escape a clear count heavier tear example species remain under the light species, bound declared, boundary, 0.1 EV ionize IF input ionize below, exceeds threshold persist old above without changing the heavy nucleus, stability edge, nuclear series, stability edge 2 strong overlay near atomic EQ, 11 track number 83 is the lone X, overlay exception check, declared interface. No long lived a stable nuclei cleaves far be well beyond the edge. Edge without a declared new in, weak half pin weak scale predict life scaling once, neutron T1 2 C. Factor 2. Lifetime, then 1 second under the reuse same pin. Eddington stellar surface, D1 cross 10 to 20% style limit boundary, ing yields an. Multi-body POSL, M-band tour declared overlay. Hill sphere Earth Sun style D equal to 1 cross, 5% boundary 2 anchor, sissing near. Tem EQ 10, 1.5x 10M used for Alica, overlay Tion, within, interface claim. Band 10 times miss, or, after as AC requires greater than on, counted. No stable star A stable con, well above band figuration, far without and out above the band. Flow channel with no wind or mass loss channel. No stable satel persistent stellite well beyond bow orbit well. The boundary beyond the predicted bound airy. Table 2 prediction, test card template I use in this book with representative example rows. Closure checklist what I verify, minimum, item. SE equal to EF plus stays explicit and positive, and I account for transfers, no hidden reservoirs. Energy closure. All distance and area scaling is confined to geometry smooth gap, only EQ. 11 may carry explicit 2 rands out gling, treat aside AP, a decisive failure. Mode. Geometry discipline. Gate roll, discipline S, answers existence. Now, DC answers change the permission and I do not conflate them uninterpretable. I stop and restate the model. Verdict is, I pin overlay scale once per regime, then reuse curve fitting, not it across cards without retuning a solver posture. Calibration reuse. Symbol and unit T remains energy per layer, DE remains in canon violation, simple and integer count, and I do not hide geometry I treat it as an errand side either or. Falsifier stated up, each card has an explicit kill test that I agree front will count as failure if triggered. Unfalsifiable posture, the reader should reject it. If it fails, I do not the result consistent. Call RSI. Table 3, closure checklist, the minimum engineering posture I apply to every RSI claim in this introduction. Part 7, evidence standard, calibration discipline, and how RSI earns. In parts 8 through 11, I start filling these cards with the 4 flagship validations. And in part 14, $14, I turn them into an operational workflow. Part 14 is where I make the procedure explicit, pick a target, declare the interface, pin once, reuse, run the closure checklist, and accept the pass or the kill test outcome. If a validation passes, I keep the pin and expand the reuse suite. If it fails, I do not hide it. I either revise the interface claim or I drop the mapping for that regime. 7.4.1 Tier 0, internal hygiene. Tier 0 is necessary and not sufficient. If I violate Tier 0, the rest is not worth reading. Unit and row consistency. T is energy per RSU layer, J. DG is a pure integer count. EPTDG is energy, J. SEA, AP is the existence gate, EQ, 1. In this intro, I treat say S, a dimensionless gate ratio, because it carries the interface scaling and its coupling factor C, EQ, S4 AP of R, and the calibration stubs in section S4. If I write something that breaks this role structure, it is a mistake. Gate separation. Sensors exist now. Dancers will transition. EQ. 5, with its closure through EQ. 7 when needed. If I mix those roles, I am not solving anything, I am narrating. Geometry confinement. Distance and area scaling live in AP. If I encode distance fall off into Tor into DE, I'm smuggling an inverse square family in the back door and RSI becomes a word game. Ledger positivity. Sigmag EP plus ed stays explicit and positive. EQ. 4. I do not introduce negative wells as hidden storage to patch contradictions. Multi-anchor accounting discipline. In multi-body environments, I do not split EP or XB hand. I allocate through the explicit partner sum, EQ, 10, 7.4.2 Tier 1, scaling reproduction without per-case tuning. Tier 1 is where RSI becomes interesting. A program like RSI should reproduce broad, robust scalings without micro-tuning. This is where inverse square behavior matters. Part 7, evidence standard, calibration discipline, and how RSI earns trust. If I can show that an inverse square family arises directly from SEA, upon a shell mapping, then RSI has earned something. It is not magic. It is what happens when the ledger carrier that matters is C, EA, upon the relevant interface is a shell mapping, EQ, S4, AP of R. The decline comes from interface growth, not from a distance-dependent decay of T. Tier 1 also includes quantization posture. If I can show that a configuration is forced into discrete stable channels because the closure only admits certain resolved states, then quantization stops being a bolt-on mystery and becomes an output of the solver. Tier 1 evidence still is not enough, because many theories can reproduce a scaling law if they are allowed to choose a constant for every case. 7.4.3 Tier 2, calibration pins that must be reused. Tier 2 is calibration discipline. In RSI, I only allow a small number of calibration pins that set scale for an overlay mapping, and then I require reuse across many cases. This is where I have to be careful with myself. If I let myself calibrate per case, I can fit anything. If I let myself change geometry regimes without justification, I can pretend that any mismatch is just a different geometry. As an evidence standard, Tier 2 is simple. A single reference pin sets the overlay scale. Then the same pin scale must be reused across multiple independent checks without retuning. If RSI needs a new constant for every new system, it is not a solver. It is relabeling curve fitting. 7.4.4 Tier 3, cross-domain reuse. Tier 3 is cross-domain reuse. This is the unification test. If RSI is truly a single solver skeleton, then the same ledger and gate grammar must survive as I move across domains. Specifically, when I move from gravity to electromagnetism, I do not redefine Sorday. When I move from electromagnetism to nuclear structure, I do not invent a new distance scaling rule. When I move from strong structure to weak decay, I do not suddenly appeal to probability as a primitive if I have been claiming determinism at the gate level. If cross-domain reuse fails, RSI can still be useful as a modeling language, but it does not deserve the name Universal Relativity. 7.4.5 Tier 4, explicit failure modes and kill tests. Tier 4 is where I force myself to be falsifiable. I do not want RSI to be unfalsifiable. So I name the failure modes I am watching for in advance. Geometry outside AP. If I find I must add explicit distance powers outside AP to make flagship replications work, then the geometry confinement rule has failed and RSI has drifted into disguised legacy form. Hidden primitives. If accurate reproduction of a domain requires me to introduce new primitive state variables that are not ledger carriers, not identity counts, and not geometry mappings, then RSI is not actually a closure-first framework. Gate roll drift. If I find I must mix existence and change, or I must split EF by hand instead of using the multi-anchor rule, or I must appeal to irreducible probability to reproduce weak rates, then RSI has violated its own solver posture. A note on the last point, because it is the most consequential philosophically. If weak interaction rates truly require probabilistic primitives rather than deterministic channel gating, then RSI's strongest claim fails. That does not mean the entire program becomes useless, but it does mean I would have to retreat to a hybrid interpretation where determinism is not fundamental. But to this point, we do not see randomness in daily life from systems where we can clearly identify all influences. Probabilities remain tied to sparse data in regimes where we don't have absolute certainty of inputs. 7.5% implementation credibility. Is this a working model or paper only? A reader should ask, is this just a conceptual shell or is it executable? This matters because many frameworks can sound coherent conceptually, but only a subset survive contact with an actual solver. So I answer directly. I built the Core 12 and the surrounding diagnostic workflow as a working Mathematica codebase, and I often describe the process as discovery because the equations emerge by pruning contradictions under the guardrails, not by guessing the final form in advance. That does not mean every overlay mapping is finished. It means the solver skeleton is implemented, and it means the theory is testable in the strongest sense. I can point to the code path that produces a verdict. 7.5.1 What is implemented? At the level of the intro, these are the implemented components that matter most: ledger carriers and gate definitions. The model enforces which symbols are ledger carriers EA, EF, sigma, which are gates, SDC, which are geometry, carriers AP, and which are closure weights, Q, theta, KCHE. This prevents role drift in code not only on the page. Geometry mapping and interface selection. Shell AP mappings are implemented in a way that keeps all distance dependence inside AP, for example EQ, S4 AP of R. Corridor interfaces are represented as effective interfaces APEFF, tied to restricted participation, rather than as a hidden tuning of T existence gate evaluation. Given declared E and AP, the model computes S, EQ, 1, and classifies admitted versus not admitted. Given declared EF and EA, the model computes DC, EQ, 5, and classifies stable band versus threshold versus collapse, using the threshold stubs in section S8. Engine-regulated closure loop. When channel structure matters, the model computes K from the channel sum, EQ, 6, and closes DC through the regulated form, EQ, 7, until the loop is stable or until the configuration exits the stable band. Multi-anchor closure and allocation. The model computes anchor closure through the partner, sum, EQ, 10, and outputs allocation readouts ledger shares EQ, 4 pesos ledger share. This is the implementation backbone for membership verdicts and system allocation problems. Calibration pin workflows. Gravity overlay calibration is implemented as a pin and reuse workflow using the S4 calibration stubs, with the intent that electromagnetism, strong and weak overlays follow the same discipline. Overlay readouts as products, not primitives. The model produces scalar diagnostic maps first, then it can generate arrow overlays or stability rain plots as reports derived from the scalar field. 7.5.2, what is tested and what that means. I use the word tested in a strict sense. I mean the code produces outputs that are consistent with the stated guardrails and consistent across repeated runs under declared inputs. In this intro, that includes internal consistency tests. Unit roles are preserved, gate roles are preserved, and multi-anchor closure is never hand-split in the solver path. Geometry confinement tests. Inverse square families arise from shell AP mappings and not from any distance decay of T. Corridor cases only change the effective interface, not the per-layer tension. Closure and allocation stability tests. In toy lattices, like the intruder classification in Part 5, ledger share patterns behave exactly as the membership logic predicts: fly through, transient corridor capture, persistent capture, or destabilization. Calibration pin stability. The gravity pin workflow is structured so that a single reference configuration sets the scale factor, and the code then reuses it across new checks. I am not claiming in this subsection that every domain is already validated to journal standard. I am claiming something narrower and more important for credibility at this stage. The solver skeleton is executable and internally consistent, and it produces deterministic verdicts that can be audited step by step. 7.5.3, what is pending? To prevent overreach, I list what is explicitly pending. These are not small details. They are the main reasons this intro is an introduction and not the final universal treatise. Broad empirical validation across domains. Gravity overlay checks are the most mature. Electromagnetism, strong and weak overlays have strong internal structure, but the breadth of external validation is still pending. Domain calibration reuse suites. Each domain needs a pinned reference. Workflow that is then reused across multiple independent checks without retuning. That is the core test for calibration discipline. Uncertainty and sensitivity analysis. Threshold verdicts can be sensitive to interface selection, shell versus corridor, and to boundary declarations. A mature RSI program must quantify that sensitivity and state confidence bands clearly. Public reproducibility packaging. The solver needs to be packaged so an independent reader can reproduce the verdicts with a declared input sheet and a declared interface model. This intro establishes the grammar. The packaging is a next step deliverable. 7.5.4, a small pseudocode window to make working model concrete. I do not want to turn this intro into a software manual, but I also do not want to hide behind words. So here is the minimal computational skeleton in pseudocode form, purely to show that the solver posture is executable. Core gates. Z op equal to EA op, DCF EA equal to EFE. Shell interface example. Appsphere equal to 4 pi R2 degrees Celsius. Multi-anchor closure. Partners are records with Q, theta, DC. E-closure partners equal to total Q theta. Engine loop sketch. K-sum channels DC equal to total Kish theta. DC closed EFKBT equal to EFKBT. That is not the full model, but it is the solver skeleton, explicit carriers, explicit gates, explicit closure. 7.6 calibration pins and reuse. Calibration is not cheating. Every serious theory has parameters that must be pinned from experiment. The question is whether the parameters are fused, stable, and reusable, or whether they proliferate. In RSI, I treat calibration as pinning overlay scale, not editing solver structure. Structure is carried by the ledger and the gates. Scale is carried by a small set of coupling factors that appear only inside permitted carriers. This is also where I want to be precise about the language of constants. Calibrated constants are mapping coefficients, not new physical knobs. In RSI, many constants that appear as fundamental in legacy overlays can be treated as calibration coefficients that map between the RSI ledger language and the SI overlay language. That does not mean RSI predicts those constants fluctuate in time. It means RSI treats them as the practical scaling limits of a contextual description pinned by reference measurements. This is exactly the posture I want. Constants become part of the dictionary between overlays and the solver, not a separate list of unrelated physical axioms for each domain. 7.6.1, what I allow myself to calibrate. I allow myself to calibrate the following, and I state it explicitly so it cannot drift: a small number of coupling scale factors inside permitted carriers. The cleanest example is inside the shell mapping AP, R equal to 4 pi R2 degrees Celsius for a gravitational regime, EQ, S4 AP of R. One calibration pin set C, and then I reuse that across gravitational predictions. Identity unit conventions. If a domain requires a unit count, for example a charge unit count, or a discrete identity count U, I allow myself to pin the unit conversion to SI through a reference measurement. The test is whether the closure logic then reproduces families of outcomes. Boundary declarations and geometry regime declarations. RSI is boundary explicit. I must declare what the system boundary is and which geometry regime applies shell, corridor, overlap, pocket. That is not a fit knob. It is part of the modeling statement, and it is itself falsifiable. 7.62 What I forbid myself to tune. To prevent RSI from becoming unfalsifiable, I forbid the most common escapes. I do not allow TTO decay with distance. If I need a decline, it must come from AP, because that is the point of geometry confinement. I do not encode distance into DE, dace, a layer count, not a radial coordinate. If I need to represent distance, I represent it through the interface mapping in AP. Part 7, Evidence Standard, Calibration Discipline, and How RSI Earns Trust. I do not add ad hoc geometry multipliers. If a shell estimate fails, and a corridor estimate succeeds, the corridor must be justified by an actual overlap geometry, not by the desire to make the numbers match. In RSI, different geometry is a physical claim. I do not introduce hidden reservoirs. The ledger is explicit. E.g. EP plus X is on the page, EQ. 4. If I need negative energy to make a story work, I have left RSI. 7.6.3 A concrete calibration pin pattern, gravity, conceptually. I will not do a full numeric derivation here because the flagship replication is in part 8, but I want the pattern to be crystal clear. The calibration workflow looks like this. 1. Choose a reference configuration that is well measured and structurally simple. For gravity, the obvious pin is the Earth surface regime. 2. Use the RSI carriers and gates to express the reference measurement in RSI terms. In practice, this means I treat the Earth boundary condition as a normalized admission point, CEQ, S4 says Earth. 3. Solve for the coupling scale factor. For gravity, sin the shell mapping. This is the only place where I'm allowed to pin scale in the gravity overlay. 4. Reuse the same factor for new predictions, orbital membership verdicts, stability band checks, and stability ratio diagnostics, EQ. 9. That correspond to redshift or dilation style readouts as overlay reports. This is the difference between calibration and fudge. A calibration pin sets a scale once, then the rest is reuse. A fudge changes the scale whenever I move to a new system. 7.7 Cross-domain reuse is the unification test. In legacy physics, the 4 fundamental interactions are often taught as fundamentally different entities, different fields, different mediators, different symmetries. Those tools are powerful, and they work. RSI does not dismiss them. RSI changes the question. The RSI claim is that beneath those domain-specific languages there is a single solver skeleton. Part 7, Evidence Standard, Calibration Discipline, and How RSI Earns. The same ledger carriers, EA, EF, EE, the same geometry confinement, AP, and the same 2-gate posture, SD, apply everywhere. The forces are overlays, meaning they are different closure readouts of the same underlying ledger discipline. So the unification test is not, can I talk about everything with the same words? It is, can I keep SEA, APAs, the existence criterion in every domain, even when the interaction looks non-classical? Can I keep D, E, F, E, A with stability threshold discipline as the change gate in every domain, even when the change looks probabilistic? Can I keep geometry strictly in AP, even when the distance dependence looks exotic? Can I allocate multi-anchor contributions through the explicit multi-anchor rule rather than by hand? If I succeed, then the overlays are genuinely unified. If I fail, then RSI still might be a useful organizational framework, but it is not the unified solver it claims to be. Cross-domain reuse is also the strongest anti-drift mechanism. It prevents me from patching each domain independently. The same mistakes recur if I let them. I will be tempted to sneak distance falloff into T, I will be tempted to treat DG as an analog distance coordinate, and I will be tempted to patch a mismatch by changing geometry regimes without justification. Cross-domain reuse punishes those moves because the patch that saves one domain will break another. 7.8 How I label claims in this book. Because this is an introduction, I need a way to separate solver facts from interpretation. Otherwise, I risk either underselling the framework or overselling it. So I label claims in 4 categories. Verified solver structure. These are statements that follow directly from the core 12 and the guardrails, and are implemented in the executable model. Example, existence is computed by SEA, AP is verified structure. Part 7, Evidence Standard, Calibration Discipline, and How RSI Earns Trust. Derived overlay consequence. These are consequences of applying the solver structure to a declared geometry regime plus a calibration pin. Example, inverse square overlays in a shell regime are derived consequences of SAND AP. Hypothesis under test. These are claims that require external validation across a suite, not just an internal derivation. Example, a specific strong overlay quantitative fit beyond the qualitative binding structure is a hypothesis under test until the reuse suite is complete. Interpretation layer. These are philosophical or cosmological readings of what the solver implies about reality. I allow these readings, but I label them. Example, pre-Big Bang math suggests a larger substrate context is an interpretation layer statement until it is supported by explicit predictive checks. This labeling is not a rhetorical shield. It is how I keep the book honest. It is also how a reader can engage without having to accept my metaphysics in order to evaluate the solver. 7.9 The 4 flagship validations. A skeptical reader should not be asked to read 50,000 words before seeing what counts as real success. So I commit now to a minimum evidence suite, 4 flagship validations, 1 per overlay. Each flagship has 3 components. 1. A single calibration pin. 2. Reuse across multiple checks, and 3. At least one clear failure condition. I preview them here. Parts 8 to 11, execute them. 7.9.1, Flagship A, Gravity Overlay. The gravity flagship is not derive Newton again. It is show that the inverse S-square family is a direct consequence of SEA up under the shell mapping, and then show that the solver can adjudicate stability as a verdict. Minimum checklist. Single calibration pin, Earth surface regime sets the gravitational scale factor, conceptually the SEM embedded in the shell AP. Reuse 1. Reproduce a basic orbital stability verdict without introducing a new constant. Reuse 2. Show that a stability ratio, EQ, 9, posture, yields a redshift or time dilation style check as a readout of stability differences, not as time curvature treated as primitive. Failure conditions. If I cannot keep distance scaling confined to AP, I fail geometry confinement. If I need new per orbit knobs, I fail calibration discipline. 7.9.2, Flagship B, Electromagnetic Overlay. The EM flagship tests two things. 1. The same geometry logic should produce Coulomb scaling in the shell regime, and 2. The discrete nature of charge outcomes should be readable as closure. Minimum checklist. Coulomb scaling, show inverse square scaling as an AP, effect, consistent, with the same geometry doctrine used in gravity. Sign and orientation, show that attraction versus repulsion is not a second force law but a closure orientation rule, carried by an orientation factor like thin the overlay. Quantization posture, show that identity unit counting, EQ, 8, posture, plus closure yields discrete charge outcomes as a solver readout, not as an arbitrary postulate. Failure conditions. If I must introduce a new distance fall-off independent of AP, I fail cross-domain reuse. If quantization cannot be expressed as closure, RSI loses one of its main explanatory advantages and becomes only a scaling model. Force versus potential energy in the electromagnetic overlay. When I say the electromagnetic overlay validates an inverse square law in RSI, I am talking about the distance scaling of the field intensity or force that the overlay reports. With the shell carrier APRR2, so for fixed EA I have SR equal to EA APR1 or 2. That is the same distance scaling as the legacy Coulomb force law F1 or 2 after one calibration that maps RSI ledger scale to the overlay units. The attraction or repulsion sign is carried by the overlay input, charge sign, and orientation, not by the shell geometry carrier. If I want a legacy potential energy statement, I recover it by integrating that force along a path, which produces the familiar UR1R behavior. I keep these facts separated because mixing them is one of the easiest ways to misread what EQ1 is doing. 7.9.3 Flagship C, Strong Overlay EQ. 11 Exception. The strong overlay is the harshest structural test because it is where many unified narratives collapse into hand-waving. RSI has a doctrinal constraint here. EQ. 11 is the one allowed place where an explicit R2 factor appears outside AP. That is not a casual feature. It is the strong overlay signature, and it must carry its weight. Minimum checklist. Use EQ. 11. Only as the explicit exception. I do not allow myself to sprinkle extra strong specific geometry outside AP elsewhere. Binding curve structure. Reproduce the qualitative shape first. Why there is a stable band, why there is a saturation effect, and then move toward quantitative replication. Confinement bands show that confinement is a stability band phenomenon in RSI terms, not a mysterious force that turns on arbitrarily. Failure conditions. If I cannot reproduce binding structure without introducing multiple new constants, I fail calibration discipline. If the strong overlay cannot be expressed as a ledger overlay with explicit closure rules, RSI is not unified at the nuclear scale. 7.9.4 Flagship D, Weak Overlay Deterministic Decay Closure. The weak overlay tests the most controversial part of the RSI stance, determinism. Modern physics uses probabilistic language here for good reasons. RSI claims that the underlying gating is deterministic, and that probabilistic appearance is a coarse-grained readout of deterministic channel closure. Minimum checklist. Half-life scaling. Show that half-life families follow deterministic collapse channel closure logic, not arbitrary stochastic postulates. Beta decay family. Treat a beta decay family as a set of channels with closure constraints, and show that allowed versus forbidden decays correspond to orientation or channel closure constraints in RSI terms. Constant emergence posture. Show how something like a Fermi-style constant can emerge as a derived scale factor rather than as a primitive bolt-on. Failure conditions. If accurate weak rates require irreducible probability as a primitive, the core determinism claim fails. If I must introduce domain-specific hidden reservoirs to patch decay energetics, the ledger fails. 7.10 How to read legacy physics as overlays. If I present RSI as replacing legacy physics, I will fail to communicate. The point is not that Newton, Maxwell, quantum mechanics, or QFT were wrong. The point is that they are different overlay languages that describe stable regimes effectively, but they do not share a single solver skeleton. So my posture is a dictionary posture. I map legacy objects to RSI readouts. Here is the practical dictionary I use while doing real work. Force, legacy, gate pressure and closure gradients, RSI. In RSI, I do not start from a vector force as a primitive. I start from whether a configuration is resolved, S, and whether it is driven toward change, DC. What legacy calls force often becomes a convenient derivative or approximation of how these scalars change across the lattice. Field. Legacy. Distributed closure state on edges, RSI. A field is often a continuous encoding of how interactions propagate. In RSI, propagation is represented through lattice edges and the geometry carrier AP. The field description can still be used, but it is treated as an overlay description of closure distribution. Potential, legacy, integrated stability, bookkeeping, RSI. Potential energy is a useful accounting tool. RSI keeps accounting explicit. Through CN through which anchor mapping is in play, the point is not to ban potentials, it is to prevent them from becoming hidden reservoirs. Spacetime curvature, legacy GR, anchor plane mapping AP, plus stability pacing, RSI. In RSI, geometry is not curvature of time treated as primitive. It is the mapping that carries interface scaling. Relativistic readouts, redshift, dilation, lensing, are read as stability diagnostics across recursion layers with EQ, 9, providing the stability ratio posture. Wave function and probability, legacy QM, closure distribution, and coarse-grained readout, RSI. I do not deny that probabilistic language is effective. I claim it is a statistical summary of deterministic closure gating at the lattice level. The weak overlay is where this dictionary will be tested most aggressively. Particles and mediators, legacy, stable closure modes and carrier signatures, RSI. In RSI, what I call a particle is a stable resolved closure configuration of the ledger under a given overlay. What legacy calls exchange or mediation can be read as a change in closure allocation along edges. This dictionary posture does two things for me. First, it prevents me from overselling. I can use the mathematics of legacy physics as an overlay approximation when it is accurate, while still insisting on a deeper solver skeleton. Second, it makes failure legible. If a legacy description succeeds where RSI fails, I do not get to declare victory by reinterpretation. I have to explain why my solver posture failed, which tier it failed in, and whether the failure is a kill test or refinement opportunity. 7.11 What this part established. I stated an explicit RSI proof standard, reproducible checks, not rhetoric. I defined a tiered evidence hierarchy, hygiene, scaling reproduction, calibration reuse, cross-domain reuse, and explicit kill tests. I added implementation credibility. The Core 12 solver skeleton exists as an executable model that computes gates and closure outcomes under declared inputs, with explicit lists of what is implemented, what is tested, and what is pending. I defined calibration discipline as pinning overlay scale factors once, for example via SynSide AP, and reusing them broadly, while forbidding distance-dependent tuning of TOR D Part 8, gravity overlay, flagship replication, and orbital stability as 712. I committed to a minimum evidence suite, 4 flagship validations, gravity, EM, strong, weak, with clear success and failure conditions. I defined a dictionary posture for legacy physics. I interpret legacy equations as overlays on the RSI ledger rather than as opponents, and I clarified how this posture makes failure legible instead of deniable. Gravity flagship incoming. Part 8 begins the flagship suite with gravity. I will show how the inverse square family falls directly out of CEA, up under the shell mapping, how a single calibration pin can be reused across regimes, and how orbital stability becomes a verdict in the RSI solver posture rather than an integration-first inference problem. Part 8, gravity overlay, flagship replication, and orbital stability as a verdict. In Part 7, I committed to a proof stance. RSI earns trust by reproducible checks, calibration discipline, and cross-domain reuse. Part 8 is the first flagship validation. I am going to treat gravitation as an overlay on the same ledger and the same gates, and I am going to be explicit about what I calibrate and what I refuse to tune. I am not trying to erase Newton or GR. I am trying to explain why their tools work, what they are really measuring in RSI terms, and what RSI can decide earlier than a long integration first workflow when data are sparse. Terminology note: to prevent drift, in this book I treat an anchored identity as the primitive object. When I say a structure is a resolved identity, I mean it is an anchored identity whose interface passes the existence gate, S1, evaluated on the appropriate geometry carrier AP. I will sometimes say anchor for brevity, but the model object is always an anchored identity with an interface, not a point mass. This part has 5 deliverables. Surface, and then reuse it without inventing new knobs. 4. I show how gravitational redshift, time dilation, and lensing are read as stability shift diagnostics, Z, rather than as primitive metric curvature. 5. I say clearly what RSI can decide quickly in sparse data regimes that legacy practice often cannot decide without long observation arcs. 8.1 Gravity, in RSI, not a primitive force, a stability overlay. In legacy mechanics, gravity is introduced as a force field or as spacetime curvature. In RSI, I start from a different primitive. The configuration either holds as a resolved structure or it does not, and that verdict is decided by the ledger and the gates. So I define the gravitational overlay in RSI language as a discipline readout of the same objects I already have. Existence and present stability, S, EQ, 1. Evaluated on the correct geometry carrier AP. Change and force transition, DC, EQ, 5. Closed through the engine. When I care about rates, EQS, 6 to 7. Geometry dilution, carried only by AP, with the spherical mapping as the default shell regime, EQ, S4 AP of R, shift and timing observables, Z, EQ, 9, and its source observer form, EQ, 18, interpreted as stability shifts. That is the entire gravity overlay in RSI. There is no new gravitational primitive. What legacy calls gravitational field magnitude is, in RSI, a readout of how a stability ratio changes across a geometry carrier. What Legacy calls gravitational potential is, in RSI, a useful overlay on the anchored budget scale after calibration. What Legacy calls geodesic bending is, in RSI, propagation through a region where the stability ratio varies across the beam profile. A reader trained in Newton and GR will immediately ask where direction lives. My answer is the same as part 6. Direction is not denied, but it is an overlay product. In the gravity overlay, the simplest posture is that coupling is coherence positive. I do not need repulsion at this stage to obtain stable orbits and practical membership verdicts. So I treat gravitational coupling as sign consistent closure, and I keep the solver layer scalar first. 8.2 inverse square without a new postulate. The inverse square family is a perfect first flagship target because it is structural, not niche. If RSI cannot reproduce it without cheating, RSI is not doing what it claims. In RSI, the existence gate is EQ, 1, S equal to EA di P. In the spherical shell regime, the anchor plane is EQ, S4 AP of R, APR equal to 4pi R2 degrees Celsius. Now I say the key RSI sentence in a way a legacy-trained reader can audit. If the anchored budget EA relevant to the interaction is treated as fixed across shells in the regime of interest, then S decreases across shells only because AP increases, not because T decays with separation. I make the anti-drift point explicit because it is easy to slide back into legacy habit. In this gravity overlay, T is energy per RSU layer, and I do not let T inherit a separation dependence. If I report a distance trend, it must come from the interface geometry inside AP, shell, or inside an explicitly declared effective interface APF, corridor, or overlap pocket. Likewise, D remains a layer count, not a hidden coordinate that I quietly treat as a metric radius, algebraically, EA1. SR equal to APR. If the geometry is genuinely spherical in that regime, AP grows like shell area, so the stability ratio falls with the shell area. In legacy language, that looks like an inverse square decline. In RSI language, it is the existence ratio being evaluated on a growing geometry carrier. I repeat the anti-drift discipline because it is the heart of the unification program. I do not postulate an inverse square force law. I do not encode separation decay into T. I do not reinterpret DE as a metric distance. I put geometry inside AP, and inverse square behavior is what appears when AP is a shell mapping. 8.3 single pin calibration, Earth surface as the reference. Inverse square behavior alone does not earn trust because it is easy to reproduce if I am allowed to introduce a new constant for every case. The flagship requirement is stricter. One pin, then reuse. In the gravity overlay, the cleanest pin is the Earth surface regime. The reason is not that Earth is metaphysically special. The reason is that it is measured well, stable, and structurally simple for a first calibration. The baseline package contains a canonical normalization I treat as the Earth reference pin, EQ, S4 trace Earth, SERTH equal to, EAPR1 dot equal to. This is a modeling declaration. At the Earth reference boundary, I normalize the existence gate to threshold. Operationally, this gives me an immediate reuse statement, EA equal to APR, under the Earth pin. Then the stability ratio on any shell in the same spherical regime follows without inventing new parameters, SREA, APR equal to, APR. That is the core reuse move. It keeps geometry inside AP, and it keeps calibration pin to one reference configuration. Now I connect the RSI pin to a legacy pin so the reader can see exactly what I am doing. The baseline package provides a legacy correspondence for the per layer budget T in the Earth reference case, EQ, S4T, legacy, T equal to G Mr. It also provides the RSI expression for the same reference through the spherical mapping and the boundary condition, EQ, S4T Earth, T equal to 4pi2 rand C. Equating those is not a new law. It is the calibration tie between the RSI geometry conversion factor C and the legacy gravitational parameters. The result is already recorded as the Earth calibration for C, EQ, S4 degrees Celsius Earth, C equal to G M4pi3 rands. I emphasize the discipline. The pin is a reference configuration. The outcome is a conversion factor C that lives inside the geometry carrier AP. I do not create a new distance-dependent coupling. I reuse the same solver structure, and only identity parameters change when the reference anchor changes. The baseline also includes the general reference statement, EQ, S4G cal, which is the cleanest one-line dictionary between RSI and legacy gravity at a chosen reference boundary. 4pi R2 ref C equal to GMref.ref. This is why I call C a calibrated constant. It is a mapping coefficient inside the geometry carrier, pinned once, then reused. I am not claiming that G varies or that nature updates constants. I am saying constants that appear fundamental in overlay language can be treated as pin translation coefficients between RSI and SI reporting. I keep the posture strict. A calibrated mapping coefficient is not a tuning knob. If I ever feel the temptation to fix a mismatch by changing C for a second case in the same regime, I treat that as a failure signal. Either I have crossed into a different regime that deserves its own pin, or I have chosen the wrong interface, shell versus corridor, or I have misallocated partners by hand instead of using multi-anchor closure, EQ, 10. In other words, constants should fall out as consequences of a mapping choice, then remain pinned while I reuse the same solver posture. 8.4 minimal worked reuse from Earth surface to an orbit regime. Now I do the simplest reuse demonstration that most readers understand, a satellite at altitude. Under the Earth pin, the shell evaluated stability ratio is SR equal to APR. This is already enough to say the key physical fact. Near Earth orbit is not zero gravity, the stability ratio on a nearby shell is still substantial. Weightlessness comes from the absence of a support edge, not from the absence of gravitational closure. That sentence is one of the best sanity checks for whether I'm using RSI correctly. RSI lets me keep the ledger statement separate from the contact statement. Gravity is not weight. Weight is a contact edge and a closure pattern in the local lattice. When that edge is removed, the system transitions along the solved stability gradients. A legacy trained reader can still use the familiar acceleration overlay to build intuition, but I keep it strictly as an overlay report, not as a primitive. 8.5 arrows after solve, recovering the Newtonian vector picture without making it primitive. Part 6, establish the posture. But gravity is where most readers want to see it made concrete. How do I get the familiar inward arrows without treating the arrows as the foundation? The RSI answer is simple. I do not begin with a vector force field. I begin with a scalar stability distribution. Then I draw arrows as a visualization of how that scalar changes across context. A clean overlay function is the logarithmic terrain built from S, phys x, ln S, x, where x is whatever context coordinate system I am using, physical space in a simple shell regime, or configuration variables in a multi-body regime. Then I define the arrow overlay direction as the direction of steepest decrease in this terrain. Goverlay x, phys x equal to ln S, x. I call these arrows directionality indicators, verdict arrows. In legacy notation, they are naturally represented as vectors, because vectors are an efficient overlay for direction and magnitude. In RSI, they are not primitives. They are reporting objects constructed from an already computed scalar stability map. If I am working in a discrete RSU picture, or a corridor geometry, where a smooth chart is not honest, I compute these indicators by finite differences across sampled interfaces instead of analytic derivatives. This equation is an overlay definition, not a new RSI axiom. It says once I have computed S across a neighborhood, I can map where the system will tend to go by pointing arrows in the direction of increasing admitted stability. In a spherical shell regime, that arrow picture points inward toward smaller shell interfaces because AP grows outward and therefore S falls outward for a fixed anchored budget. In practice, I often compute these arrows by finite differences rather than by analytic gradients because RSI is naturally discrete in its layer counting and because corridor geometry makes smooth analytic pictures less honest than sample pictures. This is the sense in which I say the arrows come after the solve. The scalar gate verdict is computed first. The arrow picture is a map of what the scalar verdict already implies in a chosen coordinate chart. 8.6 Orbit stability without vector forces as primitives. Now I address the real flagship requirement, because it is the thing that motivated RSI in the first place. Orbital stability is not just a trajectory fit, it is a verdict about whether a configuration is a persistent system. A reader trained in celestial mechanics will object. Orbital motion is directional, and without vectors I cannot write angular momentum. I understand that objection. RSI does not deny angular momentum as a useful overlay. RSI claims angular momentum is not the primitive that defines the system. The system is defined by whether the lattice closes under the gates. Directionality enters after that as an overlay mapping on the solved structure. So I separate two questions legacy workflows often blur. Question 1. Is the object allocated to the system at all? This is membership. In RSI, membership is closure participation, not proximity. Question 2. If it is allocated, is the configuration stable or driven to change? This is stability and change gating, not just orbit fitting. In the gravitational domain, the most common failure mode is to treat the shell-evaluated field overlay as if it were the binding interface. That is not what RSI does. 8.6.1 Shell overlay versus binding interface. The shell mapping APR equal to 4 per 2 degrees Celsius is a geometry carrier for isotropic dilution. It is the correct object when I want to talk about field-like readouts such as stability per interface as a function of shell. That is why it reproduces inverse square overlays cleanly. But system membership between two discrete anchors is not the whole shell, it is a coupling relationship between two identities. In RSI language, that coupling. Part 8, gravity overlay, flagship replication, and orbital stability as a verdict, is often corridor-like, meaning the effective interface for the edge is not the full shell but an overlap pocket that actually mediates coupling for that pair. So for orbital membership and stability, I use a disciplined workflow. 1. I treat the gravitational shell readout as an overlay map, not the binding edge. 2. I model the binding edge between two bodies using an effective coupling interface APA that reflects the actual overlap pocket of the two anchors in the regime. 3. I evaluate existence for that edge using C, AP. 4. I evaluate change for that edge using DEP-EA closing through the engine if I need a pacing claim. 5. I allocate membership and stability as verdicts, then I translate to legacy, orbital elements if I want a trajectory overlay. At this point I can state a practical gravity verdict that is often left implicit in legacy workflows. Membership has a boundary. In RSI I do not define that. Boundary by rhetoric about sphere of influence, and I do not define it only by fitting longer arcs. I define it by multi-anchor closure and allocation. Concretely, for a candidate intruder I build the closure sum, EQ, 10, under competing system hypotheses, and I rate out each partner's ledger share, for example via the allocation fraction F in EQ, for pesos ledger share. The membership boundary is the transition between negligible share and persistent share across justified geometry choices. This is exactly the point of the macro adjudication benchmark from part 5, and it is why I pair it with a unit coherence check. Before I argue about trajectories, I first verify that I'm comparing like with like, tension to tension, ratios to ratios, and that I have not smuggled geometry into T or DG. Once the closure allocation is explicit, I can decide much earlier whether I am looking at a member, a transient corridor pass-through, or a forced transition case. I do not pretend the exact geometry of a par is trivial. It is part of the real modeling work. The important thing in this flagship chapter is the discipline, Geometry lives in the interface, so if I need a refined binding interface, I refine the interface. I do not change T with separation. 8.6.2 A conceptual walkthrough, stable orbit, unbound fly-through, and forced transition. I keep the walkthrough at the verdict level, because the point here is what RSI can decide before a long integration becomes decisive. Case A, stable orbit, member, persistent. A stable orbit is a persistent lattice that includes an edge between the bodies that remains resolved and does not push the change gate past threshold. Operationally, the binding edge has an admitted existence state when evaluated on the correct APF. The change ratio DC for the relevant subconfiguration remains in a stable band. Multi-anchor closure, EQ 10, allocates the body as a non-negligible participant rather than a transient perturbation. In this regime, it makes sense to draw arrows and to use legacy orbital elements because the underlying structure is persistent. The orbit is not a guess path, it is a map of a solved stable structure. Case B, unbound fly-through, non-member. A fly-through can perturb trajectories. It can exchange energy in the legacy sense. But in RSI, the key is that it does not become a closure participant in a stable lattice. In this case, the interaction may exist as a transient corridor overlap, but it does not produce a persistent admitted binding edge under a justified APF. The body remains negligible in closure allocation. Any apparent orbit-like behavior over a short observational arc is classified as a data limitation, not as membership. Case C, forced transition, intruder-driven reroute. This is the case where a member system is pushed toward threshold by a new body or by a changing environment. In RSI language, forced transition appears as a gate approach. Either an existence threshold is approached because the effective interface requirement in APF no longer matches the anchored budget in the present configuration, or a change threshold is approached because DC rises toward collapse in the relevant subconfiguration, and closure allocation reroutes, meaning partner terms in EQ 10, shift in dominance. Legacy language calls this chaos, instability, or resonance crossing. RSI calls it what it is structurally, crossing a stability boundary in the lattice. 8.7 Everyday gravity examples, Apple, tides, satellites. Run 8 is required to include everyday examples because this is where readers decide whether RSI is a real physical picture or a pretty algebraic story. I am going to do 3, Apple fall, tides, and satellites. Each one uses the same grammar, lattice, interfaces, gates, and overlays. 8.71 Example 1, why an apple falls and why weight is not gravity. People ask, why does the apple fall? In legacy language, the answer is a gravitational acceleration. RSI does not deny the measurement. RSI changes the order of explanation. Configuration A, apple supported. When the apple is attached to the tree, there is a strong contact edge between the apple and the tree. That edge is an effective interface with its own closure participation. The configuration apple held up is admitted because the local lattice includes support edges that close. Configuration B, support edge removed. When the stem breaks, I remove a support edge from the lattice. That is not a small perturbation. It is a structural change. The configuration apple with no support edge is a different lattice. In that lattice, gravity is still present as a stability environment, but the previous closure pathway that held the apple in place is gone. Solver verdict and arrow overlay. In that unsupported lattice, the admitted persistent configuration is not the apple suspended at altitude. The system is driven toward a new admitted configuration, the apple on the ground, where new contact edges exist and closure is satisfied again. The arrow picture comes after I state that solver verdict. I can draw arrows derived from S gradients, section 8.5, and see an inward tendency in a shell regime. That inward arrow is not the cause. It is a map of the already solved stability gradient. This example is also where I make a practical correction to a very common confusion. Weight is not gravity. Weight is a contact closure readout. Gravity is the stability environment that becomes obvious when support edges are absent. 8.7.2. Example 2, tides is a differential stability gradient across an extended body. Tides are one of the best everyday demonstrations that gravity is not merely a pull toward a point. Tides are a differential effect across an extended body. In legacy language, the tidal effect is the difference in gravitational influence across the near side and far side of Earth. In RSI language, I say the same thing, but with the solver grammar. The Earth is an extended resolved identity, meaning it has an interface and an internal closure structure. The moon and the sun are external anchors that contribute to Earth's closure environment. The stability ratio environment is not uniform across the Earth body relative to those external anchors, so different regions of the Earth sample different effective stability conditions. That non-uniformity is the entire reason tides exist. The ocean is not responding to the moon pulling water. The ocean is responding to differential closure pressure across a coupled, rotating, elastic system. The lattice posture also clarifies the multi-anchor aspect. Tides are not a two-body story. They are a multi-anchor allocation story. In closure language, EQ 10, the moon has a small but non-zero ledger share in Earth's closure, and the sun has a ledger share as well. The measured tidal pattern is a readout of those shares plus the geometric arrangement that controls which interfaces are active at a given time. This is a good place to remember the Part 3 discipline. If I want to model the tidal coupling precisely, I must choose the correct effective interfaces. A full shell interface is often the wrong carrier for tides, because tides are inherently about differential coupling and restricted overlap geometry, not uniform coupling across a whole shell. 8.7.3. Example 3, satellites, freefall, and why GPS corrections are a stability measurement. Now I return to satellites, because they tie together three ideas in one familiar package: orbit as persistent membership, weightlessness as contact edge absence, and time dilation as a stability shift observable. Weightlessness in orbit. Astronauts in orbit are in free fall. They feel weightless not because gravity is absent, but because the support edges that create contact forces are not present. RSI says the same thing in its own grammar. The configuration person supported by ground has strong contact edges. The configuration person in orbit does not. Both configurations exist inside a gravitational stability environment. Orbit as a solved lattice. A stable orbit is a solved lattice verdict. Membership and stability are decided by whether the relevant edges are resolved and whether the change gate remains in a stable band. Once that verdict is made, drawing orbital curves in a coordinate chart is an overlay report. GPS is a stability shift measurement. GPS works only because timing corrections are applied. Legacy physics explains that with special relativity and gravitational time dilation in GR. RSI does not need to deny those. RSI says, the timing correction is exactly the kind of empirical measurement that a stability shift diagnostic Z is designed to encode, EQ9 and EQ18. The empirical program then becomes, after a single calibration pin, does the stability shift readout match the observed timing offsets in the Earth to satellite regime without additional tuning? 8.8 What RSI can decide quickly in sparse data regimes. Now I state the practical claim in plain language. RSI is not only an interpretation of gravity. RSI is a workflow change. In sparse data regimes, 3 problems recur in astronomy. 1. I do not have a long enough arc to decide whether an object is bound or unbound by trajectory fitting alone. RSI provides 3 corresponding advantages, and they are consequences of the solver posture, not new force laws. Advantage 1, membership is a closure verdict, not a trajectory guess. In RSI, membership is defined by whether a body participates materially in multi-anchor closure while the lattice remains admitted and stable. That is a scalar verdict. It can be tested under competing system hypotheses, even when the observational arc is short. Advantage 2, geometry errors become the first suspect, not new physics. If a configuration is near threshold, shell versus corridor selection can be the difference between fails and holds. RSI forces that geometry choice to be explicit, so I can test whether an anomaly is a geometry selection mismatch, wrong interface, rather than evidence for a new body or a new law. Advantage 3, stability boundaries give early warning signals. In a stable lattice, closure shares are stable. When closure share distributions drift or reroute, RSI treats that as a structural warning. It tells me which partner term is rising, which corridor might be turning on, and where a forced transition is likely to occur. This is the RSI version of an easy win target. It tells me where to look for falsifiable predictions, specific systems where a membership verdict or stability boundary predicts a measurable reconfiguration signature. 8.9% gravitational redshift and time dilation as Z diagnosed ticks. GR treats gravitational redshift and time dilation as consequences of metric structure. RSI treats the same class of phenomena as a scalar shift in the stability ratio. The canonical observable is EQ, 9, Z equal to SS. When I want to be explicit about source and observer, I use the source-observer form, EQ, 18, SOBs, source Z equal to S source. This is already enough to state the key interpretive sentence. A measured redshift or timing shift is a fractional change in the stability ratio between the emission environment and the observation environment. 2 named diagnostic classes matter here because they are clean, repeatable, and already embedded in how modern physics is operationally done. I, the Pound-Rebka Tower redshift measurement class, and 2, the GPS satellite clock offset regime. In RSI, I treat both as Z readouts between 2 stability environments. I do not do a full derivation in this intro chapter. The flagship claim is narrower and more testable. Once the Earth pin is declared, section 8.3, I can compute SOBs and source on the appropriate AP, carriers, shell, or justified effective corridor interface, and then I can report the implied fractional timing or frequency shift using the measurement mapping appropriate to the device and regime. The point is not to invent a new redshift formula, it is to store the observable in the same stability object that already reproduces inverse square behavior. Now I connect this to the gravity overlay. In a shell regime, when EA is treated as fixed across the compared shells, I have SR equal to EA, APR. So a shift between 2 environments is controlled by a ratio of interface carriers. That gives the operational use case. If I compare 2 clocks in 2 stability environments, their timing comparison is a measurement of the stability ratio difference. If I compare a photon emitted in one environment and observed in another, the frequency shift is a readout of the stability ratio change along the path. This is why I treat GR calculations as overlays. RSI does not need to deny GR where it is accurate. RSI changes the primitive I treat as fundamental. The primitive is not time curvature as an axiom. The primitive is a stability ratio shift on a ledger-defined geometry carrier. 8.10 lensing as a stability gradient effect. In GR, lensing is geodesic bending in a curve metric. In RSI, I describe the same phenomenon at the conceptual level as propagation through a region where S varies across the beam profile. I do not treat a photon as pulled by a force. I treat a beam as sampling a stability environment. If the stability ratio is not uniform across the transverse profile, then different portions of the wavefront experience different stability conditions. That produces an effective bending, in the same structural sense that a refractive index gradient bends light in optics. This is also where part 6 becomes practical. Once I have a solved scalar stability distribution, I can construct error overlays from gradients, section 8.5. Lensing is a transverse gradient phenomenon. It is sensitive to how stability varies sideways across the beam, not only along the beam direction. In this part, I'm keeping lensing at the interpretive and diagnostic level. The flagship requirement here is not to rebuild all of GR lensing. The flagship requirement is that the same stability objects that reproduce inverse square families also provide a natural place to store and interpret redshift and lensing observables, namely Zan stability gradients. 8.1. What this part established. I treated gravity as an RSI overlay, meaning I did not add a gravitational primitive beyond the ledger and gate structure. I recovered inverse square behavior by evaluating S equal to EA, AP, on the spherical anchor plane AP, R equal to 4 per 2 degrees Celsius with geometry confined to AP. I implemented a single calibration pin at the Earth surface using the baseline normalization SERth equal to 1 EQ, S4 stress Earth, and the recorded calibration relations for C EQS, S4T Earth to S4 degrees Celsius Earth. I gave a clean reuse statement from Earth's surface to an orbit regime entirely in AP ratios, and I clarified that weightlessness is a contact edge fact, not a no-gravity fact. I made the arrows after solved posture concrete by showing how the familiar inward gravity arrows can be built as an overlay from a solved scalar stability map, without treating vectors as primitives. I expanded the everyday picture with 3 examples: apple, tides, satellites, each written in the same lattice and gate grammar. I mapped gravitational redshift, time dilation, and lensing to Z diagnostics and stability gradients, using the canonical Z definition in its source observer form. 8.1. 2. Moving into electromagnetism. Part 9 moves to electromagnetism. The inverse square geometry story should carry over directly, and the new feature will be sign, attraction versus repulsion, encoded through the allowed scalar orientation gate theta in the engine enclosure sums. I will include at least 2 laboratory scale examples, static charge and conductor shielding, because I want the reader to be able to imagine a bench experiment, not only a cosmic test. 9. Part 9. Electromagnetism is signed closure on the same ledger. Part 8 ended with a promise: the inverse square story should carry over, and the new feature in this part will be sign. That is exactly what I am going to do here. Because I'm going to use legacy words like charge, electric field, and voltage in this chapter, I pin the translation posture up front. In RSI, the primitives remain the ledger carriers EA, EF, and the geometry carrier AP, evaluated by the existence gate S, EQ, 1, and the change gate DC, EQ, 5. Charge is not a fourth primitive. It is a legacy label for an orientation state of an anchored identity that shows up as a signed partner factor TH on the relevant edges of the system lattice. In the flagship list I set out in Part 7, this chapter's flag should be the electromagnetic overlay. I show that the same ledger that reproduced gravity can also reproduce attraction, repulsion, and screening once I allow sign closure. In legacy physics, electromagnetism feels like a different kind of mathematics than gravity because it is vector-rich. We start with charges, we build fields E and B, and we often use potentials as a gauge bookkeeping layer. In RSI, I keep the solver posture scalar. I do not erase direction from the world, but I refuse to make direction the primitive that decides whether a system holds. I push what legacy treats as vector content into the 2 locations that RSI doctrine already sanctions. Geometry lives in AP and nowhere else. Sign and coherence live in the orientation factor CH, and it appears only inside the engine enclosure rules that already permit it, not as a new ad hoc bolt-on. That is the whole move. Once I do that cleanly, I can translate Coulomb scaling, screening, and the basic quantization posture into the same ledger language I use for gravity, without smuggling distance dependence into T and without inventing negative hidden reservoirs. This part is a flagship overlay chapter, but I keep the contract from Part 7. I will not pretend I have rebuilt Maxwell in full detail inside an intro. What I will do is more foundational and more falsifiable. I will show that I can keep the Core 12 solver intact while explaining the most obvious EM facts that every educated reader already trusts: inverse square scaling in vacuum regimes, attraction and repulsion as a sign effect, superposition as a closure sum, screening and shielding as a cancellation and reallocation phenomenon, and discrete charge outcomes as natural, under-accounted identity posture. Then I will anchor it with 3 bench scale examples, because this is where most unified narratives die. If I cannot tell a clean conductor story, a clean static charge story, and a clean circuit story without drifting, then I am not building a real solver grammar. 9.1 Electromagnetism as signed closure on the same ledger, theta, gravity, as I used it in Part 8, is monotone in the sense that it does not present me with a basic choice between attraction and repulsion at the level of the primitive solver. I can do a lot of work with S equal to EA, AP, EQ, 1, and the change gate DC equal to EF, EA, EQ, 5, without needing a sign bit in the coupling. Electromagnetism forces the sign issue immediately. If I put 2 like charges near each other, the system does not try to close by binding. It tries to close by moving apart. If I put opposite charges near each other, the system does try to close by binding. In legacy language, that is the sign of Q1, Q2 in Coulomb's law. In Maxwell language, it is encoded in the direction of the electric field and the way that field couples to a test charge. In RSI, I refuse to solve this by introducing a new primitive vector field. I solve it by using the scalar orientation factor TH in the places where the Core 12 already permits orientation and handedness to regulate closure. Concretely, theta appears inside the engine sum, EQ, 6, K equal to P, KCH theta DC, and the multi-anchor closure allocation rule, EQ, 10, EA equal to P, Q theta DC. I keep 4 non-negotiable rules here because M is where drift is easiest. Theta is not a geometry object. It does not live in AP, and it does not depend on radius. If I make theta quietly decay with separation, I have drifted. Theta is not a second force law. It is a sign and coherence regulator on partner contributions inside the engine and the closure allocation rule. The ledger stays explicit and positive. I do not introduce negative energy as the explanation of repulsion. Repulsion is a closure outcome under a signed coupling factor, not a violation of ledger positivity. The ledger remains SE equal to EF plus EA EQ 4. Legacy. Electrostatic potential energy language is an overlay convention. It depends on a chosen zero. In RSI, I do not treat negative potentials as physical reservoirs. I keep the explicit positive ledger SE equal to EF plus EA and use sign closure to describe attraction or repulsion outcomes. A simple translation sentence for a legacy reader is: in RSI, electromagnetism is what you get when the same stability ledger is evaluated on the same geometry carrier, but partner contributions are allowed to flip sign and coherence through TH. This is also where I restate what I mean by scalar first without sounding evasive. I am not claiming the world has no directional structure. I am claiming that the verdict problem, does it hold, does it change, can be decided with scalar gates and scalar closure. Once the verdict is computed, I am free to translate the behavior into legacy vector language. In practice, that translation is how RSI earns trust. I keep the legacy tool where it works, but I change what I treat as primitive. Legacy vectors are not fake in RSI. A legacy vector encodes directionality and magnitude as an overlay representation of a scalar imbalance, expressed in a chosen coordinate chart. My solve loop stays scalar first, I compute gate values and ledger allocation, then I draw directionality indicators, verdict arrows, as a reporting layer, so a reader can recognize the familiar E, B, or force vector diagrams without mistaking those diagrams for the primitive mechanism. A practical note about the range of theta. In the simplest sign closure story, it is convenient to think of theta as 1. In real material regimes, coherence and orientation are not binary. A better mental model is theta 1, 1, where the sign encodes orientation and the magnitude encodes coherence of the relevant coupling channel under the engine. This lets RSI host cancellation, screening, and suppress coupling without inventing new primitives. 9.2 Coulomb overlay, inverse square from geometry, sign from theta. The Coulomb law is the electromagnetic sibling of the Newtonian inverse square story. It weakens with separation like an inverse square. It can attract or repel depending on sign. It superposes, and that superposition is empirically real. RSI's move is to keep the inverse square behavior in the same place I kept it for gravity, namely inside AP, and to keep the sign behavior in the same place I already sanctioned for orientation, namely inside TH. Distance scaling is always AP, never tension decay. I repeat the anti-drift sentence in the EM context because this is where people, including me, are most tempted to slide into field intuition and lose the ledger discipline. If an EM interaction looks weaker with separation, I do not let that drift into T is thinning, or the ledger decays. In RSI, separation like dilution lives in AP and only in AP. So in a spherical interface regime, I evaluate the same existence gate I used everywhere else, EQ, 1, EAS equal to AP. If I increase the interface scale in the shell regime, AP increases, and the same EA yields a smaller S. That is the RSI meaning of inverse square weakening, whether I'm talking about gravity or Coulomb. A one-line shell weakening derivation in RSI form. In a vacuum shell regime, I can write the spherical interface as APR equal to 4pi-R2CEM. Holding EA fixed for the source anchored identity on that shell, I have EAS R equal to APR 4pi-R2CEM. As R increases, the geometry carrier grows as R2 inside AP, so the same anchored budget produces a smaller resolution state readout at larger shells. That is the Coulomb weakening story in RSI language, stated without introducing any new field substance. A missing but decisive example. Why a long wire is not inverse square. A common drift error is to treat every EM interaction as spherical. A long straight wire does not produce a spherical interface in the region where the wire length is the dominant scale. In that regime, the natural geometry carrier is closer to a cylinder around the wire, so I model the relevant interface as AP wire R equal to 2pi-R LCEM for an effective participating length L of the wire segment. The RSI readout is still S equal to EA AP wire R, but now the interface grows linearly with R because the geometry is cylindrical. The apparent fall-off law changed because I changed the interface, not because I changed T, and not because I introduced a different field law. Parallel plates preview. Why some EM regions look approximately uniform. Between large parallel plates, the operative interface is an overlap pocket whose area is close to the plate area across much of the gap. In RSI language, that is just a corridor selection statement. The geometry carrier does not have to grow like a spherical shell in every configuration. Calibration posture parallels part 8. In legacy EM, the coupling scale is summarized by constants like K equal to 1, 4 pi epsilon 0, and in matter it is modified by permittivity and polarization. In RSI, I do not treat those as separate metaphysical objects. I treat them as calibration pins that live inside the geometry carrier and inside the effective interface participation, exactly the way part 8 treated gravity calibration. To keep the language concrete without adding new numbered equations, I use a simple notation. APR equal to 4pi-R2CEM, where CEM is a calibrated mapping coefficient for the EM overlay in the regime I am testing. The precise numerical value is pinned by a reference configuration, then reused. In vacuum psi language, this is where the role of E0 appears as a translation factor between RSI ledger language and SI force language. I am explicit about what I am and am not claiming here. I'm not claiming that E0 or any SI defining constant physically varies. I'm claiming that when I translate RSI ledger quantities, energies, and gate readouts on interfaces into the SI overlay that reports forces and fields, a calibrated mapping coefficient appears. I pin that mapping once per stated regime and reuse it. It is not an arbitrary tuning knob, and it is not an extra primitive added to RSI. The discipline is what matters for unification. I am allowed to pin scale once, but I'm not allowed to introduce a new knob for every new charge configuration. Attraction versus repulsion is the gate, not negative ledger. The new content in electromagnetism is that the interaction can be attractive or repulsive. In RSI, I encode that by allowing a sign and coherence factor in partner contributions regulated by 6 in the places already sanctioned by the core 12, namely the engine and the multi-anchor closure. A legacy reader can think of this as a translation layer, not as a new primitive 0, EM, R+1, unlike charges, closure reinforcing in the simplest posture. -1, like charges, closure opposing in the simplest posture. I am deliberately not claiming that this two-line map is the full microscopic story. The microscopic story is whatever the engine inputs really are, and RSI's philosophical commitment is that those inputs are deterministic even if I do not know them yet. What I am claiming is that the solver posture has a clean place to put sign without breaking the ledger, and without inventing an electromagnetic field as a new primitive substance. Superposition is already in the closure rules. The fact that EM superposes is not a puzzle for RSI. It is exactly what a closure sum does. When multiple partners contribute, I do not hand split anything. I write the partner sum, EQ, 10, and let each term carry its own Q magnitude and 6 orientation, EA equal to QOD. In a static regime, many of those D contributions are stable, and the sum is simply the closure accounting. The legacy experience of fields AD is the continuum overlay of closure. Terms add, why M is screenable, but gravity is not. The sign structure also explains one of the most basic empirical differences between EM and gravity. M can cancel locally because matter can contain both signs of charge, while gravity does not present a bulk population of negative mass that cancels ordinary mass. In the lattice picture, part 4, I interpret this as a closure fact. In a chunk of neutral matter, the internal lattice contains many charge-bearing identities of opposite orientation. When I evaluate multi-anchor closure with 6, partner contributions can cancel strongly in the interior. That produces a macroscopic outcome that legacy language summarizes as the external field is small or the interior is shielded. In RSI language, it is simply net sign closure at large scales can be small even if the internal ledger is large, because partner contributions carry and can cancel. This is exactly what I need if I want a single solver that still respects the fact that we do not walk around feeling enormous electric forces all the time. It is not that the EM ledger is absent. It is that the lattice is typically close to locally closed under signed coupling, so the residual external closure is small. 9.3 Quantization posture, why discrete charge and discrete outcomes are natural in RSI. In part 2, I introduced the identity counting law, EQ, 8, as a non-negotiable posture. RSI is a finite recursion model, built from counted layers and explicit identities. The consequence is simple but profound. Ledger budgets are not infinitely divisible in the way we often pretend they are in continuous field intuition. They are built from discrete identity contributions U that are then organized across a counted RSU span DE. This posture makes electromagnetism feel less mysterious, not more. In legacy physics, we treat charge quantization as an empirical fact. Electrons have a fixed charge, protons have the opposite, and charge conservation appears exact in all ordinary regimes we test. In RSI, I do not need to add charge as quantized as a separate metaphysical statement. I treat it as a natural consequence of the same discrete bookkeeping posture that already underlies the ledger. Charge-bearing identities are counted, they are not a continuous substance. The sign of that charge is an orientation state, encoded by theta on relevant edges. Net charge at a boundary is a net imbalance in signed identity counts that cannot be locally canceled by lattice reallocation. This is not a proof of the electron charge value. It is a modeling stance that tells me why it is reasonable to look for an integer counting structure under charge. It also tells me why field lines are a useful legacy picture. They are a visualization of corridor bundles and closure routing, and those routes can be counted. A Gauss-style sentence in RSI language. A legacy experimentalist reaches for Gauss's law when they want a clean conceptual explanation. The flux through a surface equals the enclosed charge, up to E0. In RSI language, the same structural sentence becomes: the net sign closure that crosses an anchor plane is a counted boundary condition, and the geometry carrier AP is the only place where that boundary is diluted as the surface grows. I am not claiming I have derived Maxwell from the core 12 in this intro. I am showing that the solver has room to host the same structural logic, conserved count inside, geometry carrier at the interface, and a measurable external signature. Polarization and induced charge is lattice reallocation. Quantization posture also makes induced charge and polarization read naturally. When I bring a charge near a neutral object, the object can develop an induced dipole. In legacy language, charges within the object shift slightly, creating an internal polarization field. In RSI language, the object is a lattice with many internal anchors and corridors. The external charge perturbs boundary corridors. The lattice reallocates charge-bearing identities, a change-gate-mediated process. until the interior configuration satisfies the existence gate and the relevant closure conditions. The induced dipole is the new resolved configuration under the new boundary condition, expressed in a language that Legacy calls polarization. Why discrete outcomes are not automatically probabilistic. Legacy quantum language often equates discrete outcomes with intrinsic randomness. RSI does not. RSI's commitment is that discreteness is a counting and closure fact, while probabilities are a description of my ignorance about engine inputs and microstate variables. So if I see quantized charge, quantized photon emission, or discrete spectral lines, I treat them as signatures that the underlying closure transitions are discrete. I do not treat them as evidence that nature must roll dice. In RSI posture, the dice are my ignorance, not a primitive of reality. 9.4, a laboratory example, static charge, repulsion, and induced attraction. Now I do the first bench example explicitly. I want the reader to be able to imagine this without any special equipment, because that is where the theory either connects or it does not. Example A, two like charges repel until a new resolved configuration is reached. Take two small pith balls hanging from insulating threads. Charge them the same way so they carry the same sign. Legacy language, they repel by Coulomb's law until the repulsive force is balanced by the tension in the threads and gravity. RSI language, the same facts, but with the solver grammar. Step 1, declare the lattice and the relevant edges. I have two charged identities in the environment. The relevant edges are, in the strict RSI language of this book, each charged object is an anchored identity whose boundary carries a net signed EM orientation tag that will be expressed through theta on the relevant edges. The EM coupling edge between the two charges, shell-like at this bench scale if the geometry is roughly isotropic. The mechanical constraint edges, threads, gravity environment that act as other closure participants in the larger contextual system. Step 2, apply sign closure on the EM edge. Because the charges have the same sign, the EM orientation factor is closure opposing in the simplest posture, meaning TH less than 0 for that interaction channel. That does not create negative ledger. It creates a closure direction the system will reconfigure towards separation, because separation increases the shell interface and therefore dilutes the sign interaction per interface. Step 3, solve for the new resolved configuration under constraints. The system does not separate forever because it is constrained by the threads and by the gravity environment. A new resolved configuration exists where the EM edge is sufficiently diluted by the geometry carrier and the constraint edges carry the remaining closure. That equilibrium is the RSI meaning of repulsion stops. This example is important because it shows repulsion is not a mysterious negative energy well. It is a reconfiguration direction produced by sign closure under constraints. Example B, a charged balloon sticks to a neutral wall. Now take a charged balloon and bring it near a neutral wall. Legacy language, the wall polarizes, creating an induced dipole, and the balloon is attracted. RSI language, again, the same facts, but with the lattice logic explicit. Step 1. The wall is a dense lattice with mobile and bound identities. Even an insulator has internal corridors for small reallocation and polarization. A conductor has more. Either way, the wall is not a featureless object. It is a closure network. Step 2. Boundary corridors are perturbed. The charged balloon introduces new sign partner contributions at the wall boundary. The near side corridors of the wall are now under a new sign boundary condition. Step 3. The wall reallocates to a new resolved boundary state. Charge-bearing identities in the wall shift slightly. The near side develops an effective opposite orientation relative to the balloon, meaning the near side interaction channel becomes closure reinforcing. It's greater than 0 in the simplest posture. The far side becomes effectively like-oriented and closure opposing, but it is geometrically diluted because it is further away and therefore evaluated on a larger effective interface. The net outcome is attraction. In RSI language, it is not magic. It is a closure reallocation under a new boundary condition, with near side reinforcement dominating far side dilution because the geometry carrier is not symmetric across the extended wall. This is a direct EM analog of the tidal intuition from Part 8. Differential coupling across an extended body matters, and the sign gate determines whether the differential produces a net pull or a net push. 9.5, a laboratory example, conductor shielding as system reallocation. I now do the second bench example explicitly. Electrostatic shielding is clean because it has a crisp legacy statement, charges redistribute on a conductor until the electric field inside is 0. Here is the same phenomenon in RSI language expanded into a step-by-step lattice account. Step 0, identify the system and its boundary. A conductor is not a featureless blob in RSI. It is a dense internal lattice of anchors and corridors. The charge-bearing identities that move freely in a conductor are, in this posture, the identities whose reallocation is energetically cheap compared to reorganizing the heavier anchors. The first RSI move is always the same. I specify the relevant boundary. For shielding, the boundary that matters is the conductor surface. That surface defines the interface where the external perturbation meets the internal lattice, and it defines the geometry carrier I use when I evaluate existence and closure. Step 1. Apply external perturbation as a boundary condition. Bring an external charge near the conductor. In legacy language, the external charge creates an electric field that influences electrons in the conductor. In RSI language, I say something more operational. The external charge introduces new sign partner contributions at the boundary corridors, regulated by theta. Those boundary corridors are now out of their previous resolved configuration, meaning the local closure conditions and local existence readouts are perturbed. This rephrases the entire point. I do not need an electric field as a substance. I need a statement that the boundary conditions of closure have changed. Step 2. Allow reallocation in the internal lattice. A conductor is special precisely because it can reallocate charge-bearing identities easily. In RSI terms, the system has many internal corridors that permit fast redistribution of the identities that carry EM orientation, and the change gate routes that redistribution without requiring the heavy anchors to reorganize. So what happens next is not mysterious. Charge-bearing identities move through internal corridors. This movement changes which partner edges carry which sign contributions. The system reconfigures until the interior configuration satisfies the existence gate and the relevant closure conditions under the new boundary condition. Step 3. Interpret the equilibrium condition as field cancellation. In legacy terms, the equilibrium outcome is that the electric field inside a conductor is 0. In RSI terms, the equilibrium outcome is interior identity nodes see net sign closure contributions that sum to a resolved condition under the new boundary, so the interior has no forced reconfiguration path driven by the external perturbation. What legacy calls field cancellation is RSI's the lattice found a resolved configuration. The reason it appears inside the conductor is that the conductor's internal reallocation freedom makes it easy for the lattice to cancel signed contributions in the interior. The sign gate theta is the key. Without sign, you cannot cancel. With sign, cancellation is a natural closure outcome. Example C, Faraday cage, apertures, and the corridor leak intuition. A Faraday cage is a clean demonstration of signed reallocation. If I surround a region with a closed conducting shell, external static perturbations are handled at the shell boundary. In RSI language, the outer surface is the active boundary interface. The conductor reallocates charge-bearing identities on that boundary until the interior identity nodes see a near-zero net sign closure readout under the external condition. The useful edge case is a cage with holes. Holes are not a mystery in RSI. A hole admits corridor pockets that connect exterior and interior interfaces. If the apertures are small relative to the operative measurement scale, those corridor pockets have limited effective participation, a small APF share, and the interior remains approximately screened. If the apertures are large, the corridor participation grows and the interior no longer stays quiet. This is the same solver logic as open loop versus closed loop in circuits, applied to geometry rather than wiring. A practical note about time dependence and imperfect shielding. Real conductors are not perfect, and shielding is not instantaneous for time-varying fields. Legacy physics describes this with conductivity, skin depth, and Maxwell equations. RSI has a clean conceptual way to talk about the same facts without leaving the ledger posture. If the boundary condition changes slowly, the lattice can reallocate through internal corridors and maintain interior closure. If the boundary condition changes rapidly, the change gate and the engine are forced to handle a fast reconfiguration, and the interior cannot remain perfectly closed at all depths. I am not claiming this is a quantitative skin depth derivation. I am claiming something more basic. RSI has a natural place to store the difference between static shielding and dynamic penetration, namely in change gating and engine-mediated closure timescales, not in a new primitive substance. 9.6 A laboratory example, circuits, current, and Y voltage is a stability readout. Now I do the third bench example because it forces RSI to speak about dynamics without drifting into vector-first storytelling. Circuits are also a place where the system boundary question becomes obvious. A circuit is a declared system. It is either closed or it is not. That maps directly to RSI. Closed loop versus open loop is a lattice membership verdict. Consider a battery, a resistor, and a switch. Legacy language, when the switch is open, no current flows. When the switch is closed, current flows, the resistor heats, and energy is delivered. RSI language, the difference is not mystical. It is the presence or absence of a corridor edge. Open switch. When the switch is open, the loop is not a closed closure network. The relevant reallocation corridor is not admitted. The system cannot distribute charge-bearing identities around the loop to reach the same kind of resolved dynamic steady state. What happens instead is boundary accumulation. Charges pile up at the open gap, and a new local resolved configuration forms that prevents further reallocation. Legacy language describes this as a capacitive effect and an electric field across the gap. In RSI, I say the system found a static resolved configuration under an open boundary constraint. Closed switch. When the switch closes, a corridor path is admitted. Now the loop is a closure network. Charge-bearing identities can reallocate around the loop, and the system can reach a new resolved dynamic state. This is where the change gate becomes operational. Current in RSI is not a primitive substance. It is a rate of identity reallocation through a permitted corridor under a declared boundary condition. The engine, EQ6 and EQ7, is the correct place to store channel availability and coherence, resistors, capacitors, and inductors as different closure channels. Legacy circuit theory treats elements as constitutive relations. RSI treats them as different closure channel structures in the same ledger. Resistor. A resistor is a channel where reallocation occurs with strong dissipation into other microchannels. Legacy language calls this heating. RSI language says, the engine sum has strong channels that route reconfiguration into many internal degrees of freedom, so the dynamic closure is lossy. Capacitor. A capacitor is a boundary storage geometry. It is a configuration where charge identities are held at two opposing boundary interfaces. Legacy language says energy is stored in the electric field between plates. RSI language says the system holds anchored budget in a boundary configuration, and the effective interface between the plates is a strong coupling corridor whose geometry is explicit. This is also a clean reminder of the geometry doctrine. In a capacitor, the relevant interface is not a full sphere. It is an overlap pocket between plates. That means the correct carrier is an effective interface, APF, not the full shell. RSI forces me to say that explicitly, which is exactly what I want. Inductor. An inductor is a configuration where dynamic reallocation creates a persistent closure routing in a loop geometry. Legacy language says energy is stored in the magnetic field. RSI language says the engine closure has a channel structure that resists rapid change in the reallocation pattern, meaning the system has a dynamic persistence in its closure routing. Where magnetism lives in RSI, a reader will ask, where is B in this story? The answer is the same as part 6. B is an overlay map of a dynamic closure routing, not a new substance. When I do want a picture, I translate the scalar imbalance into directionality indicators, verdict arrows, and vector overlays. The vectors are still secondary. They are a human-readable rendering of the ledger outcome, not the object that makes the outcome happen. When charge-bearing identities move, the closure network is no longer static. The change gate in the engine become active, and the orientation factor CH is no longer only a static sign. It is a coherence gate on a moving reconfiguration channel. The legacy right-hand rule is a coordinate chart summary of how a moving reallocation channel threads a loop geometry. I do not need to ban B, and I do not need to declare it primitive. I treat it as an efficient after-action map of dynamic closure. This is the same logic as arrows after solve in gravity, but in EM, it shows up as a dynamic curl-like overlay rather than a static inward arrow. What voltage is in RSI language? Voltage is one of the most abused words in physics education. In legacy circuit language it is potential difference. In RSI, I treat it as a stability difference readout between two identity nodes in a declared boundary network. Said plainly, a voltage difference is an empirical report that the lattice is not in a uniform resolved state across two identity nodes, so reallocation is driven when a corridor is admitted between them. I do not need to deny potential language. I keep it as an overlay that is exceptionally useful for engineering. I only insist that the underlying solver is the closure ledger in the gates. 9.7 What electromagnetism adds to the system lattice picture. By the time I reach this part, I have already committed to a lattice picture. Identity nodes represent anchored identities, and I use identity node only in this graph mode sense, a node that represents an anchored identity, so I do not accidentally let generic graph language replace the physical term. Edges are coupling interfaces evaluated on the correct geometry carrier. Gravity taught me that inverse square overlays can be understood as a stability per geometry readout on a shell carrier, without weakening T. Electromagnetism adds one essential structural feature. Edges can carry sign partner contributions, and those contributions can cancel. That one sentence is why EM behaves so differently in daily life than gravity does. It is also why EM is a strong unification test for RSI. If RSI cannot host sign cancellation cleanly, then it is not a serious candidate for cross-domain reuse. Here's the minimal way I operationalize the EM overlay in the lattice posture, without introducing any new primitives. Which identity nodes carry net charge, and what sign? In RSI posture, that means I assign an orientation state that will determine the partner factor TH on relevant edges. 5. Adjudicate change. If the sign closure configuration cannot satisfy the gates, I do not call that a mysterious force. I evaluate whether the change gate DC EQ 5 forces a reconfiguration, and I route that reconfiguration through the engine posture EQ 6 to EQ 7. Once I have done those steps, I can translate the outcome into legacy language. I can talk about attraction, repulsion, polarization, shielding, and induction as convenient descriptions of which closure configuration the system selected. But the decision problem itself remains scalar. 9.8 What this part established. I treated electromagnetism as a signed overlay on the same RSI ledger, not as a new primitive field substance. I kept inverse square behavior in AP, exactly as in gravity. I did not let any separation dependence drift into T or DE. I treated attraction versus repulsion as a consequence of the scalar orientation factor, TH, inside the sanctioned engine and multi-anchor closure rules rather than as negative ledger accounting. I stated a quantization posture. Discrete charge and discrete outcomes are natural in RSI because the ledger is built from counted identities and counted RSU layers, EQ 8, while probabilities remain a description of unresolved engine inputs, not a primitive of reality. I added 3 concrete laboratory examples that a reader can visualize: static charge, repulsion and induced attraction, conductor shielding as identity reallocation, and circuits as closure networks where current is reallocation through admitted corridors. I made the overlay posture explicit. Legacy vectors are allowed as reporting layers, but the solver remains scalar first. I report imbalances as directionality indicators, verdict arrows, after the gate and allocation calculations are done. I strengthen the geometry selection story with 2 concrete EM interface reminders. A long wire is a cylindrical interface regime, and parallel plates are an overlap pocket regime. The fall-off law changes only because the interface changes, while geometry still stays inside the relevant AP. I added a Faraday cage discussion to show that shielding success and failure. Apertures can be read as corridor participation changes without inventing extra primitives. New equations introduced in this part? No. I used existing gate and closure posture and treated TH as an already defined orientation factor. 9.9 Moving to the strong domain. Part 10 moves to the strong domain. This is the one place where RSI canon permits an explicit 2 rands outside AP, and it matters because nuclear binding is short range and saturating, rather than long range and shell diluted. The purpose of the next part is to show that RSI can host that domain difference without breaking its own guardrails, One exception, explicitly labeled, used only where it is allowed, and then reused to explain binding structure and confinement bands without inventing a new set of free parameters. 10 Part 10, strong overlay, the 2 rands exception, and confinement bands. Part 9 ended by naming the strong domain as the stress test. This is the one place where RSI canon permits an explicit 2 rands outside AP, and the permission is not cosmetic. It is the mechanism that lets the same scalar ledger describe a short-range saturating nuclear scale binding regime without quietly rewriting the core rules. In this part I do 6 things, in the order I would do them in a real solve. 6. I do a minimal worked magnitude pin that is explicit and conservative, and I state how it should be extended in the Mathematica model later without pretending this chapter is that full build. Terminology note, identity language. Throughout this part, when I say identity, I mean an anchored identity, a resolved participant that, at the scale of, the discussion clears the existence gate as greater than or equal to 1 under the appropriate anchor plane. APF, when I say composite identity, I mean a bound nuclear configuration that the lattice treats as a single anchored identity for the purpose of closure bookkeeping in that regime. I am being explicit because nuclear language is where it is easiest to drift into mixing objects, particles, and fields, as if RSI did not care which is which. I am going to be very strict about anti-drift here. If I let the strong domain become an excuse to sprinkle extra geometry factors wherever I want, I will destroy the unification claim. The point of the strong overlay is that I can host a domain difference with one explicit, tightly confined exception and keep everything else unchanged. 10.1 Strong as explicit nuclear coupling. In legacy physics, the strong interaction is often introduced as something fundamentally distinct from gravity and electromagnetism, color charge, gluons, running couplings, confinement, lattice QCD, and a deep mathematical machinery that is extraordinarily successful and extraordinarily specialized. RSI does not deny the success of that machinery. RSI changes the primitive story. In RSI, the strong domain is not a new vector field, not a new probabilistic postulate, and not a separate energy reservoir. It is a particular closure regime of the same ledger where short-range binding appears as a high-density coupling across a very small separation interface. The canonical strong domain object is the nuclear coupling NC in EQ 11. In the intro stubs, it is written as EA de NC equal to 2 rands if equal to 2 rands. 10.1.1 YEQ 11 must be different early intuition. I flagged the 2 rands placement early in part 1, SEC 1.9, because readers will correctly ask why the strong overlay is allowed to look different. I also audit the rule formally in Appendix A9. Here I give the intuition right where the equation first appears. In RSI, I keep 2 geometric roles separate. Propagation carrier, shell style, for gravity and Coulomb. Separation shows up through the growth of the relevant anchor plane AP, full shell, or corridor effective pocket. In that posture, inverse square behavior is an after effect of 1 APR, not a claim that T decays with distance. Contact normalization, strong style, for nuclear binding, the decisive interface is a small separation surface between shells inside an admitted corridor. EQ 11 uses an explicit 2 rands to report a coupling density on that contact interface without redefining AP or weakening the geometry confinement doctrine. If I forced the strong overlay into the propagation carrier form, I would quietly misclassify a contact problem as a shell dilution problem. The first failure would be conceptual. I would no longer be able to say what interface the equation is describing. The second failure would be physical. I would manufacture a spurious long-range tail because I would have built shell growth into a regime that is supposed to saturate and shut off. This is why the exception strengthens RSI rather than weakening it. The R2 factor is a visible isolation marker that keeps geometry smuggling from spreading into the rest of the core 12. Every other distance or area effect stays inside AP, and the audit is simple. If I see an explicit R or R2 outside AP, anywhere else I know I drifted. 10.1.2 Strong domain prediction and test cards. Compact subset. I like to keep at least one small set of hard, public, pass, or fail targets close to the equation. This mini-table is deliberately short, but it captures the 2 headline observables I expect skeptical readers to ask about: the heavy element stability frontier and the onset of nuclear effects in Rutherford-style scattering. What this tells me about the interaction. The strong overlay is not a second copy of the gravity story with a different constant. It is a different interface class. When I treat it as contact normalization on a bounded corridor, saturation and short range become natural consequences of channel availability and gate admission, not extra postulates. The explicit 2 rands is therefore a strengthening move. It keeps the propagation carrier AP clean for existence in long-range overlays, while giving me a single auditable hook for nuclear contact geometry. I'm going to say what that means in plain language, and I'm going to say what it does not mean, what NC is. NC is the nuclear scale coupling density that binds nuclear identities when the configuration is admitted by the existence gate and not driven past threshold by the change gate. It is built from the same carriers used everywhere else. The anchored budget scale EA EQ 3 posture and the recursion span day EQ 2 posture combined into the field budget EF equal to TDE, and then expressed as a coupling density through the strong domain separation factor 2 rands. The single most important conceptual sentence is this: the strong overlay is not a new ledger. It is the same ledger evaluated in a contact scale regime where the coupling is concentrated onto an extremely small effective separation interface, and that concentration is what makes binding enormous in short range. What NC is not. NC is not a long-range inverse square field overlay that competes with gravity and electromagnetism in macroscopic space. The 2 rands in EQ11 is not the same object as the shell mapping in APR, equal to 4 per 2 degrees Celsius EQ S4 AP of R. The shell mapping is a geometry carrier for field-like dilution across a full interface. The strong coupling is a nuclear separation coupling law for a binding interface that is not a full 4p shell. This is why I keep saying the solve starts with the interface. If I treat the strong domain as if it were a shell field, I will misread it. It is a contact scale coupling channel, and that is the point, what R means operationally. I treat R in EQ11 as an effective RSU separation along the relevant nuclear binding interface between the composite identities that are coupling. It is not a casual center-to-center distance, and it is not a permission slip to insert bare geometric factors into other equations. Part 3 is where I made the shell versus corridor rule explicit, and the strong overlay lives in the corridor in contact posture. Said plainly, EQ11 is only meaningful when the system declaration is nuclear contact scale and the binding corridor is actually available. Magnitude law versus channel structure. Another strict RSI discipline applies here. EQ11 is a magnitude law. It does not carry theta. Attraction, exclusion, and any handedness or channel selection effects are routed through the engine enclosure rules. EQS 6, 7, and 10, not through ad hoc sign edits in EQ11. That keeps the strong overlay from becoming a place where I cheat. So my posture is, use EQ11 for the nuclear coupling magnitude. Use the existence and change gates, EQs 1 and 5, to decide whether the configuration holds or must change. Use the engine and multi-anchor closure, EQs 6, 7, and 10, to handle channel structure, orientation, and multi-body allocation. That is how I keep the strong overlay inside the same solver skeleton. 10.2. 2 legacy meanings of strong and the single RSI posture. Legacy physics uses the word strong in 2 closely related but distinct ways. QCD strong, the fundamental color interaction and the confinement of quarks and gluons into hadrons. Residual nuclear strong, the effective binding between hadrons, especially nucleons, that holds nuclei together. RSI does not need a different ontology for these. Declaration and a clean interface declaration. It needs a clean system. Residual nuclear binding in RSI. This is the regime I am primarily modeling in this intro because it is the cleanest bridge to macroscopic physics and because it is where the binding curve language lives. EQ11 is the magnitude law for that coupling density when the nuclear binding corridor is available. QCD confinement in RSI. At the quark level, the claim is not that EQ11 alone magically becomes the standard model. The RSI claim is narrower and more structural. If a free quark configuration is not an admitted stable identity under the existence gate and the change gate, then the lattice will not persist in that form. It will reallocate into admitted hadronic identities once a threshold is reached. This is confinement as a gate and threshold statement, not as a probabilistic miracle. The detailed channel structure that Legacy describes with gauge fields is, in RSI language, an engine problem, what channels exist, what coherence they have, and what orientation constraints they enforce. Those are the things K, KCH, and theta are meant to host, but I'm not pretending this intro chapter is a full engine build. The point is that both meanings of strong are compatible with a single RSI posture. Declare the identity, declare the interface, compute the gates, then interpret the admitted band as binding and the threshold-driven reallocation as confinement or string breaking. 10 free the 1-2 rands exception, and why it is tightly confined. RSI has a geometry doctrine. All distance and area scaling belongs inside AP, and I do not sprinkle extra R or R2 factors outside the anchor plane to patch a mismatch. That doctrine is exactly what keeps RSI from drifting into disguised legacy physics. So the obvious question is, why allow 2 rands outside AP at all? The RSI answer is not because strong needs it. The RSI answer is structural. Gravity and Coulomb are field-like overlays because their dominant geometry carrier is the anchor plane AP, and in the spherical regime that carrier grows without bound. Nuclear binding is not field-like in that way. It is a contact scale coupling channel. EQ11 is the one canonical location where the solver is allowed to represent that contact scale concentration explicitly without redefining the primitives. 10.3.1 Propagation carrier versus contact normalization. I keep 2 geometric roles separate because confusing them produces exactly the wrong behavior. Propagation carrier, shell style, in gravity and in the Coulomb overlay, separation shows up through the growth of the relevant anchor plane AP, full shell or effective corridor. The inverse square behavior is a statement about how a fixed anchored budget is distributed over a growing interface, not a statement about T decaying with distance. Contact normalization, strong style, in the strong overlay, EQ11, uses 2 rands to convert a local field budget into a coupling density on a contact scale binding interface. This is a normalization on an interface that does not act like a propagating shell, and it is meaningful only inside the admitted nuclear contact band. If I were to absorb 2 rands into an effective anchor plane, and then reuse that object as if it were the propagation carrier, 2 bad things happen at once. First, S equal to EAP would inherit a spurious long-range dilution story, and the strong overlay would grow a tail that it is not supposed to have. Second, I would lose the regime separation that makes the core 12 unification legible AP would no longer mean the geometry carrier for existence and propagation. It would secretly mean whatever I needed to normalize a hard domain. So I keep 2 rands outside AP, in exactly one place, EQ, 11, and I treat that placement as a discipline marker. There are 3 reasons the exception must be tight. Reason 1, avoid double counting geometry. If I were to put shell-like APR growth into the strong coupling in the same way I did for gravity and EM, then I would build a long-range field by construction. That is precisely what I do not want. The strong domain must be short-range and saturating. It must not generate a macroscopic inverse square tail between distant nuclei. So the exception does not mean strong has different geometry rules everywhere. It means the strong domain is not governed by shell dilution. It is governed by contact separation at the binding interface. And the solver expresses that through 2 rands in EQ, 11, and nowhere else. Reason 2, keep the unification promise honest. If I allow myself to add extra geometric terms outside AP, whenever a domain is hard, RSI becomes curve-fitting. The strong domain is where that temptation is strongest, because the legacy machinery is complex and the phenomena are nonlinear. So I treat the restriction as a proof stance. If EQ, 11, cannot carry the explanatory load together with the gates enclosure, then RSI fails the strong flagship. Reason 3, preserve a clean boundary between overlays. A core RSI claim is that different forces are overlays on the same ledger. That only works if each overlay corresponds to a distinct, disciplined readout, not to a domain where I redefine the math. Gravity and M are primarily S and AP stories with sign in M. The strong overlay is primarily an NC story coupled to gate admission and closure. The weak overlay is primarily a DC and engine closure story. If I blur those, then I will not be able to tell a reader what RSI predicts that legacy does not emphasize. The solver posture will dissolve. A strict audit statement. For this intro project, I treat the following as a hard formatting and logic rule. EQ, 11, is the only location in the entire intro where an explicit 2 rands is permitted outside AP. If I need geometry elsewhere, I must put it inside the appropriate anchor plane or the appropriate effective interface. 10.4 binding curve structure as a ledger readout. A physicist usually learns nuclear binding as a story about potentials, an attractive well at intermediate separation, a repulsive core at very short separation, and a rapid fall-off beyond a few femtometers. Then, in many-body nuclei, there is a saturation behavior. Binding energy per nucleon rises quickly in light nuclei and then levels off, with heavy nuclei destabilized by Coulomb effects and decay channels. RSI does not require me to deny that the potential picture works as an overlay. RSI asks whether I can explain why this structure is natural from a ledger and gates posture. 2 sanity targets I do not let myself dodge. Before I get poetic about confinement or wells, I name 2 empirical shape constraints that any strong overlay implementation has to survive. Deuteron weakness. The simplest bound nuclear pair is only weakly bound, a few MeV total, and correspondingly large, on nuclear link scales, a few femtometers. Any model that predicts an enormous, deeply bound 2-body ground state at this first step is already wrong in its closure bookkeeping. Iron-nickel peak binding energy per nucleon rises quickly from light nuclei, then levels and peaks in the iron-nickel region, order 8 to 9 MeV per nucleon, and then drifts down as Coulomb and surface effects win. RSI's claim is not that these numbers appear by magic from EQ, 11, alone. The claim is that the shape has a natural home in the ledger picture. Local strong edges saturate boundary identities, pay a neighborhood deficit, signed electromagnetic closure accumulates without saturating in the same way, and weak reconfiguration becomes available near the change threshold. I do that in 3 layers. I, the 2-body band, 2, saturation in many-body closure, and 2, the competition with electromagnetism and weak reconfiguration that sets the instability frontier. 10.4.1 2-body shape, why there is a stable band. For 2 nuclear identities, EQ, 11, tells me a coupling density scale once I specify the ledger in the effective separation interface. But EQ, 11, alone does not decide whether the configuration holds. The configuration holds only if it clears the existence gate and stays inside the stable band for change, EQs, 1 and 5, with the stability criterion summarized in EQ, S8 DC band. So the RSI reading of the 2-body binding curve is, there exists a band of separations where the binding edge is admitted, existence clears, and the change ratio stays below threshold, no force reconfiguration. In that band, a bound nuclear configuration is a persistent lattice. At separations larger than that band, the lattice cannot maintain the same closure. In RSI language, the binding corridor fails. The solver does not need to invent a long-tail force and then tune it away. It classifies the coupling channel as absent because the configuration no longer clears the gates as a nuclear bound identity. At separations smaller than that band, the system approaches a different barrier. In legacy language, this is a repulsive core. In RSI language, it is a forced reconfiguration triggered by the change gate and engine closure as the configuration attempts to compress beyond what the admitted closure channels can support. That last bullet is important. EQ, 11, is magnitude only. It grows as R shrinks if the ledger budget is held fixed. That does not mean the system collapses into infinite compression. The gates and the engine regulate what configurations are admissible and what transitions are forced. So the repulsive core can be read as an engine and threshold phenomenon without rewriting EQ, 11. This is also where I restate the solver posture from part 6. I do not start with a potential and then ask what it predicts. I declare a configuration, choose the correct interface, compute the gates, and then interpret the admissible band as the well and the force transitions as the walls. 10.4.2 Saturation. Why binding does not scale like volume. A very strong and very basic empirical fact is that nuclear binding saturates. A nucleon does not bind strongly to every other nucleon in a nucleus, the way gravity effectively couples to every mass. Instead, each nucleon binds strongly only to a limited neighborhood. RSI has a natural place to put this, and it does not require a new postulate. In RSI, binding is closure on edges. Edges are corridors and interfaces, not global shells. A nucleon has a finite boundary and a finite number of close contact corridor opportunities. Even if the nucleus contains many nucleons, the number of strong binding edges per nucleon does not grow without bound. It approaches a local packing limit. That is the RSI mechanism for saturation. Binding energy saturates because strong coupling is mediated by local closure corridors, and each identity has a finite neighborhood of strong edges. As the nucleus grows, you add more identities, but you do not proportionally increase the number of strong edges per identity. This is a statement about lattice topology and closure allocation, not about inventing a potential. It is also why I treat the strong overlay as a contact scale coupling channel. If strong were a shell field, it would not saturate in this way. 10.4.3 Competition with electromagnetism and weak reconfiguration. The binding curve of real nuclei is not purely strong. Protons repel electromagnetically, and that repulsion is long range compared to the strong contact band. Then, when a nucleus drifts near a threshold, weak reconfiguration channels become available, and decays happen. RSI's unification posture makes this competition clean conceptually. The strong overlay contributes local binding through admitted short-range closure corridors, with magnitude scale governed by EQ 11, when the channel is available. The electromagnetic overlay contributes sign closure that can repel, and its macroscopic residual can remain significant because it does not saturate locally the way the strong contact channel does. The weak overlay becomes relevant when the combined closure pushes some subconfiguration toward the change threshold, at which point the lattice searches for an allowed reconfiguration channel that lowers stress. So the RSI summary sentence for heavy nucleus instability is, a heavy nucleus becomes unstable in RSI when multi-domain closure pushes a subconfiguration toward DC. One in the lattice finds a permitted reconfiguration that reduces stress, such as alpha emission, beta decay, or fission. 10.4.4 A legacy bridge, the semi-empirical mass formula as closure bookkeeping. Many readers know the semi-empirical mass formula terms volume, surface, Coulomb, asymmetry, pairing as a high-level successful story about nuclei. RSI can host the same structure as a closure bookkeeping decomposition without claiming it is the final derivation. Here is the RSI map in one pass. Volume term, local strong edges inside the nucleus contribute roughly proportionally to identity count because most nucleons have a similar neighborhood of strong corridors. Surface term, boundary nucleons have fewer neighbors, meaning fewer admitted strong edges per identity at the boundary, so the closure contribution per nucleon drops near the surface. Coulomb term, net signed EM closure among protons is a long-range residual that does not saturate like strong contact edges, so it grows with proton content and pushes toward threshold. Asymmetry term, composition affects what corridors are available and how well the lattice packs. In RSI language, this is a closure compatibility penalty when identity types cannot share the same local optimal neighborhood. Pairing term, pairing is coherence. In RSI language, this is an orientation and channel coherence advantage. This is precisely the kind of effect theta and engine channel structure are meant to summarize without turning it into an ad hoc force. I am not claiming this paragraph replaces nuclear theory. I am claiming RSI has a natural place to store why the mass formula decomposition makes sense. It is a decomposition of how closure is earned in a finite lattice with boundaries, sign effects, and coherent structure. 10.5 Confinement bands and what range means in RSI. Terms. In legacy language, the strong interaction has two defining qualitative features. It is short range and saturating at nuclear scale, and it exhibits confinement, meaning quarks are not observed as isolated free particles in ordinary regimes. RSI can host both features without adding new primitives, but only if I am clear about what I mean by range and what I mean by confinement. 10.5.1 Range is not tension decay, range is channel availability. A common drift mistake is to treat range as a statement like the coupling, constant decays with distance. RSI does not allow me to do that, because it would tempt me to weaken T with distance or reinterpret DE as a distance coordinate. In RSI, range is instead a statement about channel availability. The strong coupling channel exists only inside a nuclear contact regime where the binding interface is emitted. Outside that regime, the channel fails, and NC becomes irrelevant because the lattice is not solving as a nuclear-bound configuration anymore. So when I say strong is short range, I am not claiming a magical force that fades away. I am claiming that the nuclear contact closure corridor is a bounded regime in the lattice, and the solver classifies the configuration outside that regime as not admitted in the nuclear-bound form. 10.5.2 Confinement band as a gate statement. Now I define confinement in RSI terms. A confinement band is a band of configurations where the composite identity is admitted and stable. Outside that band, the system cannot persist as that composite identity, so it must reconfigure into a different set of identities. That is literally the solver posture. Inside band, existence clears and the change gate remains below threshold, so the composite holds as a persistent identity. Outside band, the composite fails admission or is driven past threshold, so it cannot persist in that form and must reconfigure. This is why RSI can talk about confinement without making probability primitive. Confinement is a gate statement. Either a free quark-like configuration is admitted as a stable identity in the relevant regime, or it is not. RSI's claim is that it is not admitted as a stable identity in ordinary regimes. and the lattice instead resolves into hadronic identities that satisfy closure. 10.5.3 Why pulling apart leads to reconfiguration rather than free pieces. A legacy reader will often picture confinement as a potential that rises with separation, so pulling quarks apart stores energy until it becomes favorable to create a new quark-antiquark pair. RSI has a direct analog, stated in the ledger language. As a separation attempt pushes the configuration toward a barrier, the system is driven toward change by the collapse ratio DC-EQ5 and engine closure, EQS 6 to 7. When a deterministic threshold is met, the multi-anchor closure, EQ10, governs how the ledger reallocates into new identities, rather than persisting as a stretched, non-admitted configuration. So the RSI sentence for what legacy calls string breaking is, when the configuration cannot stay inside the admitted confinement band, the lattice does not continue as an unbounded stretched bond. It crosses a threshold and reallocates identity and energy into a new set of admitted identities. I'm intentionally keeping this as a structural claim in the intro. The purpose here is not to replicate every QCD detail. The purpose is to show that the same solver skeleton has a place to host confinement as an admission and threshold phenomenon without introducing new ontologies. 10.6 Minimal worked example, qualitative first, then a conservative pin. I now do the minimum worked example I would be willing to show to a skeptical technical audience. I keep it honest in three ways. I state what I am estimating and what I am not. I track units explicitly. I use one conservative pin, then reuse the structure without adding a new parameter. 10.6.1 units, what NC measures. Start with units, because this is where drift hides. EF carries joules J, dividing by 2 rands M2 yields JM2. That is an energy per area which is equivalent to a tension density NM1, because 1 JM2 equal to 1 NM1. So I interpret NC as a nuclear binding tension density scale, not as a force by itself. If I want to compare to a laboratory reported force, I must state a context length L and map tension density to force by. Fef equal to NCL. For femtometer scale comparisons, a scale consistent choice is L approximately equal to R. I'm spelling this out because it stops a very common error, treating a tension density as if it were already a force. 10.6.21 pin, deuteron is the simplest nuclear bound system. If I want a single pin that is not dominated by many body complexity, the deuteron is the obvious choice, 1 proton and 1 neutron in a weakly bound nuclear state. I do not need ultra precision for this intro. I need an honest order of magnitude pin. So I take a binding energy scale EB approximately equal to 2.2 MeV and a characteristic separation scale R approximately equal to 2FM, approximately equal to 2x1015M. Now I'll make a conservative modeling identification for the pin. I treat the field budget EF that participates in the binding edge as being of order the binding energy scale. That is not a claim that the full internal nuclear ledger equals the binding energy. It is a conservative way to set a lower bound coupling scale for the edge that is responsible for the binding. Convert 2.2 MeV to joules using 1 EV approximately equal to 1.6 x 10 to 19 J. For clarity, the exact psi mapping is 1 EV equal to 1.602 176 634 x 10 19 J, so the only approximation in the conversion below is the rounding I choose for readability, not a free parameter of RSI. EFD 2.2 x 106x 1.6x, then EQ 11 2 rands 2 ranchine D 10 to 15 meters as the pinned order of magnitude tension density. I simply chose a reference system and used EQ 11 directly as the strong overlay magnitude law. 10.6.3 reuse nucleon pair at 1 FM with a conservative nuclear budget. Now I reuse the structure with a typical nuclear scale at a tighter separation to show why strong dominates at femtometer distances. Take R approximately equal to 1 FM approximately equal to 10 to 15 meters, a conservative nuclear field budget EF5 MeV order of magnitude nuclear. Well scale, convert 5 MeV, 5x, 106x, 1.6x 1019, J8x 1013 J, then 8x 1013 J NC. 1015 meters to 8x 1013 equal to 1030 JM2, 8x 1017 NM1. 10.6.4, a clean comparison statement why strong must beat him at 1 FM. A reader will immediately ask if this scale is plausibly stronger than electromagnetism at the same separation. I'm going to keep the comparison canon clean and avoid embedding legacy inverse square formulas here. The empirical point I need is simple. The Coulomb repulsion between two protons at femtometer scale is large in everyday force units, but it is still overcome inside nuclei. A useful remembered benchmark is that proton Coulomb repulsion at about 1 FM is on the order of 102 newtons. Expressed as an effective tension density at femtometer scale, that is on the order of 1017 in Mel1. Our conservative strong estimate above is on the order of 1018 in Mel for a few MeV nuclear budget at 1 FM. That exceeds the Coulomb benchmark by a modest factor in this conservative posture, which is exactly what it must do if nuclei are to be bound without fine-tuning. If the relevant nuclear field budget is larger than 5 MeV in a given configuration, the margin increases correspondingly. This is exactly the kind of check I want from a flagship overlay chapter. It is explicit about what quantity neon measures. It uses the canonical strong law EQ 11. It stays canon clean about geometry placement, and it reproduces the basic empirical fact that nuclear binding overwhelms Coulomb repulsion at femtometer scales. 10.6.5. Next benchmark. The iron-nickel peak as a many-body closure test. The deuteron pin above is a two-body unit coherence check for EQ, 11, in the correct regime. A much harder and more diagnostic target is the many-body binding curve peak, commonly called the iron peak. In RSI terms, I want a later implementation to reproduce three linked facts in one consistent solve posture without introducing a second strong law and without tuning geometry outside AP. Rapid rise in light nuclei. As I add nucleons, the count of available strong corridors per nucleon grows toward its packing limit, so the average closure earned per nucleon rises. Saturation and peak. Once local neighborhood closure saturates, additional nucleons add less strong benefit per nucleon, while the electromagnetic signed closure penalty continues to accumulate, so the net curve peaks. Downward drift and instability frontier for sufficiently heavy nuclei. The combination of Coulomb penalty and surface neighborhood deficit pushes some sub-configurations toward D1, at which point weak and fission-like reconfigurations become available as deterministic threshold outcomes. If I want a numerical readout of how the ledger is allocated across many edges in a multi-body nucleus, I can use the ledger share diagnostic F from EQ 4 peso ledger share as a reporting layer, but I do not use it to replace the solver rule itself, which remains EQ 10. I'm deliberately not doing that full computation in this intro. What I'm doing is pinning the acceptance test. The strong overlay is not done in RSI until it can reproduce this curve shape in a regime-stated way, with the same gate order. Existence, then change, and with multi-anchor allocation handled by EQ 10, rather than by hand-splitting 10.6.6, what this worked example did not do. I am not claiming this short calculation is a full nuclear structure model. It is not. I did not model spin, isospin, detailed channel structure, or many-body shell effects. Those belong in a later technical build, and they will be expressed through the engine enclosure machinery, EQS 6, 7, and 10, and through explicit system declarations. What I did do is the minimum a skeptical reader should demand. I showed that EQ 11 yields the correct magnitude scale in the correct regime without new primitives, and I kept the anti-drift doctrine intact. 10.7. What this part established. I defined the strong overlay as nuclear coupling on the same RSI ledger, not as a separate force ontology. I used the canonical magnitude law EQ 11 NC equal to EF2 rands, and I made explicit that its R2 factor is the only permitted geometry exception outside AP in this intro. I distinguish QCD confinement and residual nuclear binding as two system declarations that can share one RSI posture. Confinement as a gate and threshold statement, and nuclear binding as a short-range admitted corridor regime. I reframed the nuclear binding curve as a gate enclosure readout. Stable band behavior comes from admitted configurations, and repulsive core and dissociation behavior come from threshold-driven reconfiguration rather than ad hoc potentials. I define range as channel availability, not as decay of T with distance, and I defined confinement bands as admission and threshold structure in the lattice. I provided a conservative, explicit magnitude pin, deuteron scale reference, and 1 FM reuse that lands in the correct order of magnitude for nuclear dominance at femtometer scales. New equations introduced in this part. No. I used EQ 11 plus existing gate and closure equations for interpretation. 10.8. Moving into the weak domain. Part 11 moves to the weak overlay. I will treat weak phenomena as deterministic collapse closure, not as a new force law. The goal is to show how half-life and decay families can be read as gate pacing outcomes routed through the engine and multi-anchor closure, with one concrete beta decay example and one environment dependence example to make the deterministic posture operational. 11. Part 11. Weak overlay as deterministic decay closure. Part 10 ended with the strong domain. The strong domain is the one place RSI permits an explicit 2 rands outside AP, and I treated that permission as a stress test. Now I move to the weak domain, which is a different kind of stress test. If the strong domain tests whether RSI can host short-range saturating binding without rewriting the ledger, the weak domain tests whether RSI can host decay and transition families without making probability primitive. Modern physics uses probabilistic language here for a reason. Half-lives are empirically real. Ensemble statistics are clean. The standard language is a rate law. RSI does not deny rates. RSI changes what I treat as fundamental. In RSI, decay is not a random roll that sometimes happens and sometimes does not. Decay is a deterministic reconfiguration that occurs when a configuration is admitted to exist but cannot remain itself under the change gate given the available channels. The probabilistic language then becomes an observational summary of many unresolved microstate variables, not a statement that nature is ontologically stochastic. This part is my weak domain contract. I will do 4 things. Terminology note: identity means anchored identity in this part. Throughout part 11, when I say identity, I mean an anchored identity, a configuration that currently clears the existence gate S and therefore participates as a resolved member of a lattice. Weak phenomena are not about non-existence. They are about admitted anchored identities that do not remain themselves under the change gate and therefore must reallocate into other admitted identities when closure finds an open route. 11.1. Weak is not a force. It is change gate closure. In the earlier parts I enforced a role discipline. S is the existence gate. It answers, does it hold now? EQ 1. DC is the change gate. It answers, is it driven to change? EQ 5. with a stable band and threshold posture already formalized in the supplemental stubs, for example EQ, S8DC threshold, and EQ, S8DC band. The weak overlay is the domain where I make that role discipline non-negotiable. If I want a single sentence definition that is compatible with the entire RSI doctrine, it is this. Weak phenomena are what I observe when a configuration is admitted by existence but not persistent under the change gate, and the engine has an open channel that reallocates the ledger into a new set of admitted identities. This is also why EQ, 12, is intentionally not a standalone new force law in the Core 12 map. It is a program note. In RSI, weak behavior is built out of the same change gate and closure machinery I already have, especially EQ, 5, and the engine and allocation closures in EQ, 7 through 10. I do not get to introduce extra primitives here without breaking the unification claim. So weak is not introduced as a new field that pushes things. Weak is introduced as a deterministic transition regime. The observable signature is that an admitted identity does not remain itself. It reconfigures into other identities that satisfy closure. This is why I keep ledger positivity explicit. A weak transition is not allowed to hide energy in a negative well. It must be expressed as a ledger reallocation under explicit closure. SE equal to EF plus EA EQ 4. The transition happens because the change gate crosses threshold under the available channels, not because energy disappeared and not because probability is a primitive. 11.2 The engine is the pacing mechanism. The main reason weak phenomena are usually described probabilistically is that we observe rates. A single nucleus might decay quickly or slowly, and a large ensemble produces clean exponential statistics. RSI has a natural place to host this without elevating probability to a primitive, engine closure, and boundary pacing. The two engine relations are already in the canon. K equal to X KCH theta DC EQ 6 EFDC equal to K BT EQ 7. I interpret these as the formal statement of a deterministic program. EF supplies the available field budget for change across the RSU span. K is the aggregate channel response. It encodes which channels exist and whether they are coherent and allowed in the present configuration through theta, and it feeds back on the effective collapse ratio through EQ 7. BT is the boundary pacing scale, the clock of the recursion update for that regime. So the weak overlay posture is not nature chooses randomly to decay. It is. Given the current ledger and the current channel availability, the configuration has a deterministic pacing toward a barrier, and when the barrier is crossed, the lattice reallocates into a new configuration that is admitted. This is also where I place probability language, carefully and explicitly. In RSI, probabilities are not primitives, they are overlays. When I do not know the full microstate, or I do not track every live contribution to the engine sum, I can still report a distribution for when an ensemble will cross the deterministic threshold. That reporting distribution is the weak domain analog of what I call directionality indicators, verdict arrows. Earlier in this book, it is a post-solve human interface layer, not the generator of the dynamics. Why half-life can still look exponential. RSI does not need to deny exponential ensemble behavior. It explains it as coarse graining. Even if the transition program is deterministic, I do not observe all microstate variables, and I do not know every channel input in EQ. 6. In an ensemble, those unknown microstates are distributed across the population. If the system is metastable and sits near a threshold, then small microstate differences can move the effective pacing slightly earlier or slightly later. When I coarse grain over that microstate distribution, an exponential law can appear, even though each individual decay is deterministic in principle. I am using the word metastable here as a legacy shorthand, not as a new primitive. In RSI grammar, metastable means the configuration is admitted. Now, S greater than or equal to 1, but the engine-regulated change posture places it near the threshold, DC approximately equal to 1, so it is expected to cross the change gate under pacing even though it is resolved at the present moment. In other words, the exponential is not a proof of ontological randomness. It is a statement that my macroscopic description does not track the microstate variables that control when the deterministic threshold is crossed. So I interpret the half-life as an engine readout. A half-life is a macroscopic summary of how quickly an ensemble of identically prepared configurations crosses a deterministic change threshold under the available channels and the boundary pacing scale. Half-life is a system property in RSI. This is a crucial posture shift. In RSI, a half-life is not only an intrinsic attribute of an isolated identity, it is a property of an identity in a declared system context. If the environment changes, which channels exist, which channels are coherent, through theta, or the boundary pacing scale BT, then the observed pacing changes. This is not speculation. Legacy physics already knows clear cases where weak rates depend on environment, electron capture, bound state beta decay in ionized atoms, capture channels from muons in matter. RSI interprets those differences as channel and closure differences, not as violations of the solver posture. 11.3 Example 1. Free neutron beta decay as a closure reallocation. A free neutron is a perfect weak example because it cleanly separates two contexts. A neutron as a bound member inside a nucleus can be stable for very long times. A free neutron outside that closure environment is not persistent and undergoes beta decay. Legacy physics describes this as the weak interaction, causing the neutron to decay into a proton, an electron, and an antineutrino. RSI describes the same outcome as a deterministic reallocation of the ledger into a new set of admitted identities under an open channel. I now walk through the solve loop explicitly, because the loop is the point of RSI. Step A, declare the configuration and the boundary. The configuration is a free neutron in isolation on the timescale where electromagnetic and strong bindings to other objects are negligible. The boundary question is, does this identity persist, or is it admitted only as a transient configuration? Step B, existence admission. I am not claiming a neutron fails to exist, it exists now. In RSI language, it clears the existence gate for its boundary, S equal to EAP, EQ, 1. At nuclear scale, the relevant interfaces are not macroscopic shells. They are contact scale corridors and internal boundaries. The important weak domain point is simply this. The neutron is an admitted identity at the present time. So weak does not come from failing existence. Weak comes from failing persistence under change. Step C, change gate and engine closure. Now I evaluate the change posture. EFDC equal to EA, EQ, 5. In RSI, a configuration can exist and still be driven to reconfigure. If the engine has an open channel that lowers closure stress by reallocating into different identities, then the deterministic program pushes the system toward that transition. This is the RSI reading of free neutron is unstable. The identity is admitted now, but it is not persistent under the change gate given the channel set. The change gate crosses threshold on a timescale governed by engine closure, EQ, 7, under the channel structure, EQ, 6, step D, ledger reallocation as the decay event. Legacy writes, N, P plus E plus nu. RSI does not need to rederive the standard model in this intro to state the RSI point cleanly. The initial identity is admitted now, but it is not stable under the change gate. The engine has an allowed channel that reallocates the ledger into a new set of identities. The resulting identities are admitted and satisfy closure in the new configuration. Notice what I did not do. I did not claim a negative energy well-released energy. I did not claim a random roll selected the outcome. I treated the transition as a deterministic closure reallocation under the available channel. Why bound neutrons can be stable in RSI language. This is a coherence test. A neutron in a nucleus does not behave like a free neutron. In RSI, that difference is not mystical. It is a system boundary difference. A bound neutron is not an isolated identity. It is part of a larger multi-anchor lattice. That lattice changes. Which channels are open? Which channels are coherent? Through theta. And the closure allocation for the neutron identity via multi-anchor closure. EQ, 10. So a bound neutron can remain in a stable band under the change gate even when a free neutron does not. This is the same logic I use for orbital membership, environment, and closure allocation matter, and RSI forces me to make them explicit. Why weak decay families exist at all. In nuclei, weak decays are not random surprises. They are part of how the lattice finds a more stable configuration when strong binding and electromagnetic repulsion compete. Legacy calls this the valley of stability and describes beta decays as moving nuclei toward an energetically favorable neutron to proton ratio. RSI says the same thing in closure grammar. Weak decay is one of the lattice's deterministic tools for editing identity composition when the current configuration is admitted now but cannot remain inside the stable band under the change gate. That is why weak decay families are systematic. They are closure corrections, not dice rolls. 11.4 Example 2, muon decay as the same solve loop. A muon is a second weak example that is valuable because it strips away nuclear structure and lets me talk about a clean, unstable identity in a different family. In legacy language, a muon decays into an electron and neutrinos. In RSI language, it is the same structural posture as the free neutron. The muon is an admitted identity now, but it is not persistent under the change gate, and an engine channel reallocates it into other admitted identities. I walk the loop again, more compactly. Step A, declare the configuration. The configuration is a free muon in isolation. Boundary question, persistent identity or transient. Step B, existence. The muon exists now. It clears the existence gate at its boundary, in the same sense any admitted identity does. Step C, change gate and engine. The muon does not remain itself. It crosses the change threshold on a characteristic timescale. In RSI terms, the timescale is not a magical probability constant. It is an outcome of engine pacing. EFKBT EQ7 DC equal to. Legacy presentations often package this pacing into a coupling constant and a rate expression. In RSI, I do not dismiss that legacy constant, I relocate it. It becomes a calibrated mapping coefficient between the ledger primitives I am actually solving, EFKBT, and the measurement overlay in seconds that an instrument reports. Once pinned in a stated regime, it is reused, not tuned nucleus by nucleus or particle by particle as a free knob. I emphasize what K means in this context. K is not an arbitrary fit knob per muon. It is the sum of allowed channel contributions, EQ, 6, and whether those channels are coherent in the present configuration through theta. If the muon is placed in matter, additional capture channels can open, which changes the effective channel sum and therefore changes the observed lifetime. That environmental dependence is a direct RSI prediction. Step D, decay as ledger reallocation. Legacy writes UE plus nu. RSI reads it as the muon identity is a transient configuration, and the lattice reallocates into a new set of admitted identities when the change threshold is crossed. The unification point is that nothing about the solver posture changed between neutron beta decay and muon decay. The identities are different, the channel lists are different, the closure details are different. But the posture is identical, admit existence, evaluate change, close change through the engine, reallocate through closure. 11.5 Environment dependence example, electron capture, ionization, and captured channels. I include at least one explicit environment dependence example here, because this is where the claim half-life is a system property either connects to reality or it does not. I will do the cleanest legacy known case, electron capture, and then I will briefly connect it to the muon capture fact I already referenced. Electron capture shows channel availability directly. In legacy nuclear physics, some decays proceed by electron capture EC. A bound electron is captured by a proton in the nucleus, producing a neutron and an electron neutrino. The key empirical feature is that the rate depends on the availability and density of electrons near the nucleus. In RSI, that dependence is exactly what I should expect, because EC is not a decay that happens because probability says so. EC is a reconfiguration channel. Channels can be open, suppressed, or absent depending on boundary and lattice context. In RSI terms, the EC channel requires an electron to be present in the relevant boundary region of the system. If the atom is chemically bound differently, the electron density at the nucleus can change. If the atom is highly ionized, few bound electrons, the EC channel can be strongly suppressed or altered because the required boundary participants are missing or changed. So in the engine language, the EC channel contribution to K, EQ, 6 is not a fixed constant of the nucleus alone. It is a system term. If the electron boundary state changes, the effective channel coherence and availability changes. In RSI terms, that means K changes, and therefore the pacing statement in EQ, 7, changes. This is the RSI sentence that matters. Electron capture is an environment-dependent stress test, and it passes naturally in RSI because the channel literally requires a boundary participant whose availability depends on context. Ionization can open and close weak channels. There is a second famous environment lesson in legacy nuclear physics. Some beta decays behave differently when an atom is highly ionized. In extreme ionization, new channels can become allowed, bound state beta decay, and old channels can be suppressed, electron capture. I do not need to detail those experiments in this intro. I need to state the RSI structure. Weak selection rules are channel rules. Channel rules are part of the engine closure. If I change the environment enough to change which boundary participants exist and which corridors are available, I can change which weak channels are admitted and therefore change the observed pacing. This is why I do not treat half-life as an untouchable magic property. It is a stability and channel property of a system in context. Muon capture is the same kind of environment dependence. A negative muon in matter can be captured by a nucleus. This introduces an additional channel that does not exist for a free muon, and it competes with ordinary decay. The observed lifetime in matter then differs from the free muon lifetime, and the difference depends on the nuclear environment. In RSI terms, this is not an add-on. It is exactly what EQ 6 and EQ 7 are for. The channel list and coherence changes in a new environment, so the engine sum changes, so the pacing changes. 11.6 Allowed, forbidden, and the meaning of selection rules. Legacy weak physics has the language of selection rules. Some transitions are allowed, some are suppressed, and some do not happen at all. In standard quantum language, this is expressed through symmetries, coupling structures, and matrix elements. RSI has a direct structural analog that stays inside the core 12 posture. Allowed versus forbidden is channel coherence and channel availability in the engine closure. In other words, a channel is allowed if it exists in the system declaration and contributes coherently in the engine sum, EQ, 6, such that the change closure supports it. A channel is forbidden if it does not exist in that system context, or if its coherence gate theta suppresses it in the present configuration. A channel is suppressed if it exists, but contributes weakly compared to others, so the pacing is slow and the apparent half-life is long. Decay family scaling posture, brief but explicit. Within a decay family, allowed versus suppressed is not a mystical category in RSI. It is a statement about the effective channel weight that appears in the engine loop. A channel that is structurally allowed has a large effective contribution in EQ 6. Its KCH term is present, and its coherence gate theta is not strongly suppressing it. That yields a fixed point pacing that reaches the change threshold quickly. A suppressed or forbidden transition corresponds to the opposite. The relevant channel is missing, or its coherence factor is small in the present configuration, so its contribution to the engine sum is negligible, and the route is effectively unavailable on practical timescales. This is why half-lives cluster and scale in families. Without me adding a new primitive, the scaling is a readout of which channels exist and how coherently they participate in closure, in that declared system context. This gives me a clean RSI meaning for why half-lives can vary enormously across families. It is not because nature is rolling dice with different biases for each nucleus. It is because the engine channel structure differs and closure coherence differs across systems. 11.7 What would count as success and failure for the weak overlay? I keep the proof stance honest. I name success targets and failure conditions. Success target 1, family resemblance without new primitives. If I can treat neutron decay families, muon decay, and nuclear beta decay series as the same solved loop with different channel lists and different boundary conditions without inventing new force objects, then RSI has passed the first unification burden. Success target 2, environment dependence is explainable at the channel level. If electron capture and capture channels in matter read cleanly as channel availability and coherence effects in the engine sum, then RSI has demonstrated it is not merely relabeling legacy rates. It is giving a more primitive explanation of why rates depend on context. Success target 3. Half-life scaling can be posed as a closed pacing program. If I can express half-life families as consequences of engine pacing, K and BT, and closure allocation, EQ, 10, and reuse the same posture across many systems, then RSI has a path to a quantitative program. Failure condition 1. Irreducible probability as primitive. If accurate weak rates require a probability postulate that cannot be reduced to coarse graining of deterministic channel closure, then the core RSI determinism claim fails. RSI could still be a useful ledger, but it would no longer be universal in the way I am claiming. Failure condition 2. Hidden reservoirs or hand splitting. If I find I must hide energy in negative wells to make weak energetics balance, or I must split energy by hand rather than allocate through closure, then RSI fails its ledger discipline. Failure condition 3. Domain-specific geometry hacks. If I find I must introduce distance decay tuning of T or reinterpret D as distance in order to model weak transitions, then RSI fails the cross-domain reuse test. Weak must remain a change gate story, not a geometry smuggling story. 11.8. What this part established. I define the weak overlay as deterministic change gate closure, admitted identities that are not persistent under DC cross a threshold, and reallocate into new admitted identities through open channels. I treated half-life as engine pacing, not as a primitive probability. Ensemble randomness is a coarse-grained readout of unresolved microstate variables under a deterministic closure program. I gave real decay narratives, free neutron beta decay and muon decay, using the same solve loop, existence admission, change gate evaluation, engine closure, and ledger reallocation. I provided an explicit environment dependence example using electron capture and ionization posture, and I connected it to muon capture in matter as the same channel availability mechanism. I mapped selection rules to RSI channel coherence and availability in the engine sum, and I stated explicit success and failure conditions for the weak overlay. 11.9. 4 domains, 4 overlays. Part 12 is where I reconnect the 4 overlays into a single picture of the universe. I will strengthen redshift, dilation, and lensing as stability diagnostics and after-action reports, and I will show how those observables fit inside the same gate and ledger posture rather than being treated as separate primitives. 12 Part 12, 1 universe, 1 solver, 4 overlays. Parts 8 to 11 were the flagship sequence. I treated gravity, electromagnetism, strong binding, and weak decay as overlays on a single solver posture. Now, I have to do something that matters more than any individual domain chapter. I have to show what the universe looks like when I take the solver seriously as a unification grammar. This part is the glue chapter. It is where I stop presenting RSI as 4 separate overlays and instead present it as one picture with 4 reporting languages. So I am going to do 3 things in a way that is concrete and audit-friendly. 1. I give the single RSI solve loop in its final universal form, and I make clear where legacy concepts enter as overlays. 2. I define the system lattice picture, meaning how atoms, apples, planets, black holes, galaxies, and the far-field universe all appear as the same kind of object, just at different recursion spans and different effective interfaces. 3. I show that the headline observables people trust, orbits, weight, charge attraction and shielding, binding, decay timing, redshift, dilation lensing, can all be read as gate outputs, closure allocation outputs, or stability shift outputs, not as unrelated miracles requiring 4 unrelated ontologies. I am not claiming this chapter is the final full replacement of all physics textbooks. I am claiming it makes the posture coherent. If the posture is coherent, then the rest of the program is clear. Expand the validation suites, widen the calibration reuse, and refine the effective interface models until the predictions are sharp. Terminology note: to prevent drift. Throughout this part, when I say identity, I mean an anchored identity in RSI terms, a resolved participant that carries an anchored budget EA and is admitted or rejected by the existence gate S. When I draw a lattice, each dot is an identity node, meaning a node that represents an anchored identity, and each edge is an interface where I choose an explicit geometry carrier, shell, or corridor before I compute anything. I also keep the overlay posture explicit. Legacy constants and vector tools are not erased. They are calibrated mappings and reporting representations layered on top of the scalar ledger. I pin a mapping coefficient once per regime and reuse it. I do not treat constants as arbitrary tuning knobs, and I do not treat vector diagrams as the primitive source of a verdict. 12.1. Part 12. 1 universe, 1 solver, 4 overlays. The universal solve loop, I keep the loop short enough to hold in one brain at once, but strict enough that it is not a story. Step 0. Declare the boundary question. I start by stating what I am solving. Examples. Does this configuration exist as a resolved identity now? If it exists now, does it persist or must it change? If it must change, which channel is open and what is the pacing? Is this object a member of the system or a fly-through? If I cannot state the boundary question, I am not doing RSI. I am narrating. Step 1. Declare identities and edges, the lattice. I list the anchors I am treating as identities in this solve. Then I list the coupling edges that are active in the present configuration. The lattice is not decoration. It is the system. I list the anchors I am treating as anchored identities in this solve, identity nodes in the lattice picture. Then I list the coupling edges that are. Step 2. Choose the correct interface geometry. I select the correct geometry carrier for each edge. 1. Shell regime uses. AP with the appropriate mapping, for example EQ, S4 AP of R. Corridor and overlap pockets use an explicit effective interface AP, not AP, and not geometry hidden in D. This is the anti-drift step. If the solve surprises me, I check this step first. Step 3. Build the ledger. I keep roles strict. Tis energy per RSU layer J. DGI is an integer layer count. EF equal to TD EQ2. Edits the anchored budget scale, EQ3, posture, with D1 at the boundary when needed. Sigma EP plus stays explicit and positive, EQ4. Step 4. Evaluate gates in the correct order. I evaluate existence first, S equal to EEAP, EQ1. Then I evaluate change, DC equal to EFEA, EQ5. I do not swap those roles, I do not blend them. Step 5. Close change through the engine when pacing matters. If the question is not only hold or change but also how and how fast, I close through the engine. K equal to X, KCH theta DC, EQ6, EFDC equal to KBT, EQ7. This is where channel structure and coherence live. This is where selection rules and suppression live. This is where weak pacing lives. This is where magnetism becomes a dynamic closure overlay rather than a new substance. Step 6. Allocate multi-anchor closure without hand splitting. If more than one anchor participates, I do not split EF or EB hand. I allocate through the partner sum. EA equal to X, Q theta DC, EQ 10. Membership and system allocation are read off that closure, not guessed from short trajectory arcs. Step 7. Report and overlays. Only after the solve do I produce vector arrows, trajectories, potentials, or time parameters. Those are reporting layers. In RSI, I try to never confuse the overlay for the primitive. The system is solved first. The arrow is drawn afterward. Only after the solve do I produce directionality indicators, verdict arrows, trajectories, potentials, or time parameters. Those are primitive. The system is solved first. The directionality indicator is drawn afterward. Legacy vectors remain one of the best overlays for representing direction and flow, but they encode directionality and magnitude as a reporting representation, not as the decision primitive. In RSI, I first solve a scalar verdict, stability ratios and allocation shares, and then I draw directionality indicators from the already solved imbalance. This is the universal loop. The domains do not change the loop. The domains change the interface geometry regime and the channel list. That is why I claim unification. 12.2. The system lattice picture, what the universe looks like in RSI. Now I say what this posture implies visually. In RSI, the universe is not primarily a set of particles moving in a continuous background. It is a nested lattice of resolved systems. Each system is a finite closure network with a boundary. That boundary is not a philosophical metaphor. It is the place where I'm willing to say D is an integer layer count, where the interface has a defined geometry carrier, and where existence and change are evaluated explicitly. So I picture the universe like this. An atom is a system. It has anchors, nucleus, and electron identity structure, edges, coupling channels, a boundary, its admitted identity interface, and a far field where its closure participation becomes negligible relative to larger systems. A molecule is a system built from atoms as identity nodes, nodes representing anchored identities. It has its own boundary and its own closure. Allocation. The atoms do not stop existing. They become internal identinodes in a larger lattice. An apple is a system. It has an internal lattice, molecules, cells, and it sits inside a larger system Earth environment, where gravity and contact edges govern its macro stability. A planet is a system, a solar system is a system, a galaxy is a system. Each is a lattice with nodes, edges, boundaries, and a far-field transition into the next context. Identity nodes, edges, boundaries, and a far-field transition into the next context. This nesting is what I mean by universal relativity in practical terms. The same object can be treated as a boundary system in one context, and as an internal node in a larger context. What is flat and what is curved is not absolute. It depends on what system boundary I declared. As a boundary system in one context, and as an internal identity node in a larger context. What is flat and 12.2.1 Tripp scale horizons as system boundaries. I use the word Tripp scale as a practical label for the far-field horizon of a system, the region beyond which the system's closure participation becomes so thin relative to the surrounding context that it is effectively flat from that system's perspective. I want to be careful here, because this is where readers often mistake me for saying distance is hidden in DE. I am not doing that. I keep the doctrine. DA is an integer layer count, not a metric distance. Distance scaling is carried by interface geometry in AP or in an explicit effective interface, APEF. So when I talk about a Tripp horizon, I mean a contextual transition defined by solver outputs. A Tripp horizon is the boundary beyond which further recursion layers do not materially change the admission and allocation verdicts of the declared system, because the system's closure contribution is diluted by interface growth and overwhelmed by the larger context. In other words, every system has a finite contextual limit, where, for practical purposes, it becomes a node in the next system up. That limit is not only geometric, it is allocation, it is membership, it is a closure horizon, an identity node in the next system up. That limit is not only geometric, it is allocation, it is membership. This is the RSI mechanism for why systems are separate. Systems are separate because they are closure networks with finite boundaries and finite effective interaction corridors. Beyond that boundary, the system is not missing, it is contextualized. The solver can evaluate gate ratios, S and DC, across declared interfaces. Those gate ratios define a stability distribution in the surrounding context, a stability terrain. That stability distribution is what legacy language calls a field, and it is why directionality indicators, verdict arrows, can be drawn after the scalar solve. So my discipline translation is, Anchor influence produces a stability distribution across the correct interface geometry. And the observable overlays, forces, arrows, potentials, travel time delays, are reports of how identities traverse or sit inside that distribution. 12.3, how the 4 overlays fit in one picture. Now I summarize the 4 overlays in the one paragraph form I would use on a whiteboard at a convention. Gravity overlay. Gravity is what the lattice looks like when the dominant coupling readout is the existence ratio evaluated on a shell interface. Inverse square behavior appears because AP grows like a shell and S equal to EAAP EQ. 1. The arrows are drawn after solve. Electromagnetic overlay. Electromagnetism is the same shell dilution logic plus sign closure. The inverse square family still lives in AP. Attraction and repulsion live in theta, inside sanction closure and engine sums, EQs 6 and 10. Screening and shielding exist because sign closure can cancel in matter. Strong overlay. Strong binding is not shell dilution, it is contact scale corridor closure. Its magnitude law is the single explicit geometry exception in EQ 11, NC equal to EF 2 rands. Range is not decay of T with distance. Range is channel availability. Saturation exists because strong edges are local and finite in a packed lattice. Weak overlay. Weak phenomena are not primarily spatial forces. They are deterministic change closure. An identity can be admitted now and still be driven to reconfigure under DC EQ 5 with pacing and selection rules stored in engine closure EQS 6 and 7. Half-life is an engine pacing readout in context, not an ontological dice roll. This is the unification claim stated cleanly. The solver skeleton does not change. Only the geometry regime and channel list change. That is why I can talk about atoms and apples with the same grammar. 12.4 observables as stability readouts. Now I tie the big observables together because this is what makes the picture feel real. 12.4.1 redshift and time dilation as stability shift diagnostics. In part 8, I introduced ZAS, the stability shift observable, SC equal to S, EQ, 9, and its source observer form. Z equal to SOBS, SSRC, EQ, 18. In RSI, gravitational redshift, gravitational time dilation, and a large class of propagation shifts are not separate primitives. They are different faces of the same statement. A measured shift compares two contexts. RSI stores that comparison as a fractional stability ratio difference. I keep the posture modest and testable. I do not claim this paragraph replaces all of GR. I claim it tells you what GR observables are measuring in RSI language, and it sets up the correct empirical program. After a single calibration pin, does the readout match the observed timing and frequency shifts across multiple independent contexts without retuning. 12.4.2 flagship observational anchor, the Pound-Rebka Tower redshift. If I want a single terrestrial experiment that forces me to treat redshift as a real diagnostic and not as an interpretive story, I use the Pound-Rebka Tower measurement. The reason is simple. It is deliberately built to remove the usual escape hatches. There is no cosmology. There is no need to invoke large-scale expansion. It is a local comparison of a spectral identity prepared at one height and reported at another height inside one gravitational system. Operationally, the benchmark uses a narrow gamma transition so that an extremely small fractional shift can be detected for a tower-scale height difference. The key point for this intro is not instrumentation detail. The point is that the measured shift is tiny but non-zero, and it is a controlled readout of a stability contrast across two nearby contexts in the same anchored lattice. In RSI language, I do not treat the result as a primitive claim that time itself slows. I treat it as a direct measurement of a stability ratio difference between two recursion contexts in the same system. The clean diagnostic posture is the source observer redshift form. SOBs, SSRCZ equal to SSRC, EQ, 18. Here SRC is the emission context, and OBS is the reception context. The measurement is a report of how the same anchored identity is expressed when it is carried across a small but real stability mismatch. The smallness of the effect is also RSI native. Earth-scale shell changes over tens of meters produce extremely small changes in the geometry carrier, so the ratio shift insists small. What matters is that the same gate and ledger grammar that later produces large shifts near compact objects also produces this local shift with no ontology change. This is why I treat Pound-Rebka class experiments as a flagship reality anchor for the claim that Part 12 observables are solver diagnostics, not metaphors. 12.4.3 flagship observational anchor, Shapiro time delay as an integrated pacing differential. Redshift and clock offsets are not the only way a stability contrast shows up. There is a timing signature that sits at the seam between dilation and lensing, and it is one of the cleanest solar system confirmations that the field is not a story. It is the Shapiro time delay signals that pass near a massive anchor take longer to arrive than they would along a far-field comparison path, even when endpoints are fixed. In legacy language, this is described as increased coordinate travel time. In RSI language, I do not need a coordinate time ontology. I need the same posture I already used for redshift. An anchored identity moves through a lattice whose stability context is not uniform. The net effect along a path is an accumulation of small layer-to-layer pacing differentials, and that accumulation is reported as an arrival time delay when translated back into instrument overlay language. This anchor matters because it gives a linked triad test in one environment without switching primitives. Frequency shift, clock pacing offset, and travel time offset should be mutually constrained by one stability terrain. 12.4.4 lensing as a transverse stability gradient. Legacy GR frames lensing as geodesic bending. RSI frames it as propagation through a region where stability varies across the beam profile. Once a stability distribution exists, it is automatic that a transverse gradient can produce bending in an overlay trajectory picture. So the lensing story is not separate from the redshift story. It is the same kind of object, a stability distribution in context. Different observables emphasize different aspects of the distribution. 12.4.5 Flagship Observational Anchor, Solar Grazing Ray Deflection. The solar grazing ray deflection is the historical lensing benchmark because it forced physics to treat light deflection as a real field diagnostic. In legacy general relativity, the classic value for a grazing ray at the solar limb is about 1.75 arcseconds, and later measurements confirm the effect robustly. In RSI terms, the solar deflection is a reuse test of the stability terrain. The sun is an anchor concentration that produces a structured stability gradient in its surrounding shell context. A photon is a resolved identity unit with energy, so it participates in the ledger. A wavefront whose near side and far side traverse slightly different stability contexts cannot remain balanced without reorienting. The reorientation is a layer-by-layer accumulation of small scalar rebalances, reported as a net angular deflection. I do not need to switch primitives to say this. The same calibrated gravity overlay that constrains orbital stability should constrain grazing ray propagation, because both are readouts of the same stability profile. 12.4.6 Flagship Observational Anchor, Einstein rings, and strong lens arcs. Strong lensing is where nature draws the diagnostic on the sky as geometry. When a background source, a foreground lens, and the observer align closely enough, the deflection field produces multiple images and, in near symmetry, an Einstein ring. When the lens is structured, we see arcs and shear fields. Time delays between multiple images add a timing channel on top of the image geometry. In RSI language, I treat these as direct probes of the stability terrain. Ring and arc morphology encodes transverse structure gradients across a lens plane. Multiple images are multiple stable path solutions through a structured lattice. Image time delays are pacing mismatch readouts expressed as integrated differences along different paths, consistent with the Shapiro delay posture. Strong lensing also forces accounting discipline. Real lenses are multi-anchor environments. I do not smear the ledger by hand. Contributions must be allocated explicitly using EQ 10. This creates a clean fork. Either the declared ledger and correct interface regime reproduce arcs and delays, or the model fails, or the ledger is incomplete, or the regime declaration, shell versus corridor, is wrong. Observables map, the 4 anchor diagnostics. In this chapter, I'm treating 4 flagship observational anchors as diagnostics of the same underlying stability terrain. Pound-Rebka redshift, Shapiro delay, solar grazing ray deflection, and Einstein ring strong lens arcs. They are not separate ontologies. In RSI, there are 4 readouts of the same gate and ledger grammar. In part 14, I collect these as validation cards with a clear calibration pin, a computation path, and an explicit failure condition. 12.4.7 Binding energies, reaction thresholds, and decay timing. At microscale, the observable suite is different, but the ledger posture is identical. A binding energy is a ledger difference between admitted configurations in a declared system context. A reaction threshold is a gate boundary. In RSI language, it is a change gate boundary. The system crosses it and reallocates. A half-life is a pacing readout of that threshold crossing, controlled by the engine channel sum and the boundary pacing scale, EQs 6 and 7. This is why I keep repeating that RSI is not just a new math toy. It is a reinterpretation of what the observables are already telling us. In RSI, observables are not evidence of unrelated forces. They are evidence of gate behavior and closure behavior across contexts. 12.5 vectors and time are still useful, but they enter after the solve. A reader trained in physics will often worry that this unification posture is trying to erase the most useful tools we have. I am not. I am trying to reorder them so they do not become metaphysical crutches. Vectors. Vectors are the cleanest way to map direction and flow. RSI does not forbid vectors. RSI forbids using vectors as the primitive that decides existence and stability. In RSI, the primitive verdict is scalar. Does it hold? Does it change? How is closure allocated? Then I can derive arrow overlays from solved scalar fields and use vector calculus as a reporting layer. This is why I say arrows are drawn after solve. Vectors are a powerful overlay for representing directionality and flow, and I use them constantly once I have a solved ledger. RSI does not forbid legacy vectors. RSI forbids using vectors as the primitive that decides existence and stability. In RSI, the primitive verdict is scalar. Does it hold? Existence gate. Does it change? Change gate. And how is closure allocated? Multi-anchor closure. Then I build directionality indicators, verdict arrows, from the already solved scalar imbalance, for example, from a gradient of S across a declared interface, or from an allocation asymmetry in EQ 10, and I'm free to use vector calculus as a reporting layer without letting it sneak into the primitives. Time. Time coordinates are the cleanest way to index sequences. RSI does not forbid time parameters. RSI forbids assuming a privileged universal clock is required to decide what the system is. In RSI, a system is a closure network with a boundary. A process is a reconfiguration sequence. If I want to report that sequence with a time coordinate, I can. The choice of time parameter is part of the overlay. That is, universal relativity is posture. The reporting coordinates depend on context, but the solver verdict does not. 12.6 What this part established. I stated the universal RSI solve loop in a single audit sequence: declare boundary, declare lattice, select interface geometry, build ledger, evaluate gates, close through engine if needed, allocate multi-anchor closure, then report and overlays. I define the system lattice picture, Atoms to apples to planets to galaxies are the same kind of object. Nested systems with boundaries and closure. Horizons. I define trip-scale horizons as solver-defined contextual limits, where further recursion does not materially change admission and allocation verdicts, without smuggling distance into deep. I summarized the 4 overlays in one unified picture and kept a strong reception confinetto EQ. 11. I tied major observables to RSI readouts, redshift and dilation to Z, lensing to transverse stability gradients, binding and decay to gate boundaries, and engine pacing. I reaffirmed the overlay stance. Vectors and time remain essential reporting tools, but they enter after the solve rather than functioning as the primitive system definition. 12.7. Heading out to system horizons. Part 13 moves outward in scale and inward in consequence. I will sharpen the trip horizon idea into a system boundary tool, and I will apply it to extreme systems such as compact objects and black holes. The goal is to show that RSI can describe event horizon-style phenomena as stability boundaries in the same gate and ledger language, while keeping the observational posture disciplined and testable. 13. Part 13, Elios Tripp ladder, horizons and cosmology scaffold. Part 12 gave me the observational language. Redshift, clock offsets, and lensing are not 3 different primitive mechanisms. They are 3 diagnostic faces of one scalar mismatch. The stability ratio sand, its fractional shift Z, EQ, 9, with the source observer form in EQ, 18. Now I need to say what those diagnostics are diagnosing. This part is the universe map chapter in RSI terms. It is where I put the phrase Elios to Tripp on the page and make it operational instead of mystical. I will do 5 things in the order I want a technically educated reader to absorb them. 1. I define the Elios Tripp ladder as bounded recursion, not a metaphysical ladder. 2. I define horizons as stability boundaries inside a lattice, not singularities. 3. I give a cosmology scaffold that says what early universe means under RSI primitives. 4. I place the Big Bang anchor story inside that scaffold as a corridor to anchor transition. 5. I state what RSI predicts structurally at cosmological scale before fine calibration, meaning the things that must be true if the primitives are true. If this part does not land, then the earlier chapters can feel like a local modeling language with no global picture. If it lands, then the earlier chapters become legs of one map. The universe is a stability network with bounded recursion depth, and every phenomenon is a hold verdict or a change verdict inside that network. 13.1 claims ladder for cosmology and horizons. Because this chapter touches the Big Bang, horizons, and the far field, I tier my claims explicitly. This is not rhetorical caution. It is solver hygiene. Tier 1, derived and defined inside RSI. These are statements that follow directly from the primitive gates and ledger rules already established. Existence is evaluated by Sun, an explicitly chosen interface, sequel to EAAP, EQ, 1. Change is evaluated by the change ratio, dSequal to EF, EA, EQ, 5, with the stable band and threshold posture described in the project stubs. Geometry factors live inside AP everywhere, except EQ, 11, is the single allowed strong domain exception with an explicit 2 rands. Multi-anchor allocation is not a manual split, it is the partner sum, EQ, 10, redshift is a stability after action report, is equal to SS, EQ, 9, and EQ, 18. Tier 2, interpretation of Tier 1 results as a physical picture. These are not new equations. These are the coherent physical meanings that follow once I take the Tier 1 rules seriously. A horizon is the last resolved interface in an exterior accounting, expressed as a gate boundary using EQ. 1. Coming from a point is reinterpreted as coming from a first admitted anchor interface, not as a literal singular point. Pre-Big Bang modeling means modeling corridor pockets and asking whether gate conditions can nucleate the first anchor. Tier 3, speculation and open inference. These statements are not theorems. They are plausible consequences if Tier 1 and Tier 2 continue to succeed under data pressure. Other universes or other contexts could exist outside our ladder window. What Legacy calls extra dimensions could be a way of describing context, layers and recursion horizons, rather than literal extra spatial directions. I will label Tier 3 language when I use it. I will not smuggle Tier 3 into Tier 1. 13.2 The ladder as bounded recursion, not mysticism. When I say Elios Tripp ladder, I am not introducing 2 new forces or 2 new cosmic objects. I am naming the bounded window in which the RSI solver has meaning. RSI is explicitly a recursion layer theory. I do not use continuous infinities as primitive structure. My ledger is built from a per layer budget T, energy per RSU layer 200, an integer recursion span DG, layer count, field energy ETDEQ, 2, anchor energy X EQ, 3, posture, with the boundary condition DG equal to 1 at an anchor interface, and the existence gate SEA, AP, EQ, 1, with geometry confined to AP. In this part, when I say identity, I mean an anchored identity, a resolved configuration admitted by the existence gate that carries a defined E-date its boundary. A recursion theory, with these primitives, naturally forces a question that most legacy theories postpone. How far can recursion proceed before the primitives stop being meaningful? RSI answers by bounding the ladder at both ends. The upper bound, Tripp. I use Tripp scale to mean the practical cap on resolved recursion in our universe. In the spine intent, this is the scale beyond which resolved interaction ceases to make sense in the RSI primitive layer. A useful magnitude to keep in mind for context is the observable universe order, around 1026 meters. But the RSI meaning is not a wall in space. The RSI meaning is a boundary of resolved accounting. Operationally, resolved interaction means there is a lawful interface on which I can evaluate S. If I cannot define an anchor plane mapping AP that makes sense for the interaction context, I cannot evaluate SA as a gate. If I cannot evaluate S, I cannot make a hold verdict, and I cannot define stable membership allocation at that scale. So Tripp is the upper boundary where the lattice becomes too dilute, too spread, or too uncorrelated for the existence gate to be a meaningful solver on that scale. This is why I call it an upper bound on resolved recursion rather than a distance to a boundary. It is not a boundary in space. It is a boundary of stable, reportable resolution in the solver itself. The lower bound, Elios. I use Elios scale to mean the minimal resolved interface, the lower bound that prevents point collapse to a mathematical singularity. If the only way a theory can represent extreme collapse is to let R 0 and accept a singularity, then the theory has given up on staying physical at the limit. RSI does not accept that. RSI enforces a minimum interface scale where the anchor plane is still meaningful, meaning there is a smallest admissible shell in the ledger sense. Operationally, Elios is the statement. There exists a smallest meaningful interface on which cis evaluated as a gate. Collapse does not proceed past that interface as a resolved external description. This does not mean nothing exists below Elios. It means the external accounting does not propagate inward past that last resolved interface without violating the existence gate conditions for the external ledger. In RSI, that is what it means to say singularities are not required as externally resolved objects. A compact way to hold the latter in mind. It helps to keep the latter as a bounded interface statement rather than a mystical hierarchy. Let R Elios denote the smallest resolved interface radius for an external accounting, and let R Tripp denote the largest resolved interface radius for that accounting. Then the solver only claims fully resolved external gate evaluations in the window. R Elios less than or equal to R less than or equal to R Tripp. This is not a new law. It is the declared domain of meaningful application for EQ. 1. As a resolved external gate. What the ladder buys immediately, no required infinities. The Elios Tripp ladder gives me something that is hard to get cleanly in a purely continuous model. A principled reason to reject both ends of the infinity spectrum as required physical objects. No R, 0 singularities as required physical objects because Elios is a minimal resolved interface for external accounting. No R, infinity perfectly resolved influence because Tripp is a practical cap on. Resolved recursion and unstable membership accounting. This is not a philosophical preference. It is a modeling constraint that keeps the solver finite and keeps the gates meaningful. The price of that finiteness is that horizons and observational limits are not just accidents, they are expected. The latter is bounded, so the universe should contain last resolved interfaces in both extreme collapse and extreme reach. 13.3 Horizons as stability boundaries in a lattice. Legacy relativity treats horizons as geometric structures in spacetime, and classical GR predicts a singularity in the interior of a black hole. RSI uses a different primitive vocabulary. In RSI, a horizon is not a place where physics ends. It is a place where the external recursion accounting ends, meaning the last resolved interface for the external solver. The draft uses the phrase black shell horizon, and I will keep it because it is more precise than event horizon in the RSI context. Black shell horizon definition. A black shell horizon is the last resolved shell for an exterior accounting context defined by the existence gate as evaluated externally. A compact operational definition is the horizon radius RH is the last shell where the exteriorly evaluated reaches the gate threshold SRH equal to 1 using the exterior anchor plane mapping in EQ. 1. This definition encodes 3 RSI commitments at once. Horizons are gate statements, not singularities. The horizon is defined relative to an accounting frame, external evaluation, not as an absolute ontological edge. I do not propagate outward from unresolved layers. If the interface is not resolved in the external accounting, the external solver does not claim a resolved description past it. Flagship observational anchor, horizon shadows and event horizon telescope images. If I want a modern observational anchor for the RSI horizon posture, I use the event horizon telescope shadow images. They are not a complete test of RSI by themselves, but they are a widely recognized empirical object that makes the phrase black shell horizon feel like physics rather than philosophy. In RSI terms, a horizon is not a singularity. It is the last externally resolved interface where the gate evaluation remains meaningful. Near that last resolved interface, stability gradients are extreme. Wavefront imbalance becomes strong, and lensing becomes correspondingly strong. The ring-like brightness structure is consistent with near-interface path structure, where many photon trajectories are bent into the observer's line of sight, while others are excluded by the last resolved boundary. I am not claiming an image proves the full theory. I am claiming something narrower and testable. Robust horizon shadow signatures are consistent with the RSI posture that horizons are last resolved stability boundaries, not required singularities, why infinite redshift is not a required physical object. In legacy GR language, a horizon is often described as an infinite redshift surface for an external observer. RSI does not require an infinity because the latter is finite. In the RSI diagnostic language part 12, redshift is a stability mismatch. SOBs, S source Z equal to source, EQ, 18. That implies, so if an emission context approaches a last resolved shell, the source approaches the threshold value associated with that shell in the external accounting. The redshift can grow large as the ratio grows, but RSI does not require it to become infinite because the latter does not permit an infinite accumulation of resolved shells. The accumulation is bounded by the finite ladder depth and by the fact that past the horizon the external solver stops propagating. This is one of the places where the Helios Tripp ladder matters physically. It turns infinite into bounded but extreme, which is an empirical posture rather than an asymptote you can never test. 1 plus Z equal to sobs dot S source. Extreme collapse as a solver statement. RSI does not deny that collapse can be extreme. It denies that my external description must include a point singularity. The RSI solver statement is, collapse continues until the external evaluation reaches the last resolved interface. At that interface, the external evaluation reaches the gate threshold. Past that interface, the external solver does not claim a resolved geometry or a resolved pacing map. If I want to talk about the interior, RSI forces me to admit that I am switching to a different accounting context. I cannot use external shells to describe interior structure as if nothing changed. This is what I mean by no singularity. The interior is not denied. It is declared not externally resolved by the same ladder that produces horizons in the first place. Nested horizons, stars, compact objects, and black shells. A useful way to prevent horizon talk from drifting into myth is to treat horizons as nested system boundaries. A star is a system with a boundary. A neutron star is a system with a tighter boundary and a different closure balance. A black shell object is a system whose exterior accounting reaches a last resolved interface. In RSI language, the shared structure is a declared system boundary, an interface geometry carrier AP for the exterior accounting, a gate evaluation for existence, EQ, 1, and a change posture that tells me whether the system can persist or must reconfigure, EQ, 5, plus engine closure when needed. So I can talk about event horizons without making them metaphysical. A horizon is a boundary where the external solve stops being a resolved map. Cosmological horizons and Tripp limited recursion. The same logic applies at the largest scale. If Tripp is the practical upper bound of resolved recursion, then there is a natural cosmological horizon statement. Beyond the Tripp limited recursion span, resolved interaction is not a meaningful solver concept in the RSI primitive layer, so observational horizons are not just instrumental limitations. They are expected structural boundaries. This does not mean I cannot observe anything beyond a distance, because photons can still arrive. It means that the kind of stable, reportable interactions that define systems, memberships, and closure cannot be extended arbitrarily beyond the ladder. The lattice itself is bounded in resolved depth. 13.4 Cosmology Scaffold, what the early universe means under RSI primitives. Now I build the cosmology scaffold. I am not going to write a full cosmology model in this primer, but I am going to define what the words mean in RSI terms so we do not drift. In legacy cosmology, the early universe is described in terms of an expanding metric, inflation fields, thermal histories, and a sequence of phase transitions. In RSI, I can discuss those overlays later, but the primitive picture is different. RSI describes the early universe as the emergence and propagation of resolved interfaces and identities inside a bounded recursion ladder. I treat it as 4 stages, each stated as a solver posture rather than a metaphor. Stage 0, pre-anchored background, Tripp dominant context. In the origin story that motivated this project, the pre-Big Bang context is effectively flat geometry to us, and it is Tripp scale everywhere. I interpret that as a pre-anchored regime where there are no localized anchors in the RSI sense that would define stable, reportable physics the way we experience it. Operationally, it means the ledger exists as a background condition, but stable identities, anchors with defined EAT, a boundary, are not formed as localized closures, so our familiar skate evaluations that depend on a meaningful interface geometry are not yet producing a universe of discrete systems. This is the sense in which it is so resolved. It is not physics for us. There is no stable boundary language that produces atoms, stars, and clocks as persistent systems. The solver is not yet producing the discrete lattice we inhabit. Stage 1, corridor emergence, overlap pockets form. The next step is the key RSI mechanism that is not a standard chapter title in legacy cosmology, overlap corridors. In RSI, the difference between a shell and a corridor is not cosmetic. A corridor is a restricted overlap interface where 2 regions of recursion interact through a localized pocket, rather than a full isotropic interface. Operationally, a corridor pocket is where the effective interface area is small compared to a full shell carrier. This matters because the existence gate is equal to EAAP EQ, 1. If the effective interface is small enough relative to the available EAT that interface, the gate can cross threshold locally, even if nothing like that existed in the uniform background. This is also the clean place to say what effective interface means in RSI language, without violating geometry discipline. In corridor regimes, I do not write APEFF. I write an explicit effective interface area in math mode, APEF, because it is not a new primitive. It is the correct geometry carrier for the pocket. So I describe corridor emergence as localized overlap pockets form in the pre-anchored background, creating restricted interfaces APF, on which the existence gate can be satisfied locally. This is where the capture corridor intuition from the planet -9 alternate story belongs. In the solar system story, a corridor between 2 systems can create enough closure to capture or to reallocate membership. In the cosmology story, corridor pockets can create the first anchors. Stage 2, anchor nucleation, the first admitted identity. The anchor nucleation event is the first time the existence gate produces a stable, reportable identity in a way that defines the beginning of our physics. In RSI terms, it is the first local configuration where an anchor budget EII is defined at a boundary EQ3 posture with the boundary layer condition. The interface geometry is defined by a corridor pocket AP, F, and the gate sequel to EAE reaches the admission threshold EQ1. A simple way to remember the threshold condition is to rewrite EQ1 at the gate boundary. If admission occurs at sequel to 1, then the condition is EA equal to AP, gate boundary form of EQ1. In corridor form, the same sentence becomes, admission occurs when E matches the effective pocket interface, APF. I am not inventing a new equation. I am applying the existing gate condition to the correct interface. This is why I treat the Big Bang not as a literal explosion of matter into pre-existing space, but as an anchor nucleation event that makes geometry and stable identity language meaningful at scale. Once the first anchor exists, the universe is no longer flat Tripp everywhere, it becomes a lattice that can propagate. Stage 3, rapid layer propagation, what inflation means in RSI posture. Legacy inflation is a mathematical mechanism used to solve specific cosmological problems. RSI does not need to import the inflation field ontology at the primitive level to say something structurally similar happened. In RSI language, the immediate post-nucleation phase is naturally a rapid recursion layer propagation phase. New resolved shells become available as the lattice propagates outward. The effective geometry carriers AP update as shells are added. And the diagnostic observables, redshift, pacing differentials, lensing structure, become meaningful because there is now a stable ladder across which a signal can move. If I want a single RSI sentence for what inflation is trying to capture, it is a rapid opening of resolved recursion layers that makes a large, coherent, reportable stability network available early. I'm not claiming the detailed legacy inflation field is wrong. I'm saying RSI can express the structural necessity without changing primitives. The lattice must become large and coherent quickly if it is to produce the observational coherence we see. Stage 4, system formation as local closure. Atoms to galaxies are the same story. Once the latter exists and shells propagate, everything else is repetition of the same solver posture at different scales. Atoms, stars, galaxies, and clusters are not separate categories in RSI. They are all local closure solutions. They are admitted by existence, meaning sclears on their relevant interfaces. They persist or change according to decanned engine closure. They allocate membership by multi-anchor closure, EQ10, which is why system boundaries are decidable rather than inferred only by long arcs. This is where the Helios Tripp ladder becomes practical again. A galaxy cluster is not bigger than RSI. It is a set of identities inside a bounded recursion ladder. A proton is not too small. It is an identity inside the same ladder, with Helios bounding the smallest resolved interface in the external accounting. 13.5, where the Big Bang anchor story lives in this scaffold. I want to explicitly locate the Big Bang in the RSI story, because drift happens when the story is left implicit. In RSI, the Big Bang is not primarily a statement about a temperature or an equation of state. Those are overlay details. The Big Bang is primarily a statement about the first large-scale anchor nucleation. So I place it here. 1. A corridor pocket forms in the pre-anchored background. 2. The pocket defines an effective interface area APF, small enough that the existence gate can be satisfied locally. 3. Once reaches threshold, an anchor exists. 4. Once an anchor exists, the lattice can propagate and build shells, meaning the universe of stable systems begins. This is also the clean place to restate the arrows after solve posture from part 6, but at cosmological scale. In legacy cosmology, we often talk as if the early universe is determined by differential equations that evolve forward and create structures as a consequence. In RSI, the posture is inverted. Structure exists when the gates admit it. Once it exists, our arrows and evolution equations are maps of the already admitted closure, not the cause of the admission. When I draw arrows in this book, I mean directionality indicators, verdict arrows. An overlay way to visualize ledger imbalance after the scalar verdict is already computed, not a primitive vector force law. So the Big Bang is the first admission event at scale, and the rest of cosmic evolution is a sequence of admitted closures and deterministic transitions inside the ladder. How the universe came from a point becomes a solvable sentence. A common failure mode in cosmology discussion is to treat a point as a literal geometric point and then get trapped in singularity talk. RSI gives me a different sentence. In RSI, the point is the first admitted anchor interface, meaning the first resolved boundary on which EQ1 can be applied for a large-scale system. That boundary can be extremely small relative to what comes later, but it is not a mathematical zero, and it is not a claim that all future structure was literally located at a Euclidean point in an already existing space. The solvable RSI reading is, the first anchor is a localized admitted interface. Once admitted, the lattice propagates layers, stage 3. The growth of available resolved interface produces what legacy calls expansion, but RSI treats it as recursion layer propagation and context formation. This is why RSI can talk about a point origin without requiring a singular point. The origin is an anchor admission event, not a coordinate artifact. What pre-Big Bang math means in RSI terms. Tier 1 content here is simple and strict. The gate exists, the effective interface exists, and I can ask whether a corridor pocket can satisfy the admission condition. If I can specify a corridor pocket with effective interface APEF and specify an anchor budget, ETH can localize at that interface, then EQ1 gives a deterministic admission criterion. S equal to EAAP, EAEF. Anchor nucleation occurs when S crosses the threshold, meaning when E matches or exceeds the effective interface scale. Again, this is not a new law. It is EQ1 applied to the correct interface. The further step, which belongs to the Mathematica model rather than this primer, is to connect that criterion to pacing. If I want to talk about when, in an overlay sense, I wrote pacing through the engine and boundary time, EQs 6 and 7, the important posture is that nothing in this requires a probabilistic miracle. The admission is a deterministic threshold crossing, given a deterministic corridor configuration. That is the core claim. Pre-Big Bang modeling is corridor threshold modeling, not metaphysical guessing. 13.6. What RSI predicts structurally at cosmological scale before fine calibration? Now I state the structural predictions that do not require fine-tuning. These are the things that follow from the primitives themselves, and they are what I would put on a slide for an educated audience. I group them into 5 families. Prediction family 1. Bounded recursion implies bounded extremes. If the latter is bounded by Elios and Tripp, then I should not require singularities as physical objects in any externally resolved regime. I should expect horizons as last resolved interfaces, both for extreme collapse, black shell horizons, and for cosmological reach, Tripp-limited recursion horizons. I should expect maximum achievable redshift and maximum pacing differentials in any externally resolved accounting, because infinite accumulation would contradict the bounded ladder. This does not mean infinite is forbidden in mathematics. It means infinite is not required in the physical solver. Prediction family 2, redshift, dilation, and lensing are mutually constraining diagnostics. If redshift and clock offsets are stability mismatch diagnostics, EQ9 and EQ18, and lensing is wavefront response to stability gradients, then I should be able to treat cosmic surveys as different projections of one underlying stability terrain. So RSI predicts, structurally, redshift maps should constrain the line of sight stability accumulation. Lensing maps should constrain the transverse stability gradient structure. Where both datasets exist, they should be mutually consistent under one ledger model or RSI fails. This is a practical prediction posture because it forces RSI to face data without inventing a new ontology for every mismatch. Overlay readout, Hubble regime as cumulative stability mismatch. In the small z regime where per-layer mismatches are small and roughly homogeneous on average, the net shift along a long line of sight is well approximated as an accumulation of many small s contributions. When observers translate that accumulated mismatch into the legacy distance and recession overlay, they report a Hubble-style linear law at low redshift. In RSI, I treat H0 and any similar fit parameter as a calibrated mapping coefficient between the cumulative stability mismatch readout and the measurement interface, pin per declared regime, not as a new primitive. If the mapping breaks in a given environment or method, that is not a license to add a new force. It is a prompt to recheck ledger completeness and interface choice. Prediction family 3, apparent missing mass is either missing ledger or wrong interface. In part 8, I already stated the honest RSI fork when lensing or dynamics imply more closure than luminous matter suggests. 1. I am missing anchor energy in the ledger input, meaning there are unaccounted identities or misallocated closure shares, EQ, 10, discipline. 2. I've used the wrong geometry carrier for the interaction interface, meaning I treated a corridor regime as a shell regime or vice versa. So RSI predicts that any dark matter-like phenomenon will show up as a mismatch between observed stability diagnostics, lensing, redshift, pacing, and the modeled ledger inputs under the correct interface choice. The key structural difference from some legacy narratives is that RSI does not treat missing mass as automatically implying a new particle species. It treats it as a ledger accounting mismatch first. That is falsifiable because it forces me to produce an allocation explanation or admit failure. Prediction family 4, cosmic structure as corridor network topology. If corridor pockets are the mechanism for anchor nucleation and for membership reallocation, then cosmic structure should naturally look like a network of corridors and overlap pockets across scales. I am not claiming RSI invented the cosmic web observation. I am claiming RSI has a primitive mechanism that naturally produces web-like topology. Local pockets admit as anchors. Edges between anchors are corridor-like interfaces where closure flows. And stable structures form where the lattice admits persistent closure. So RSI predicts that webness is not an accident of initial conditions alone. It is a generic outcome of corridor-mediated closure in a bounded recursion ladder. Prediction family 5. Cosmic acceleration narratives should be testable as stability terrain evolution. Legacy cosmology often treats late-time acceleration as evidence for dark energy or a cosmological constant. RSI does not accept hidden negative pressure reservoirs as a primitive fix. The ledger must remain explicit and positive, EQ, 4. So RSI predicts that if something like late-time acceleration is real observationally, it should be expressible as an evolution of the stability terrain and recursion layering, not as a new negative energy substance. Operationally, that means compare redshift data as stability accumulation, compare lensing as stability gradient structure, and test whether a consistent ledger and ladder model can reproduce both, without introducing hidden reservoirs. If I cannot do that, RSI fails this part of the cosmology story. I do not get to declare victory by redefining Tor or inventing a new geometry factor outside AP. 13.7. Speculative extensions, labeled as Tier 3. I end this chapter by naming two Tier 3 extensions that readers often ask about, and I label them clearly as inference, not theorem. Tier 3. Other universes and other ladders. If the ladder window is a bounded domain of resolved recursion for our universe, it is reasonable to ask whether there exist other ladder windows, meaning other contexts in which different stable closure networks exist. RSI does not prove this. RSI makes it conceptually coherent to discuss it without mysticism. Our universe is a system, and systems can exist within larger contexts. If that continues to be the right posture under data pressure, then other universes are not a fantasy, they are a plausible context inference. Tier 3, extra dimensions is a context language, not necessarily extra spatial axes. Legacy theories that add dimensions often succeed in math, but struggle to explain what the picture means. RSI offers a different interpretive possibility. Some of what we call extra dimensions could be context layers and recursion horizons, meaning degrees of freedom that are real in a larger accounting but not resolved in our accounting. This is not a claim that extra spatial axes literally exist. It is a claim that context dependence and bounded resolution can produce the same phenomenology people are trying to describe with dimension language. I include this here only to prevent drift. If I speculate, I label it. The solver itself remains Tier 1. 13.8. What this part established. I define the Elios-Tripp ladder as the bounded recursion window in which RSI's gates are meaningful. Elios is the minimal resolved interface for external accounting, no required singularities, and Tripp is the practical upper bound of resolved interaction, no infinite range resolved recursion. I defined horizons as stability boundaries. A black shell horizon is the last externally resolved shell defined by the existence gate threshold evaluation, not a singularity. I gave a cosmology scaffold that defines early universe in RSI primitives, pre-anchored background, corridor emergence, anchor nucleation, rapid layer propagation, and then system formation as local closure at all scales. I placed the Big Bang story as an anchor nucleation event triggered by a corridor to anchor transition, which is the first large-scale admission event for stable reportable physics. I tiered cosmology claims explicitly: Tier 1 derived, Tier 2 interpretation, Tier 3 speculation, so the reader can separate what is solved from what is inferred. I stated structural predictions that follow before fine calibration, bounded extremes, mutually constraining diagnostics, redshift, dilation, lensing, accounting first interpretation of missing mass signatures, corridor network topology for structure, and testable stability terrain evolution in place of hidden reservoirs. I added a concrete modern observational anchor to keep the horizon discussion grounded. Event horizon telescope, horizon shadow images are consistent with the RSI posture that horizons are last resolved interfaces, not required singularities. I connected the low Z Hubble regime to cumulative stability mismatch explicitly as an overlay readout, with H0 treated as a calibrated mapping coefficient rather than a new primitive. 13.9. Next, we examine the solver checklist. Part 14 is the practical chapter. I will turn the solver posture into a working checklist for allocation and prediction, how I decide what belongs to what, how I write an RSI solve in sparse data regimes, and what easy wins look like, meaning predictions that can be tested without building a full numerical cosmology first. 14. Part 14, practical workflow, application gallery, and prediction menu. Part 13 ended with the bridge. I want to honor directly this is the practical chapter. I am going to turn the solver posture into something I can hand to a working scientist or engineer and say, run this on a system and tell me what you get. I am not asking anyone to abandon legacy physics here. I am doing something more conservative and more useful. I am specifying a deterministic workflow that decides system membership and stability as verdicts, then uses legacy tools as overlays only after the verdict is established. The practical goal of this chapter is not to impress anyone with philosophy. It is to prevent drift. If I can standardize the way I declare a system, choose geometry, build the ledger, compute gates, allocate partners, and report outcomes, then I can test RSI against data without reinterpreting the rules every time I hit a hard case. So I will deliver 5 things. 4. I give an application gallery across life and across scale, with the same solve posture repeated. 5. I list an easy win prediction menu and a falsification posture, meaning tests that do not require building a full numerical cosmology first, and clear criteria for when RSI fails. 14.1. The RSI solve card, the minimum report that prevents drift. Every RSI solve, no matter the domain, gets reported using the same card. If a solve cannot be written on this card, it is not ready to claim a result. I keep this strict because RSI is a unification attempt, and unification only works if the same steps recur across domains. Solve card A, declaration. System statement, what is the configuration and what is the question? Exam. Ples. Is object X a member of system Y, or does this configuration hold, or must it transition? Boundary statement, what boundary is being used for the verdict? This matters because sys evaluated on a boundary interface, EQ1. Timescale statement, what timescale the verdict is meant to apply to, short, medium, long relative to the system. Solve card B, anchored identities and edges. If I want a graph picture, each anchored identity is an identity node, and each coupling interface I declare is an edge. Anchors, list the identities treated as anchors in this solve. Edges, list the coupling interfaces that define the lattice for this solve. Open or closed, state whether the ledger is treated as closed on the timescale. Of interest. If open, State what flux is being ignored. Solve card C, geometry carrier selection. AP choice for each edge. State whether the interface is shell-like or corridor-like. Shell, use the spherical mapping when appropriate. EQ, S4 AP of R. Corridor, use an effective interface area APE. E, when the geometry is an overlap. Pocket. I do not write APEF because AP already contains a subscript. This section exists to enforce the geometry doctrine, distance and area scaling live inside AP, and I do not patch mismatches by weakening to a distance or encoding distance into DE. Solve card D, ledger build. Field budget, compute EF using EQ, 2, EF equal to TD. Anchor budget, specify EL lawfully. Boundary identity, identity counting, or multi-anchor closure posture. Positivity check, state the ledger explicitly. SE equal to EF plus EA, EQ. Hidden reservoirs, 4, no. Solve card E, gates, in order. Existence gate, compute S equal to EA AP, EQ, 1, on the declared interface. This. Answers exist now at that boundary. Change gate, compute DC equal to EF, EA, EQ, 5, and state whether it is in the stable band or beyond threshold. This answers will transition. I do not swap the gate order. If the configuration is not admitted, I do not claim long-run behavior. Solve card F, engine and channels, only when needed. If the solve requires pacing, rates, or allowed versus forbidden channel decisions, I close DC through the engine. K equal to X KCH theta DC. EFDC equal to KBT EQ 7, EQ 6, Part 14, Practical Workflow, Application Gallery, and Prediction Menu. Channel List, Weights KCH, Coherence Gate 6, Boundary Pacing Presumptions. Solve card G, Multi-Anchor Allocation and Membership. If more than one partner participates, I do not split energy by hand. I use multi-anchor closure. EA equal to sigma, 0 Guatemalan Quetzals DC, EQ, 10. I then report membership and allocation explicitly next subsection. Solve card H, verdict statement. I provide a final one-paragraph verdict that includes 1. Interface declaration, computed SAND whether it is above threshold, computed D and whether it is in band or beyond threshold. If multi-anchor, the share readout, EQ. 4 pesos ledger share, and the stated kill test that would force revision. Solve card WA, overlay reporting, arrows after solve. If I decide to draw directionality indicators, verdict arrows, I do it after the scalar solve. I do not let an arrow field decide admission or membership. Vectors in legacy physics are useful overlay representations for directionality and magnitude, but in RSI, the solver yields scalar stability and imbalance. Then I report directionality indicators as a reporting layer. So I report which scalar, S, the arrow is derived from, for example, stability gradient surrogate, imbalance gradient surrogate, which overlay convention I am using to map it into a visual arrow field, and the limitations of that overlay. If I must compare to a legacy force direction picture, I say that explicitly. I report directionality indicator, verdict arrow, direction S toward increasing stability, or toward the subconfiguration where DCIS approaching threshold, depending on whether I am mapping motion or mapping transition. I then use legacy vector tools to render the directionality indicators, verdict arrows, as a human map. But I do not let the arrow field decide membership. Quick compute validation cards, 1 per domain. I keep a tiny deck of pass-fail cards that I can run quickly before I do any full modeling. These are not meant to be complete derivations, and they are not replacements for the full solve card. They are drift detectors that tell me whether I am about to misapply geometry, conflate gates, or smuggle a hidden mapping constant into a story. To avoid confusion with the solve card letter labels above, A through I label these quick compute cards by domain tag, G, gravity, E, electromagnetism, S, strong, and W, weak. Each card includes an explicit audit link, line into Appendix A, so I can jump straight to the audited quick check capsule that justifies the shortcut. Card G, gravity, lab scale redshift sanity, pound Rebka class. Purpose, confirm that my gravity mapping and my redshift diagnostic produce the correct sign and order of magnitude before I touch any exotic application. Carrier, shell dilution, so I use AP in the existence gate with the spherical carrier posture in EQ, S4 AP of R. Minimum equation path, I keep the gate discipline explicit, S equal to EA AP, EQ, 1. Sets the interface verdict language, and the diagnostic mapping uses the redshift relation, EQ, 18, with the Earth calibration posture pinned in the gravity supplement, for example, EQ. S4 degrees Celsius Earth, or EQ, S4 GCal. Kill test, wrong sign, or a result that is orders of magnitude off at the 1015 scale for a lab height path. If I miss that by a lot, I do not proceed. I revisit geometry in the stated mapping regime, audit link Appendix A SEC, A5, card E electromagnetism intensity check, inverse square scaling as an interface. Purpose, confirm that the shell carrier produces the correct distance scaling for the legacy Coulomb force overlay after one calibration pin, without claiming a literal 1 degree Celsius tabletop configuration. Carrier, shell dilution again. So APR, R2 via EQ, S4 AP of R, for fixed ledger scale EA, the existence ratio S equal to EA AP, EQ, 1, scales as 1 R2. Kill test. If having R does not multiply the reported interface intensity by 4 in this shell regime, then I have violated the geometry confinement doctrine somewhere, or I have changed the mapping regime without declaring it. Audit link Appendix A SEC A4 Card S Strong EQ 11 Exception discipline no shell dilution smuggled into confinement. Purpose confirm that I am using the one allowed geometry exception correctly. Strong is treated as a confinement and contact normalization interface, not as a far-field dilution carrier. Exception rule, only EQ 11 is allowed to carry an explicit R2 factor outside AP. In every other equation path, I keep all separation dependence inside AP. Kill test, any derivation that forces strong into AP as if it were a shell propagation law, or that introduces stray R or R2 factors outside AP in a non-EQ 11 context is a failed card. I treat it as a geometry drift, not as a parameter problem. Audit link Appendix A SEC A9 Card W weak, D-Kroll discipline and pacing closure weak is change gate closure, not a force. Purpose confirm that I am not conflating the existence gate S with the change gate DC, and that any timing claim is explicitly closed through the engine when pacing matters. Minimum equation path, I compute the ratio verdict DC equal to EF/EA EQ 5. If a rate or half-life statement is being made, I close the pacing through the engine channel sum EQ 6 and the pacing relation EQ 7 with channels and coherence factors declared rather than implied. Part 14, Practical Workflow, Application Gallery and Prediction Menu. Kill test, a timing claim that has no declared channel list, or a claim that treats weak as a signed force-like field rather than a closure and pacing verdict, is not audit-ready. Audit link, Appendix A SEC A6 14.2 Allocation and Membership as Explicit Readouts. EQ 10 gives me a lawful multi-anchor allocation posture. The normalized share for partner I is Q1, S equal to sigma, omicron, EQ, 4 pesos ledger share. I treat that share as the membership meter. If an identity has a stable, non-negligible share across the declared boundary and timescale, it is a member of the system. If it has a vanishing share, it is not a member. If the share spikes only under a corridor window or transient interaction geometry, it is a transient member. This is a practical definition. It is not a vibe, it is a computed readout. It is also the best way I know to stop myself from drifting into story mode when I am looking at a multi-body configuration. Ledger share is the membership meter. In the multi-anchor posture, I do not need to invent a new metaphysical rule for what counts as belonging. I compute the share, and I report it. I interpret the share as follows. IFF is stable and non-negligible under the declared boundary and timescale. I treat identity I as a member. If F is near 0, I treat identity I as non-member, even if it is nearby in some geometric sense. If F spikes during a corridor window or under a transient edge configuration, I treat identity I as a transient member. I do not claim that membership is a binary metaphysical state. I claim it as a readout under a declared solve. Part 14, Practical Workflow, Application Gallery and Prediction Menu. Membership categories. To keep the language clean, I use 3 categories in practice. Persistent member F stays non-negligible across the declared observation. Window. Transient member F spikes under corridor-like overlap or short-lived edges, then falls back. Non-member perturber F stays near 0, even if the object produces a measurable perturbation in a legacy trajectory overlay. This is not semantic decoration. It matters for prediction, because persistent members have stable allocation shares and stable gate posture, while transients have structured share windows that should be observable as prediction signatures. Why this matters for prediction. Many legacy problems that look like missing mass or unmodeled perturbation problems are, under RSI, membership and allocation problems. If I misclassify a transient member as a persistent member, I will be forced to retune constants or invent a new object to save the story. If I classify it correctly, I will predict structured windows where the perturbation signature appears and disappears. So I treat allocation and membership as explicit readouts, and I report them in any claim that involves more than one anchor. 14.3 Sparse Data Workflow, how I run RSI when the data are incomplete. RSI is supposed to be most valuable where the data are sparse and incomplete. That is where many traditional approaches drift into guesswork or into overfitting. So here is the workflow I actually use. Step 1. Build competing system hypotheses. I do not start by forcing a single system narrative. I build competing hypotheses. Hypothesis A, identity X is a member of system Y. Hypothesis B, identity X is a transient member of system Y, corridor window, fly-through capture window. Hypothesis C, identity X is a non-member perturber, meaning it couples but does not belong. I do not change primitives between hypotheses. I keep the same ledger variables, the same gate order, and the same geometry doctrine. Step 2. Choose the geometry carrier per edge. I choose geometry per edge, not per story. If the interaction is shell-like, I use EQ S for AP of R. If the interaction is corridor-like, I use an effective interface area, and I declare Y. If I cannot justify the geometry carrier in one sentence, I treat the solve as not ready. Step 3. Compute gate verdicts and share readouts I compute. Set the boundary interfaces, EQ 1. Churned, whether it approaches threshold, EQ 5, with the stability band posture, and the multi-anchor allocation readout, EQ 10, if more than one partner matters. If the gate verdicts contradict basic observation, for example, I claim a configuration is not admitted even though it is manifestly stable, That is a geometry or mapping error, and I do not proceed. Step 4. Extract discriminating predictions. I do not claim a result just because I can compute a gate. I extract predictions that discriminate the hypotheses. Share windows in time, boundary threshold crossings, structured changes in Kunder channel availability changes, redshift and lensing consistency checks if gravity overlay is involved. I state the kill test explicitly. What observation would force me to reject the hypothesis? Step 5. Carry uncertainty forward explicitly. If I do not know a mapping constant precisely, I do not hide that uncertainty. I carry it forward. I show the dependence of the verdict on the uncertain parameter. I do not retune it per example. Step 6. Update with new data without rewriting primitives. When new data arrives, I update the hypothesis assessment without rewriting primitives. I do not change T, D, A, P, S, or DC. If a hypothesis fails, it fails. I do not patch it by changing definitions. This is the operational meaning of determinism for me. The workflow is stable under new data pressure. 14.4 Application Gallery across life and scale. This gallery is not meant to replace full derivations. It is meant to show how I apply the same solve posture to very different systems. Case study 1, why an apple falls, and what else is happening while it falls. This is the simplest everyday case study, and it is also a good reminder that many events are multi-overlay interactions, even when we tell a single domain story. Declaration: the apple is an anchored identity. The earth is an anchored identity. The question is not does gravity exist? The question is does the apple remain a member of the branch support configuration, or does it transition into freefall motion? Dominant edges in geometry, gravity is the context edge. The relevant mapping is shell-like, so I use AP, EQ, S4, AP of R. Inside the existence gate, EQ, 1. The contact edge between the apple and the branch is electromagnetic in character, molecular bonds, and frictional contact. Strong is present only as the reason the matter has rigidity. Weak is present only as slow compositional drift on long time scales. Gate verdict: the apple exists as a stable identity. The question is the stability of the support configuration. When the electromagnetic contact edge can no longer maintain the necessary closure, the configuration transitions. That transition is a change gate statement for the support microconfiguration, even though the apple itself is still admitted. Reporting: if I draw directionality indicators, verdict arrows, I draw them after the solve. The arrow I draw in a falling picture is an overlay, the underlying. RSI statement is the gate verdict and the change gate closure. The support edge fails and the system transitions. Case study 2, throwing a football through air. A football in flight is a clean multi-overlay case study at everyday scale. Declaration: the football is an anchored identity. The earth is an anchored identity. The air is a distributed medium that participates in coupling edges. The question is, does the football remain a stable identity and a member of the local earth system during flight? And what are the dominant verdict drivers? Dominant edges in geometry. Gravity is shell-like through AP. Aerodynamic drag is electromagnetic, meaning it is the closure consequence of collisions and shear interactions between the football surface and air molecules. Spin-induced curvature is not a new force. It is a change in how the air coupling edges distribute around the ball, meaning the effective edge imbalance changes as the ball spins. Strong holds the football's material identity under stress. Weak is irrelevant on the flight timescale. Gate and allocation posture. The football is admitted as an identity. The motion path is a legacy overlay. In RSI terms, the relevant practical statement is that D stays far from threshold for the football identity on the flight timescale, and the membership share remains non-negligible for the Earth football system. The air coupling produces energy exchange, so the ledger is open unless I declare a closed subsystem. Reporting: a legacy trajectory solver is still useful as an overlay. RSI does not forbid it. RSI insists I declare the boundaries and the ledger posture first. Case study 3, static electricity, a balloon and hair. This is an electromagnetic overlay case that is familiar and easy to misread if I mix force and potential energy in my mental picture. Declaration: the balloon and the hair are anchored identities. The question is whether the balloon-hair configuration produces a stable coupling and a measurable overlay effect at the interface. Dominant edges in geometry. This is an electromagnetic overlay case. The key RSI discipline is that the sign is a closure orientation stored in the tane side allocation in engine terms, EQS, 6 and 10. Geometry remains in AP, for the shell-like interaction scale if I am modeling it macroscopically. Gate posture: if the coupling is admitted, I report SAT the relevant boundary interface. If the coupling breaks, balloon releases, I report it as a change gate event. The interface transitions from admitted to non-admitted under the declared boundary. Reporting: I can draw directionality indicators, verdict arrows to match the legacy field direction picture, but that is a reporting overlay, not the solve. Case study 4, chemical reaction and heat release. This is a good reminder that EF and E are not metaphors. They are energy ledger quantities. Declaration: reactants, products, and environment are identities in a declared system boundary. The question is whether the reaction proceeds under the boundary conditions, and what the pacing looks like. Gate posture: if the reaction proceeds, DC must be beyond threshold under the declared channel availability. If it does not proceed, DC remains in band. The existence gate tells me which identities are admitted at the boundary. The change gate tells me which configurations transition. Engine posture: if the pacing matters, reaction rates, I close DC through the engine and I declare channels rather than hiding them. Reporting: heat release is a ledger exchange. If I do not declare the boundary as open, I will misaccount energy. So I explicitly state whether the system is open. Case study 5, a nucleus that is stable in one context and unstable in another. This is a micro-scale case study that shows why weak overlay effects are change gate closure statements and why environment dependence is not a contradiction. Declaration: the nucleus is an anchored identity. The environment, electron shell state, ionization state, embedding lattice, changes what channels are available. The question is whether the nucleus remains stable or transitions, and what the decay pacing is. Gate posture: the nucleus exists. The transition timing changes because the engine channel sum changes, meaning K changes, and therefore the pacing statement in EQ7 changes. This is not mysticism, it is a channel availability statement. Reporting: I do not say weak forces the nucleus to decay, I say the change gate is closed under channel availability and pacing. If environment changes channels, timing changes. Case study 6, a star system, a fly-through, and a membership verdict. This is a case study where membership can be misread if I focus only on geometric proximity. Part 14, practical workflow. Declaration: a candidate object passes through a multi-body system. The question is whether it becomes a member, remains a transient, or stays a non-member perturber. Workflow: I evaluate existence and change for the candidate membership configuration, and I compute a share readout J, EQ, 4 pesos ledger share. If the share remains near zero even while trajectories appear close, I classify non-member perturber. If the share spikes only during a corridor interval and then falls, I classify transient member. If the share remains stable and the system stays in the stable band, I classify persistent member. Reporting: this is the practical power of the share readout. It tells me what belongs without requiring me to guess a narrative. Case study 7, a black shell horizon as a practical boundary choice. This is the boundary choice that keeps the horizon discussion from drifting into singularity stories. Declaration: the black shell boundary is the last resolved exterior interface for an external accounting observer. The question is not what happens at a singularity, the question is, what boundary do I use for an external solve, and what does the existence gate say at that interface? Geometry and gate posture: the exterior mapping is shell-like, so I use AP in S. The horizon is the last resolved exterior interface where the existence gate reaches the boundary threshold in the exterior accounting. Reporting: if I use legacy coordinates to draw a spacetime picture, that is an overlay. RSI's claim is about boundary verdicts on resolved interfaces. 14.5 Easy win prediction templates. This subsection is the practical reason RSI is worth building before a full 50,000 word expansion. These are prediction templates that can be tested with limited resources. I will list 8 templates. Each template is stated as a procedure, a predicted signature, and an observational check. Prediction menu, domain sorted quick cards, table form. Before I expand the 8 templates, I put the same idea in a compact menu table. I want the reader to see, at a glance, that RSI is willing to make hard numeric commitments and to attach kill tests to them. These are not meant to be the only tests. They are meant to be the quickest tests that touch multiple domains while enforcing the same discipline. Declare the Part 14, practical workflow, application gallery, and prediction menu. Interface: keep geometry inside AP, compute S and D in order, and then make a claim with a kill test. Inverse parameter hunts: what I calibrate and how I refuse to retune. An inverse hunt is what I do when I have a clean threshold observation and I want to pin a mapping coefficient once, then reuse it. I use a D equal to 1 crossing, or an equivalent crisp threshold, as the calibration anchor, and I treat the resulting constants as calibrated mappings between ledger primitives and measurement overlays, not as free knobs. Closure checklist table form. Template 1, membership verdict for a sparse arc object. Procedure: build competing hypotheses. Member, transient, non-member. Compute SAN day, then compute the ledger share FEQ, 4 pesos ledger share, for the candidate object under EQ. 10. Predicted signature: a member has stable non-negligible share. A transient has a share spike tied to a corridor window. A non-member stays near zero share. Check: as new astrometry arrives, the share classification should not flip randomly if the geometry carrier is chosen correctly. If it does flip, the hypothesis or the geometry claim is wrong. This is the template I want for outer solar system anomalies and capture corridor hypotheses. Template 2, corridor detection without seeing the corridor directly. Procedure: identify a system near a stability boundary where small perturbations cause large changes. Use RSI to predict that a corridor pocket must be active to explain repeated coherent deviations without requiring a new massive object. Predicted signature: a corridor pocket produces a periodic or quasi-periodic allocation reroute signature, shares change in a structured way during corridor windows, then relax. Check: look for correlated anomalies across multiple bodies that share the same corridor timing signature. If anomalies are uncorrelated, corridor explanation weakens. Template 3, redshift and lensing consistency as a stability terrain check. Procedure: treat redshift patterns as line-of-sight stability accumulation, Part 12, and lensing patterns as transverse stability gradients. Build a unified stability terrain for a system. Predicted signature: if the terrain model is correct, lensing and redshift diagnostics will be mutually consistent under one ledger input model. Large inconsistencies imply missing ledger inputs or wrong geometry carrier. Check: use existing survey datasets where both lensing and redshift information exist for the same region. Template 4, early warning signals for forced transitions. Procedure: identify a system that undergoes transitions, phase changes, collapse, disruption. Monitor a stability proxy and compute DEC under evolving boundary conditions. Track whether DEC approaches threshold. Predicted signature: there should be early warning signals. DC drifts toward threshold, coherence factors degrade, and engine channels change. Check. If transitions occur without any measurable drift in the computed gate posture under a correctly declared interface, then the model or the mapping regime is wrong. Template 5. Environment dependence of decay pacing. Procedure: pick a decay or capture process known to change with environment, ionization state, lattice embedding, electron availability. Compute decan channel availability under each environment. Close pacing through the engine. Predicted signature: timing shifts track channel availability changes through K. The identity remains admitted. The pacing changes. Check. If timing changes occur without any plausible channel difference, then my channel accounting is wrong. Template 6. One calibration pin, then reuse without retuning. Procedure: choose a crisp threshold observation. Pin the mapping constant once. Reuse it across related systems and scales without retuning. Predicted signature: predictions remain within stated tolerance under the same regime. If they fail, the failure should cluster by regime boundary, not by whim. Check. If I need a new constant per case to save results, then RSI has failed as a unification posture. Template 7. Composition change as a weak-driven stability correction. Procedure: in a system where composition change occurs, stellar burning, nuclear transmutation, decay chains, treat composition change as a weak-driven stability correction that shifts E and therefore DC. Track how the system moves through stability bands. Predicted signature: composition changes correlate with systematic changes in stability and transition timing. The system seeks a new stable configuration under the updated ledger. Check. If composition changes have no stability signature at all, then my mapping between composition and ledger is wrong. Template 8. Cross-domain event accounting in one card. Procedure: pick a complex event that involves multiple overlays, for example, a star wind, a planetary escape event, or a high-energy transient. Write one solve card that includes all relevant identities and edges. Keep gate order. Report S, DC, and allocations. Then report overlays. Predicted signature: cross-domain constraints should tighten predictions. For example, redshift diagnostics and lensing diagnostics should agree if gravity mapping is correct, and decay timing should be consistent with available channels if weak mapping is correct. Check. If the event can only be described by letting each domain tell an independent story with independent constants, then the unification posture is failing. 14.6 Falsification posture: how RSI fails cleanly. A unification attempt must fail cleanly, otherwise it is not science. So I state a 3-layer failure posture. I do not get to save the theory by redefining the primitives. If it fails layer 3, it fails. Failure layer 1, geometry error. If the prediction fails, the first question I ask is geometry. Did I choose the wrong interface, shell versus corridor? Did I violate the geometry confinement doctrine? Did I misuse AP outside its declared regime? Did I accidentally place separation dependence outside AP in a non-EQ 11 context? If geometry is wrong, the fix is to correct geometry, not to invent a new constant. Failure layer 2, ledger omission. If geometry is clean, I ask whether I omitted ledger terms, missing identities, missing coupling edges, missing open boundary flux, misallocated closure shares violating EQ 10 discipline, sing channel terms when pacing matters, violating the engine posture in EQ 6 and EQ 7. If I omitted ledger terms, the fix is to add them explicitly and rerun. Failure layer 3, model failure. If geometry is clean and the ledger is complete and the prediction still fails, then RSI has failed for that domain or that regime. I do not get to save it by redefining Tor by hiding negative energy reservoirs. Model failure can take several forms. The gate definitions do not track stability correctly. The allocation closure does not match observed membership behavior, or the stability diagnostic Z, EQ 9, and EQ 18 is not mapping observables consistently, or the strong exception rule, EQ 11, is not isolating confinement behavior correctly. If it fails layer 3, I record the failure, and I revise. I do not rewrite history. 14.7 Reporting Standard, what I include in every RSI claim. To keep RSI auditable, I enforce a reporting standard. It has 4 rules designed to stop me from drifting into story mode. 2. Every claim declares geometry. I state the AP used, and if it is corridor-like, I state that it is an effective interface and why. 3. Every multi-body claim reports allocation. If more than one partner matters, I report the closure share readout, EQ, 4 pesos ledger share, rather than splitting budgets by hand. 4. Every bold interpretation is tiered. Tier 1 is gate math and ledger accounting. Tier 2 is physical interpretation consistent with the math. Tier 3 is speculation labeled as such. This prevents cosmology drift. These rules are enough to make the theory testable even by someone who disagrees with my interpretation. 14.8 What this part established. I converted RSI from a narrative into a repeatable workflow by providing a standardized solve card, declarations, geometry carriers, ledger build, gates in order, engine closure when needed, allocation, and a verdict statement. I defined membership as an allocation readout under multi-anchor closure, EQ 10, and tied the practical meter directly to the normalized share equation, EQ, 4 pesos ledger share. I provided a sparse data hypothesis workflow that uses RSI to decide membership and stability earlier than trajectory first approaches, while staying inside the geometry doctrine and gate order. I added an across-life application gallery to show that events are multi-relay interactions even when we tell a single domain story, and I kept the same solve posture in each case study. I expanded the easy win prediction menu to include membership verdicts, corridor detection, redshift lensing consistency, early warning signals for transitions, environment dependence of decay, calibration reuse, decay family directionality, and cross-domain event accounting. I stated a falsification protocol and reporting standard that make RSI auditable, check geometry, then ledger completeness, then accept model failure when both are clean. 14.9 Solver Summary and Equation List. Part 15 closes the primer. I will provide a compact solver summary, an explicit end-to-end checklist that matches the solve card, and a clean equation list and symbol reminder that makes this document usable as a standalone reference before we expand into the full manuscript build. Part 15 Solver Summary and Reference Index. This primer has one job. If I hand it to a technically educated reader, they should be able to I. Understand what RSI is claiming, T.E. see exactly which equations are being used, T. reproduce the solver posture on a real system, and IV. know what would count as success or failure. I end the primer in the most practical way I know how. I tell the reader how to use this book without drifting. I restate the solver as a printable checklist. I restate what a system lattice is in RSI terms. I give a short dictionary back to legacy language so a reader can keep their bearings. I give an equation index for everything the standalone document relies on. I give a compact symbol reminder. I restate my falsifiability commitments in plain language. 15.1 How to use this book. To use this intro well, I keep part 14 open next to me as the working card deck, inputs, geometry choice, gate order, and allocation readouts, and I treat Appendix A as the audit trail for any equation path claim I intend to lean on. Appendix B is the implementation posture, Appendix C is applied case studies, and Appendix D is the forward test and open problem ledger. If I follow that loop, I do not mistake overlays, constants, vectors, and time coordinates for primitives, and I can tell exactly which claim tier a sentence belongs to. I wrote this as an introduction. It is not the full manuscript, and it is not a complete replacement of every legacy derivation. It is a baseline that keeps the conceptual picture and the math posture stable so the larger program can expand without contradiction. There are 3 ways to read it depending on what the reader wants. Path A, concept first, the universe picture. If the reader wants the global picture and the posture shift, I recommend Parts 1 to 3 for the thesis and the universe map language. Parts 12 to 13 for unification and the Helios to Tripp ladder picture. Part 14 for how RSI turns into an actual workflow. And this part 15 as the reference card. Path B, solver first, how to run RSI. If the reader wants to test RSI on a system immediately, I recommend Part 6, gates and thresholds. Part 5 for the macro adjudication benchmark with a unit coherence check in a sparse data lattice. Part 14, solve card, membership, prediction templates. And this part 15, solver checklist, equation index, symbol reference. Path C, domains first, how RSI overlays legacy fields. If the reader wants to compare RSI to legacy physics domain by domain, I recommend Parts 8 to 11, gravity, EM, strong, weak overlays. Part 12, how the 4 overlays become one picture. Then Part 14, application gallery to see the overlays interact in one event. Main text versus appendices. The main text is written to be readable at a conference. The appendices are where I place the hard math, the model architecture, and the open problems. In the project plan, the appendices are structured like this. Appendix A, audited derivations only. No new claims without rederivation. Appendix B, Mathematica model documentation, invariance, and verification posture. 200C, cross-scale case studies, each with boundary, gate, overlay, verdict. Appendix D, open problems and speculative extensions, explicitly labeled as Tier 3. The reader should treat Appendix A and Appendix B as the engineering layer of RSI. The main text tells the story and shows how the solver is used. The appendices show how the solver is checked. 15.2. The RSI solver in one page. When I say RSI is a solver, I mean I can write a procedure that yields a verdict. This is that procedure. Step 0, declare the question, do not skip. I write one sentence that declares the verdict question and the boundary question. Examples. Is object X a persistent member of system Y? Does configuration C hold, or is it forced to transition? If it transitions, which channel class is open and what sets the pacing? If I cannot write this sentence, I'm not solving anything yet. Step 1. Declare the lattice, identity nodes, and edges I list. Anchored identities, identity nodes when I draw the lattice. Edges, which pairs or effective pairs actually couple for this solve. Whether the solve is treated as closed or open on the relevant timescale. Step 2. Choose the geometry carrier for each edge. I do not allow geometry to leak outside AP. I choose shell geometry when the coupling samples a full interface. Use EQ, S4 AP of R as the default spherical mapping, or corridor geometry when the coupling is an overlap pocket, meaning an effective interface area APF. I keep effective interfaces explicit by writing APF in math mode, because I want the reader to see that the geometry still lives in AP and nowhere else. In this project, macros RSI.text group subscripted symbols safely, so AP can be indexed without a TX error, but I still prefer the expanded form to reduce notation drift. Step 3, build the ledger explicitly. No hidden reservoirs, I compute. Field energy EEF using EQ. 2, EF equal to TDE. Anchor energy E lawfully. Boundary identity posture, identity counting posture, or multi-anchor closure posture. And I keep the ledger explicit and positive. SE equal to EF plus EA, EQ. 4, step 4, evaluate gates in order I evaluate. Existence first, S equal to EAAP, EQ. 1, change second. DC equal to EF, EA, EQ. 5, including the stable band and threshold posture already defined in the supplemental stubs. For example, EQ, S8 DC threshold, and EQ, S8 DC band. I do not swap these. If it is not admitted, I do not claim long-run behavior for that configuration. Step 5. Close change through the engine when pacing matters. If I need a rate, a half-life, a channel prediction, or a path selection, I close through the engine. K equal to X KCH theta DC. EFDC equal to K BT EQ 7, EQ 6. I report the channel list and the assumptions KCH theta BT. If I cannot report them, I do not claim a rate. Step 6. Apply multi-anchor closure for membership and allocation. If more than one partner matters, I do not split energy by hand. I apply EA equal to XQ theta DC EQ 10. Then I report partner allocation as a share readout using EQ, P4 ledger share, and I classify membership as persistent, transient, or non-member. Step 7. Output a verdict. I output one of the 4 verdicts and I name which gate triggered it. Not admitted, fails existence. Admitted but transient, exists now, force change. Admitted and persistent, stable band. Intruder-driven transition, allocation reroute pushes a threshold crossing. A print-ready checklist, copy to a lab notebook. I include this compact checklist because RSI only works if I keep myself honest about what I claimed in a solve. RSI solve checklist, printable, question and boundary stated in one sentence. Anchors listed, edges listed, closed or open declared. Geometry carrier chosen per edge, shell or corridor. No stray R outside AP. Ledger built EF, EQ, 2, EA, EQ, 3 or EQ, 8 or EQ, 10, SE, EQ, 4. Gates evaluated in order, S, EQ, 1, DC, EQ, 5. Band check, EQ, SADC band. If pacing is claimed, engine close and channels reported, EQS, 6 and 7. If multi-body allocation reported, EQ, 4 pesos ledger share, no hand splitting. Verdict stated in one line. Overlay arrows drawn afterward. If I am leaning on a derivation or flagship validation, I can point to the matching Part 14 card and an Appendix A audit trail, not just an intuition. 15.3. What I mean by a system lattice, one paragraph. A system lattice is a set of anchored identities connected by coupling interfaces, where each interface has a geometry carrier and each identity has an explicit ledger budget. The system is not defined by trajectories. The system is defined by closure. Whether the existence gate admits the configuration at the declared boundary, whether the change gate pushes the configuration toward transition, and how multi-anchor closure allocates ledger participation. Once the lattice verdict is computed, legacy arrows and trajectories become a map of an already admitted structure, not the cause of admission. 15.4 Quick Dictionary to Legacy Physics, Overlay Posture. I do not present RSI as an enemy of legacy physics. I treat legacy tools as overlays that describe stable regimes effectively. This is the dictionary posture I use. Force, legacy. A convenient overlay readout of stability gradients and closure rerouting, not a primitive. Field, legacy. An overlay description of how closure and geometry readouts vary over space, not a new substance. Potential energy, legacy, a bookkeeping overlay. RSI keeps bookkeeping. Explicit via sigma, EQ. 4. Constants, legacy, calibrated mapping coefficients between the RSI ledger primitives and measurement. Overlays, pinned once per regime and reused. They are not arbitrary tuning knobs. They fall out as consequences of the mapping. Curvature, legacy GR, an overlay on AP, mapping and stability pacing differences. RSI reads redshift and timing shifts through Z, EQ 9, and EQ 18. Vectors and trajectories, legacy vectors, encode directionality, and magnitude as an overlay representation. In RSI, I solve scalar stability and allocation first. Then I report directionality indicators, verdict arrows, as a readable map of the imbalance already encoded in the ledger. Time coordinates, legacy, a reporting overlay for sequencing. In RSI, I do not assume a privileged universal clock is required to decide what the system is. Quantum probability, legacy QM, QFT, a coarse-grained description of unresolved channel inputs. RSI treats gate outcomes as deterministic and uses the engine, EQS, 6 and 7, to express channel structure and pacing. Particles and mediators, legacy, stable closure modes and carrier signatures, meaning identities that persist as admitted lattice configurations. 15.5 Equation index for this standalone primer. This index lists the equations this primer relies on. I include both the Corey 12 equations and the supplemental derived relations used for calibration and interpretation. The expressions below are restated for quick reference, but the authoritative forms are the numbered equations in the intro-specific stubs file. When I want audited derivations rather than quick reference, I use Appendix A, where I lay out inputs, equation path, units checks, and explicit failure conditions for the flagship targets. Core 12 ledger and gates, and the intro canon continuations. EQ 1, existence gate, S equal to EA.AP. EQ 2, field energy, EF equal to TD. EQ 3, anchor energy, boundary identity, EF EA equal to T. DEQ 4, ledger closure, SE equal to EF plus EA. EQ 5, change gate, EF DC equal to EA. EQ 6, engine channel sum, K equal to X KCH theta DC. Part 15, solver summary and reference index. EQ 7, engine closed form, EF. D2 equal to KVT. EQ 8, identity counting posture, epsilon equal to dex sigma epsilon. EQ 9, stability shift diagnostic, Z equal to A's. EQ 10, multi-anchor closure and allocation. E1 equal to sigma QOD EQ 11, strong overlay magnitude law, the only allowed outside AP geometry. No equal to E to AP R2. R2. EQ 12, intro canon weak emergence note. Weak behavior is expressed through the change gate and engine and allocation structure, meaning EQ 5 and EQs 7 to 10. Key supplemental relations used in this primer EQ. 4 pesos ledger share readout. 0 Guatemalan quetzals, day, 00 des. EQ. S4 AP of R. Spherical anchor plane. APR equal to 4x2c, EQ. S4 Shrey's Earth reference pin. Surth equal to EAAP, Re equal to 1, EQ. S4T legacy, and EQ, S4T Earth, gravity calibration tie, T equal to GM Re, and T equal to 4 per 2c. EQ, S4 degrees Celsius Earth calibration for C. C equal to GM, 4 per 3, EQ, S4 GCal, general calibration relation, 4 per 2 FC equal to GM ref.ref. EQ, S6D at boundary, and EQ, S6EA equals T, boundary identity, and D, EA equal to T. Anchor equal to 1, D equal to 1, EQ, S8 DC threshold, and EQ, S8 DC band, change threshold in stable band, persistence criteria for DCUs throughout the stability parts. EQ, 18, source observer redshift form. Z equal to SOBS source, S source. 15.6, symbol reminder what I mean in one line each. This primer uses a small set of symbols repeatedly. I keep them here so the reader never has to guess. T, tension, energy per RSU layer J. Day, integer RSU layer count, dimensionless. EF, field energy, EF equal to TD, J. EA, anchor energy, J. With boundary identity, EA equal to T when D equal to 1. SE, explicit positive ledger sum, SE equal to EF plus EA. AP, anchor plane mapping, the geometry carrier, all distance and area scaling. Stays here. S, existence gate, S equal to EA AP. DC, change gate, DC equal to EF EA, with persistence determined by the stable band. And threshold posture, K, engine aggregate, channel weighted closure sum. KCH, channel weight for channel CH. Theta, orientation or coherence gate on partner contribution, signed or suppressing, depending on overlay. BT, boundary pacing scale used in engine closure. Q, partner contribution magnitude used in multi-anchor closure. U, accounted unit identity used in the identity counting posture. EQ, 8. Z, stability shift diagnostic, Z equal to SS. S source, source stability ratio used in the explicit observer form. EQ, 18. Text, safe text subscript helper, used for group subscripts like SOBs. NC, nuclear coupling density scale in the strong overlay. EQ, 11. R, effective nuclear separation interface for the strong overlay, not a macroscopic. Shell radius, C, calibrated geometry factor inside APR, equal to 4PR2C, pinned by reference. System. 15.7, my falsifiability commitments, what would force revision. I close the primer by restating the commitments that make RSI testable. I will not weaken with distance to patch a mismatch. If something weakens, with separation, I treat it as a geometry carrier issue in AP, or an allocation issue via EQ. 10. I will not encode distance into D. D is a layer count, not a radial coordinate. I will not hand-split EF or EN multi-body environments. I will use EQ, 10, and report shares using EQ. 4 pesos ledger share, 242. I will keep the ledger explicit and positive. I will not introduce negative energy reservoirs to make a story work. I will keep Sandy Crolls separate. If a result requires mixing existence and change, it is a failure of the solver posture. I will keep geometry outside AP, confined to the one canonical exception, EQ, 11, in the strong overlay. If I need more exceptions, the unification claim fails. If weak rates require irreducible probability as a primitive, rather than deterministic channel closure with coarse graining, then RSI's strongest determinism claim fails and must be revised. If the same calibrated pin cannot be reused across multiple systems without retuning domain-specific constants, then RSI's strongest unification claim fails and must be revised. 15.8 closing. I wrote this document as the baseline I wish I had every time I started a new RSI build, and realized that small conceptual drift in one chapter would cascade into contradictions 3 chapters later. If a reader takes only one thing from this primer, I want it to be this. RSI is a finite, explicit, positive ledger model with 2 gates. A configuration either holds, admitted by existence and persistent under change, or it transitions, driven past a threshold under available channels. Systems are not guessed from arrows. Systems are solved by closure, then arrows are drawn as maps of solved structure. When I actually use RSI, I treat part 14 as the operating console. The cards there are designed to prevent drift. They tell me what I must declare, which interface geometry I am allowed to use, which gate is being evaluated, and what counts as a failure. When I want to verify a derivation rather than just accept a story, I go to Appendix A and follow the audited path. I also keep one sentence on repeat because it keeps the whole project honest. Constants, vectors, and time coordinates are overlays, not primitives. They are calibrated mappings from the ledger carriers, EA, EF, AP, into a measurement interface, and they are produced after the scalar verdict, not used as hidden inputs to manufacture it. Table 4, Strong overlay prediction, test cards, compact subset. Observable RSI target, what compute? ISO predict a sharp frontier number atomic at Z crit approximately equal to 83, allowing a isotope Z, not narrow band for detailed Z greater than or equal to 84, with predicted front. Redshift shell effects, by track edge cases tier. Diagnostic Z, ing when multi-domain at Z equal to 82. Closure pushes configura and Z equal to 83 shans toward DC. 1 is stable or Z rises. Effectively, stable. Compare Z equal to 82 predict that the all edge cases, lead and Z equal to 83 cases, sit extremely close ments, are decay rapidly. Bismuth. To Z greater than or equal to DC equal to 1, so decay stable or stable ISO 84. Channels exist but can effectively topes appear be astronomically slow stable, while well above the. When barely inside the Z greater than or equal to 84 has frontier. Admitted band. No stable. Isotopes. Alpha beam scattering predicted transition. Deviation. No deviation off a heavy nucleus. Pure Coulomb from the at close app with energy sweep. Large RMN. Then a inverse approach or track large angle deviation once closest square deviation at events. Approach reaches the Coulomb macroscopic contact regime where scattering separations. NC equal to EF2 rands pushes overlay app the encounter toward pairs only at. DC approximately equal to 1. Very small. Closest approach few FM. Use a simple nuke compute NC equal to EF2 rands coupling requires extra clear pin, deuteron and map to an effective lands and fitted factors. Coupling scale or mid-nucleus bind 4 scale via declared the known outside the ion energy per new context length for X nuclear declared pin Cleon with R1 ample FEF NCR dominance or misses the to 2 FM. Range at scale by orders. FM scale of magnitude without new constants. Setup I pass kill. Heavy survey stable element topes by stability front number tier Z shirt the RSI. Stable nuclei for far beyond the near threshold longevity. Rutherford scattering deviation. Order of magnitude. Domain observable, rig, RSI target tolerance kill test. Gravity ZSS, pound Z approximately equal to 2.46 x 10 to 15 1%. Wrong sign or order. Rebka scale 22.5 meters of magnitude Tycho path. Gravity escape selectivity, HDC approximately equal to 1 at the escape threshold, any clean count. Exobase threshold tear example, heavy. Species escape under the same conditions. EMH 1 second photoionization, BT approximately equal to 13.6 EV, 0.1 EV ionized below thresh. Ton threshold scan old or remain bound. Above. Strong stability edge, nuclear Z crit approximately equal to 83.2 Z stable isotopes for reason Z83, weak 16 degrees Celsius, beta half-life, neutron, tone half 1 second factor 2 greater than 10x off after theta append scaling counted. Mixed Eddington limit, stellar LM approximately equal to 1.3 x 1031 10 to 20 stable star above. Surface WKG1 band without winds. Mixed hill sphere boundary R approximately equal to 1.5 x 109 meters, 5%. Stable Earth Satel Earth Sun, light well beyond. Table 5, compact prediction menu, test cards with explicit targets and explicit kill tests, adapted from the domain sorted card format I use in my longer campaign drafts. The full solve card still applies. This table only tells the reader where the quickest falsifiers live. Rig control threshold I use what I pin, and then reuse. H1 second, photoionizer, HNU approximately equal to 13.6 EVBT for the atomic EM pacing. T on map, single source case typically. Has theta approximately equal to +1. Escape T species gravity regime mapping scale. H. Dependent escape that makes DC approximately equal to 1 at exobase. Threshold then reuse across escape problems. Stability edge Z shirt approximately equal to 83 strong domain scale order. BI. 8 MeV per nucleon and overlay orientation versus EM, often. Summarized by theta approximately equal to 1 in that. Comparison. Free neutron life ton TN approximately equal to 879 seconds BT weak pinned once then reused. Time for weak half-life scaling with only decan theta varying. 2-source EM phase constructive versus D theta. 1 0 plus 1 as a cohere. Structive cases int overlay indicator reused in. Multi-source coupling cards. Exobase. Table 6, inverse parameter hunts. Examples of how I pin a mapping constant or pacing anchor from a crisp threshold, then reuse it. This is the posture behind one calibration pin, then reuse without retuning. Checklist item energy closure. Geometry met. Role discipline. Allocation discipline. Calibration reuse. Determinism language falsifier statement. Confine what I require before I call it an RSI result. I write the ledger explicitly and show that SE equal to. EF plus EA is conserved for the declared system, or I declare open boundaries in the exchange term. All distance or area scaling sits inside AP. I do not write stray R2 or 1 or 2 factors outside AP, except the audited 2 rands isolation in EQ. 11. I do not conflate gates, sys the existence gate now on a boundary interface, and DCIS the change gate becoming for transitions. If more than one partner matters, I use EQ. 10. And I report the share readout phi. I do not split EF by hand. Any calibrated mapping, for example BT, KCH, or a regime constant, is pinned once per regime and then reused. I do not introduce a new constant to save a failed prediction. I report transitions as threshold crossings under decan channel closure, not as intrinsic randomness. Every card has a kill test, a concrete counterexample that would force me to reject the claim or reject the framework. Table 7, closure checklist. The audit gates I enforce before I treat a solve as credible. This is the practical counterpart to the RSI guardrails, and it is the fastest way to stop myself from drifting into story mode. A hard math library, audited derivations, and